Hello everyone, my name is Tarun Malhotra. I am a lead software engineer here at InterviewBit and also take classes at Scalar Academy. Today's session is going to be a session which deals with basics of dynamic programming. That is, what is this paradigm? What kinds of questions can you solve using this paradigm? And we would try to solve some simple problems on DB today. But going forward, as and when we move on with these sessions, you should be able to be more and more confident with the idea of DP and how to apply dynamic programming in the problems where you can actually model those problems as DP problems. Okay, cool. So before actually coming to the definition of dynamic programming, describing what this paradigm is, let's take an example with whose help we'll actually figure out that what is the reason of coming up with a paradigm like this. Okay, what kinds of problem can you actually hope to optimize further using this paradigm of dynamic programming? Cool. Yeah, the very first problem that we'd want to see without actually knowing about DP would be the problem of Fibonacci numbers. I am sure that most of you would have heard about this problem of Fibonacci numbers. The problem is as follows. You want to figure out the nth Fibonacci number, and the Fibonacci numbers are as follows. The first Fibonacci number by definition would be equal to, let's say, 1. The second Fibonacci number would be equal to, let's say, 1 again. And now for any Fibonacci number n, where n is greater than 2, the number can be defined using the previously defined Fibonacci numbers. Okay, so for fn, where n is greater than 2, you can say that the nth Fibonacci number would be equal to the summation of n minus 1th Fibonacci number plus the n minus 2th Fibonacci number. I hope this definition should be clear to everybody. The first Fibonacci number is 1, the second Fibonacci number is 1. Now, and for any n which is greater than 2, the nth Fibonacci number would be the summation of the last two Fibonacci numbers. Okay, the n minus 1th and the n minus 2th. Now, I am pretty sure that just by looking at the definition of Fibonacci numbers, everyone would be clear that the definition of Fibonacci numbers is nothing but a recursive definition, right? You are actually defining a number recursively using the previously defined numbers. Okay, so how would you go about solving this? The problems of recursion can actually be very easily visualized by drawing a recursive tree. I hope all of you should be able to appreciate that. Let's take an example and see if we are able to appreciate that completely. Okay, so let's say I wanted to compute the 7th Fibonacci number. Okay, I wanted to compute the 7th Fibonacci number. So let's say, yes, this is a state that I want to compute the 7th Fibonacci number. Now, by definition, if I want to compute the 7th Fibonacci number, I should go to the number n minus 1th and the number n minus 2th. Okay, so f7 would actually be nothing but a summation of f6 and f5. I hope this should be crystal clear to everybody that this is just a recursive definition. Now, we do not know what f6 is, and f6 can again be computed using the same definition that we have given above by saying that f6 would be nothing but f5 plus f4. You can keep on drawing this tree, and now f5 can be represented by, let's say, f4, f3. f4 can be represented as the summation of f3 and f2, where f3 can be represented as the summation of f2 and f1. Now we know that we need not define this f2 into smaller subproblems, because by definition, I already know that f2 is equal to 1 and I already know that f1 is equal to 1. So now I know that the answer to this is already known, so no need to divide it further. The answer to this is already known, no need to divide this further. The answer to this is already known, no need to divide it further. So we call these cases, which are trivially easy to answer themselves in any recursive problem, as the base case of a recursive problem. Okay, so also just to give a context why we are discussing about recursion should be very clear in a bit when we actually move from recursion to DP. So just hold on for a while and understand this properly. Okay, so this would be a base case. This would be a base case. That is a problem for whom we know the solution already. This would also be a base case. Now, is F3 a base case? No, F3 is not a base case because I do not know the answer of F3 already. So I would define F3 into smaller problems as the summation of F2 and F1. Now, F2 is a base case and F1 is a base case. Now, let's come to the node which is still remaining, F4. You would realize that this F4 would again be expanded as an entire subtree. Does it make sense? F4 would be expanded to the summation of F3 and F2, so on and so forth. F3 would be expanded to a subtree. F2 would be again expanded to a subtree, and this would go on. And you can also look at F5. This would also be expanded to a subtree where the base cases would only be F2s and F1s. I hope this makes crystal sense to everybody. So we represented this Fibonacci problem as a recursive tree because it's a recursive problem. Now, once I have defined this, now to compute this problem, you will essentially have to compute every single node in this recursive tree, right? You can start from the very top and then you will be computing every single node in this recursive tree. Now the problem arises that how much time would I actually require to compute the value of F7 or any F9? To compute the value of F7, I will have to compute this entire tree. So to estimate the time required to compute that, I would suggest that let's first of all estimate the number of states that are there. Okay. From looking at this diagram and realizing it intuitively, you would realize that first of all, what is the depth of this tree, right? So you start with F7 and what is the farthest distance where you would be actually finding a base case? The farthest distance would actually be 7 in this case because you started with F7. And in each iteration at each level, you at least have one node which was just reduced by 1. Okay. So the depth of this tree is 7 in this case, or to speak generally, the depth of this tree would be n if you are computing the nth Fibonacci number. Okay. If the depth of the tree is n, the fan factor of the tree is 2, you would realize intuitively that the number of states here would be of the order 2 power n. I hope this makes sense to everybody. The number of states would be of the order 2 power n. Now, let's actually figure out the amount of time required to compute a state. That I would claim time required per state in this case is nothing but a constant amount of time. Let's call it order 1. Why? Because if I want to compute this state and I already know the answers to F4 and F5, I just need to add them up. So the time required per state, if you are already assuming that you know the states below it, would be order 1. There are 2 power n states to be computed. Every state would be computed in order 1 time. So time complexity is definitely going to be exponential, is definitely going to be 2 power n. This is one way to look at it. The other way to look at it would be solving the recurrence relationship. The recurrence for this problem would be that you have a problem of size n. You are reducing that problem of size n to a problem of size n minus 1 and a problem of size n minus 2. And you are combining them by spending some constant amount of time. If you solve this recurrence, you will again get the same time complexity, which is exponential time complexity 2 power n. I hope till this point in time, everything makes sense, that to solve a Fibonacci number, you are essentially giving exponential time. Now let's actually draw some observations in the tree that we have just formulated. The observation that I want you guys to draw, that there are a lot of states that you are computing that you could have avoided computing. Okay, listen it again. I am saying that there are a lot of states here which could have been avoided. You could have avoided computing them just because you already knew the answer of those states. Okay, let's see some examples. So have a look at it. You have already computed f of 3 here. Does it make sense? But you are again seeing this f of 3 here. And that's not all. When you actually solve this f of 4, you again solve f of 3 here, right? And when you actually solve f of 5, you are essentially going to solve f of 4 and f of 3. This f of 3 is again repeated. To solve this f of 4, you are again going to call f of 3, which is again repeated. So you see that there is a lot of repetition happening here in the states that we have defined. Okay, in this recursive tree, there are a lot of repetitions. and you could have actually avoided doing those repetitive computations. Try to understand it's not only about one state being repeated, it's about so many entire subtrees being repeated. Okay, so if this F3 was already known, you could have avoided computing this entire subtree. Now, if this F4 was already known, you could have avoided computing this entire subtree. If this F5 was already known, you could have avoided computing this entire subtree. And this, if F2 was already known, which is a base case, you could have avoided computing this subtree. And this F1 is again a base case. You can just remove it because that's a problem that you already know, or you can assume that F2 could have been divided into F1 and something. And this is, so basically this is just a base case. So now you actually see that the problem, which was a binary tree in the beginning, is now reduced to nothing but a linked list. Does it make sense? There is no tree here now. The recursive tree is no longer a tree in this case, just happens to be a list of some states that you are computing. Okay, so you see that the number of unique states that you have, is just of order n. You only have order n unique states here, but in the recursive tree you had 2 power n states, and now you actually get the idea that you could have actually stored the values of these states, and whenever you wanted to get those values again, rather than recomputing them, you could have just utilized the answers that you already had. I hope this makes sense to everybody. So we have actually reduced a problem which had so many number of states into a problem with lesser number of states, just because the number of unique states that I had, was smaller than the number of total states that I was seeing. Okay, so this is the basic idea. Now let's actually come to the definition of dynamic programming and see how this idea can be extended and can be utilized to solve a lot of problems. Okay, cool. So let me actually take you to one interesting definition of dynamic programming. A way to put it would be that dynamic programming is a method of solving complex problems by breaking the problem down into collection of simpler subproblems. So you have a bigger problem. You are breaking that bigger problem into a collection of smaller problems of the same type. Now you end up solving those smaller problems exactly once, and then you utilize those solutions to construct the answer to a bigger problem. Okay, so what exactly you are doing? Let's look at this problem. That you have a problem which could have been solved using smaller subproblems. So Fn could have been solved using the answers to smaller subproblems, where n would be less than this n dashed. And now you end up solving those subproblems exactly once. So you are only going to solve F6 exactly once, F5 exactly once, F4 exactly once, and so on and so forth. And you are then going to utilize the answers to those smaller problems to construct the answer to a bigger problem. Okay, so this is exactly what we will end up doing here. Let me actually just tell you how we can solve this problem here, right? So you know this is a recursive problem. So a simple recursive code of this solution would be that, let's say you wanted to solve, let's say you want to return an int. You want to say int get Fibonacci number. It takes as input the nth Fibonacci number that you want to return. So this is a recursive code. In any recursive code, you start with the base case. This is something that you should always remember. So you start with the base case. The base case here happens to be n equal to 1 or n equal to 2, right? So what do? You say, first of all, let's check for a safety case that if n is less than one, then let's say it's not defined. So you return -1, let's assume. Now, if this is not the case, if n happens to be less than or equal to 2, that is, if n happens to be exactly 1 or 2, that is, you want the first Fibonacci number or the second Fibonacci number, you are just going to return 1. This is the base case that we have by definition. Now, after this, for any other n, you would simply be calling f of n minus 1 and f of n minus 2. So a simple recursive solution would look something like this. That's simply going to return get fib for n minus 1 plus get fib for n minus 2. This is a simple recursive problem. but you see a lot of recomputations are happening here. So what do? You just add memoization. So what do? This is plain recursion. In plain recursion, you just add something which is called as, let's say, memoization. Just because you see a lot of states being recomputed again and again. So rather than recomputing them, let's actually store them and only compute them exactly once. So how to store them? Let's say you now have an array of size, let's say n, which is initialized by, let's say, -1 to begin with. Make it n+1 if you are using it. Let's assume this was one indexing array. Okay. Now you initialize the base cases here by, or let's say, yeah, you can initialize the base case here by saying that f of 1 would be equal to f of 2 would be equal to 1. And now what do? When you actually want to compute that, you first check if that n-1th value was already computed or not. So rather than just doing this, you actually do something else. So now you first check if f of n-1 was still equal to -1, that is, it was still not computed, only then you make a call to compute it. So you now say f of n-1 would be equal to get fib n-1. You now have the value here. Similarly, you do that for f of n-2 and see if that is equal to -1. You compute the value and store it there. And then once you have done both of these operations, you simply return the summation of them. So just by changing the solution a bit, you have reduced a lot of time complexity. The time complexity now becomes order n. Okay. The space complexity also becomes order n. Cool. So this was a very, very basic problem. Let's move ahead. You can actually reduce the space complexity, but let's leave it as a homework for you guys to understand that how you can actually reduce the space complexity here. So now let's actually move to a lot more interesting problems on dynamic programming. And before that, let me give you the formal definition here, which will help us to figure out when to use dynamic programming. Okay. So the formal definition of dynamic programming is that a problem can be modeled into dynamic programming if it has two features. So what are the features for a problem to be modeled in dynamic programming? The first feature is that the problem exhibits optimal substructure. What is optimal substructure? We'll just come to it in a moment. The second feature is that you should be seeing overlapping subproblems. So these are the two features that you look in any problem to make sure whether that problem can be solved using the dynamic programming paradigm or not. Now let's explain these two features in more detail. Okay. Optimal substructure feature simply means that your problem, the solution to the problem, the optimal solution to a bigger problem can actually be constructed using optimal solutions to smaller problems. Okay. So the optimal solution to a bigger problem can be computed using the optimal solutions to smaller problems. So this is the optimal substructure property. That is, let's say here you want to compute f of 7. Can you actually compute f of 7 using the smaller problems ka answers? Can you compute it using f of 6 and f of 5? Yes, you can do that. Right? Can you compute f of 6 using f of 4 and f of 5? Yes, you can do that. So a problem which shows that you can compute an answer to a bigger problem using the solutions to smaller problems is called as optimal substructure. The problem being showing optimal substructure. Okay. The second part is that you should see a lot of overlapping subproblems. Okay. So what is overlapping subproblems? That is, you should be able to see subproblems which were otherwise being repeated several times, and now you can just memorize them so that you do not compute the same problem again and again. Okay. So just because a problem which exhibits overlapping subproblems, you see an opening that yes, you can exploit that overlapping subproblems and reduce substantially the number of subproblems that you actually compute. Okay. So overlapping subproblems. That is, you should see a subproblem being computed again and again. The moment you see that, you can stop doing that, and then you call your solution to be a dynamic programming solution. Okay. So you see subproblems being computed multiple number of times. Now, these are the two features which will help you to judge whether a problem can be solved using a dynamic programming paradigm or not. Now, keeping this in mind, let's try to solve a few problems, and then we would keep on building on the concepts using those problems. Okay. The very first problem that I would want to discuss with you guys is called as the problem of stairs. So this is a problem that is actually asked in several product companies. This problem was asked at Morgan Stanley. This problem was solved at Amazon, was asked at interviews of Amazon. This problem was also asked at interviews of Intel. So this is a problem which you, just by looking at the companies that have asked this problem, you guys would have gotten an idea that yes, this happens to be a very, very interesting application of dynamic programming. Okay, cool. Let's define the problem. The problem is as follows, that you have n stairs. Okay, you have n stairs. So let's call it the first stair, the second stair, the third stair, and let's call it the nth stair. You have n stairs. Let's assume originally you are at the first stair. Okay, so originally you are at the first stair. Okay, now at every stair you have two options. Option one that you have is to just from the ith stair go to the I plus 1th stair. The second option that you have is that from the ith stair you go to the I plus the second stair. So I plus 2th stair. Okay, so what does that mean? So let's say you were at the first stair. The first option that you have is to go to the second stair, or you could have actually chosen to directly jump to the third stair. You could have avoided going to the second stair and directly jump to the third stair. These are the two options that you have. The question asks you that you want to figure out the number of ways to reach the nth stair from the first stair. What does that mean? That how many distinct number of ways are there in this problem which will take you from the first stair to the nth stair. I hope the problem is clear to everybody. Okay, cool. Now let's actually look at a couple of examples and see what kind of a pattern do we observe. Okay, let's take an example for what happens if the number of stairs was only equal to 1. So let's say there is only one stair. You are at the first stair, you only have to reach the first stair. How many number of ways that are there? The number of ways that you have is only one. That you can choose not to do anything because you are at the first stair itself. You cannot do anything else but to stay at that stair. Now let's look at the example 2. What happens if you have n equal to 2? That you happen to be at the first stair and you have to reach at the second stair. How many distinct ways do you have? So you have at the first stair, you have two options, either to go to the second stair or the third stair. The third stair does not exist. So there is only one option, that you can just go to the second stair. And the moment you go to the second stair, you have reached the solution that you have. You can only stay there, cannot go anywhere else. So the number of ways for this n equal to 2 problem would also be equal to 1. Now let's look at the example 3 that we have. So let's say now we have n equal to 3. You are at the first stair, you want to reach at the third stair. What all options do you have, people? You are at the first stair, you have two options. Either from the first stair, you can go to the second stair, or you have the second option which says from the first stair, you can go directly to the third stair. Okay? If you actually choose to do the second option, that is from the first to the third, you have already reached your destination and you can only stay there. You cannot do anything else. Now let's look at the first case that you assume that you can move from the first to the second. If you move from the first to the second, what options do you have from the second stair onwards? You can either go to the third stair or you can jump to the fourth stair, but fourth stair does not exist. So you only have one option, that is to go to the third stair. Now this also completes the entire path and you have reached the solution. So you see that there are two ways to solve this problem. If n was equal to 3, the number of ways that you have is 2. Does it make sense to everybody? We have seen 3 examples here. N equal to 1, n equal to 2, and n equal to 3. And we now know that what are the number of ways that you have to reach to your nth stair. Cool. We have understood the problem. Now let's see, can we, how I would approach to a greedy problem. Okay. One thing that I just told you, that it's very important to check whether these features are there in the DP problem. So let's check whether these features are actually there in the DP problem. The first feature is there an optimal substructure? Okay. So do you see an optimal substructure? What does that mean? Can you solve a bigger problem using the answers to smaller problems? Okay. So let's try to answer that. Let's take any bigger problem. Let's take n equal to 5. Let's assume that you had 5 stairs. Now let's assume if you want to compute the number of ways to reach the 5th stair from the first stair, and somehow you already know the answer to number of ways to reach the 4th stair and the number of ways to reach the 3rd stair. Let's say somebody told you that number of ways to reach the 3rd stair is equal to A, and the number of ways to reach the 4th stair is equal to B. Now, can I actually compute the number of ways to reach the 5th stair? Okay, let's try to find out. So if I want to reach the 5th stair, you guys tell me what are the options that I have for the penultimate step. If the last step that I make happens to be the 5th stair, that is I want to reach the 5th stair, what options do I have for the penultimate stair? That is the second last stair that I would have taken. The option 1 that I have for the penultimate stair is that I would have been at the 4th stair. Does that make sense, guys? From the 4th stair, you could have gone to the 5th stair. This is one option. The second option that you have for the penultimate stair would be that you could have actually gone from the 3rd stair to the 5th stair. I hope it makes sense. The options that you have for the penultimate stair would either be from the 4th stair or from the 3rd stair. Okay? So you could have actually, one option is you could have come from the 4th stair to the 5th stair. The other option is that you would have come from the 3rd stair and jumped directly to the 5th stair. Now, I know the number of ways I would have reached the 4th stair from the 1st, which is nothing but B. If I know that from the 4th stair, I only have one option to go to the 5th stair, which is just to take a single step, I will multiply this by 1 because I only have one option from the 4th stair. So B into 1. Then the second option was that I come to the 3rd stair somehow and then jump directly to the 5th stair. If I come to the 3rd stair somehow, number of ways I already knew, let's assume was equal to A. So I do A. And now from 3rd to 5th, if I want to have a jump, I will just multiply it by 1. These were the two mutually exclusive and exhaustive options that I had. So I will just add them up to get my complete answer. So number of ways to reach the 5th stair from the 1st stair would be nothing but the number of ways to reach the 4th stair multiplied by 1 plus the number of ways to reach the 3rd stair multiplied by 1. Okay, you can actually generalize this and say that number of ways to reach the nth stair is nothing but number of ways to reach the n minus 1th stair multiplied by 1 plus number of ways to reach the n minus 2th stair multiplied by 1. So this also happens to be a problem which very interestingly mimics the problem that we had for Fibonacci numbers. Does that make sense to everybody? Have we actually just proven to ourselves that we see an optimal substructure here, that we can actually solve a bigger problem using smaller problems? If you can see that optimal substructure is there, using that we have arrived at a recurrence relationship as well. Now looking at this recurrence relationship, we also see that a lot of states would be repeated. So yes, there is an overlapping subproblem point here as well. So this problem can be very easily solved using dynamic programming. Does that make sense to everybody? That you have actually proven to yourself that this problem actually has overlapping subproblems and optimal substructure both. So you can solve this problem using the dynamic programming way. Cool. So once we have established that how to look at a problem and figure out whether you can solve it using DP approach or not, let me actually describe to you two ways to solve a DP problem. Okay. So this is one way to look at a DP problem. Hold on for a while. In the next question or so, I would be discussing another way of looking at DP problems and solving them. In the meanwhile, let me tell you that there are two broad ways to solve any DP problem. Okay. One of them happens to be a top-down approach. What is meant by a top-down approach? A top-down approach means that you just write a recursive code as we did in our first problem for Fibonacci, and with the recursive code, just because you see that there are overlapping subproblems, and you can actually reduce the time complexity by memoizing those subproblems. That is, storing the answers to those subproblems. You can just, in the recursive code, just throw in memoization, and you would get a solution for the top-down approach using DP. I hope it makes sense. That what did we do in our first solution? We just wrote a recursive code and just added memoization. That is, we just added an array where we actually just added some states where we actually stored the answer to those states and did not compute them again. So a simple recursive problem code with throwing in memoization in it would actually solve your problem top down. Why do we call it top down? That you actually start solving your problem from the answer that you want. That top problem gets divided into smaller problems, and this keeps on happening. So you move from the top to the down. This is one way of solving DP problems. The second approach of solving DP problems is bottom up. What does that mean? The bottom up approach means that you actually start constructing your DP solution from the base case. Okay? So you actually have the answers to base cases already. This is what we know. You already have the answers to base case. Using the answer to those base case, compute the state that you could have computed just by using those answers. So in case of Fibonacci, if I know the answers to f of 1, which is a base case, and f of 2, which is a base case, both of them were equal to 1. Using these two, can you tell me what state can I compute? Using these two, I am pretty sure that you guys would be able to appreciate that you can compute, using these two states, you can compute the third Fibonacci state, which is just a summation of f1 and f2, which happens to be 2. Now you are constructing your solution bottom up. You start with the base cases and you keep on constructing your solution. Now you have the answer to f of 1, f of 2, and f of 3. Which state can you compute using this information? So my suggestion would be that you can now use the answer to f of 2 and f of 3, and you can compute the answer of f of 4. Does that make sense? It would just be the sum of them, which would be equal to 3. Now you have constructed the answers till f of 4. Now you can construct thereafter as well. So now you can use the answer to f of 3 and f of 4 and create the answer to f of 5, which happens to be just the sum of them, which happens to be 5. So you would see that you can just keep on creating answers, constructing answers in the bottom-up approach as well. So this was the first answer that you knew just by the base case. Second answer that you knew just by the base case. The third answer that you computed was this. The fourth that you computed was this. The fifth that you computed was this. And the sixth would be, just using f of 4 and f of 5, you can compute f of 6, which would just be 3 plus 5, which is 8. And this would be the sixth step that you compute. So you now understand that there are two ways to solve DP problems. You can either write your code in a top-down approach, which is recursive plus memoization, or you can write your code in a bottom-up fashion, which is just by using the base cases, you keep on building your solutions to bigger and bigger problems. Okay, so this was just a big bit of a digression that we took to explain that to you, that different ways of solving DP problems. Before that, we made sure that all of us understand that DP problems that can show the features of optimal substructure, that is a bigger problem being divided into smaller problems and utilizing the answers to smaller problems to solve the bigger problem. This is the first feature that problems being solved using dynamic programming paradigm should have. The second feature that we have is of overlapping subproblems. That is, when you divide a bigger problem into smaller problems, you see a lot of smaller problems being overlapping. And you can optimize them by having memoization, that is storing the value somewhere, and the next time you see the same problem, just utilizing the value and not computing it again. So these are the two features that any problem should show if you have to solve that problem using dynamic programming. Cool. Now let's move ahead, and then using the next question, I would try to explain to you guys that what is the difference between greedy solutions versus dynamic programming solutions. So we would look at a problem and see in what problems do you see greedy solutions not being able to solve the problem for you and you choosing to go to a DP solution. Okay, cool. The problem is a problem which is again a very famous problem, problem of robbers. This is the problem of robbers. This problem, again, we have seen this being asked in the interviews of Amazon, and we have asked this problem being asked in the interviews of the shop. Okay, so these are the two companies that we have seen this problem being asked at. Now the problem is as follows. You are a robber. Unfortunately, you are a robber. Okay, you see a street where there are n houses. You see a street where there are n houses. Every house has some gold coins in it. Okay, so let's assume the first house has 2 gold coins, second house has 7 gold coins, third house has 9 gold coin, 3 and 1. So these are the gold coins that are present in these houses that you see on a single street. Okay, now you are a robber. So what would you do? You would want to rob these houses. Okay, what is the function that you would want to maximize? You would want to maximize your robbery. Does that make sense? So if unfortunately you happen to be a robber, what would be your optimization function? That you would want to maximize your robbery. Okay, if you want to maximize your robbery and there was no constraint, then you would have actually robbed every single house. Does that make sense? Right? But let's now add, to make the problem interesting, let's add a constraint. The constraint is as follows, that every 2 adjacent house on the street are connected by an alarm. Okay, so you see an alarm between the first and the second house. You see an alarm between the second and the third house, between the third and the fourth house, the fourth and the fifth house. So you see there are some alarms being placed between every 2 adjacent house. What does that alarm do? That alarm simply rings if any one of these 2 houses are being robbed. So what does that mean? It means that if this house is being robbed by you, this alarm would go up and this alarm would also go up. So if this alarm goes up, the people in this house will wake up and you will no longer be able to rob this house. Similarly, if this alarm goes up, people in this house will also wake up, and unfortunately or fortunately for them and unfortunately for you, you cannot rob this house also. Okay, so this is the problem, that the moment you rob one house, there are your left house and the right house now cannot be robbed. I hope everybody gets the problem. Okay, how would we go about solving it? The answer to that, so let me just remove the things that I just drew over this problem, and let's first of all see, can I actually come up with a greedy solution to this problem? So before actually answering, can I have a greedy solution, let me actually define for you very quickly what a greedy solution is. A greedy solution is that without looking at what holds for you in the future, without looking at the future numbers, can you just make a call by looking at the number that you are just seeing? By looking at the thing that you are just seeing, can you actually figure out the solution to the entire, can you actually make a choice by looking at the current number? So what does that mean? You can claim that you have a greedy solution if you can think in this way, that just by looking at this house, the first house, can you make a decision of robbing this house or not robbing this house? Just by looking at the first house, can you make a decision of robbing this house or not robbing this house? Is it possible? You cannot. Similarly, can you say, I will never rob the first house? You cannot do that. You will actually have to look at the houses thereafter to figure out whether robbing this house makes sense or not. Right? Why do I say so? Because the moment I rob this house, I am changing the landscape of the problem. The moment I rob this house, I am enforcing a constraint on me that I can no longer rob this house. Does that make sense? And without looking at what holds for me in the future, would I ever be fine with imposing these constraints? No. So that is why I would tell you that greedy solution here would not work. Just by looking at this 2, you cannot make a decision whether to rob it or not. Similarly, just by looking at this 7, you cannot make a decision whether to rob it or not. So the problems where you have a choice, the problems where you have a choice and you cannot take any choice greedily without looking at what holds for you in the future, greedy solutions won't work. So here, greedy solutions won't work. That may make us a bit unhappy that why greedy solutions are not working here. Okay, so let me just define the problem again. Whenever you see a choice or a set of choices, you see a set of choices and you cannot make a greedy decision, greedy problems won't work. Okay, so now if greedy solutions won't work, let's actually try if we can see that a dynamic programming solution can work. What does a dynamic programming solution do? It essentially allows you to explore all the possible choices that you had. So what does a DP solution do? The moment you see a set of choices and you see that you cannot make a choice randomly, you cannot just greedily make a choice, DP solution would say that let's explore all the choices that you have. DP solutions would allow you to do that you can actually explore all the choices that you have. And if you can explore all the choices that you have, then you can think in DP direction. Greedy won't work. Let's think the dynamic programming way. Before actually making sure that, before actually jumping to dynamic programming, let's see if the two features that we discussed before, does those features hold for this problem or not. The first feature that I told you was, does this problem show optimal substructure? What does that mean? If you know the solution to a smaller problem, can you know the solution to a bigger problem? Okay, so let me prove to you guys that yes, this problem does have optimal substructure. Okay, so let's actually come to the first feature that we had of optimal substructure. Let's actually prove to ourselves that yes, optimal substructure as a property is being held in this example. Okay, how to prove that? Let me give you an example. So let's say somebody told you that, hey man, don't worry, I know the best answer for robbing houses till this point, till the first 4 houses, and I'm telling you that I definitely robbed the last house. Okay, so I'm telling you the best answer, the best number of gold coins that I can accumulate by robbing the first 4 houses and making sure that I rob the 4th house would be something like this. Okay, somebody told you this answer. Let's call it maximum robbery for the first 4 houses. Somebody also told you the answer to another question, that I am robbing the first 3 houses, man, and I have definitely robbed the 3rd house. I also know the answer to that. So somebody tells you that yes, maximum robbery 3 ka answer you already know. Now if you know the answer of maximum robbery 3 and maximum robbery 4, can you actually construct the answer of maximum robbery 5? Yes, you can do that. Why you can do that? Because for the 5th house, you have 2 choices. Either you can rob this house or not rob this house, right? If you choose to rob this house, what is the constraint that you are imposing on yourself? The constraint that you are imposing on yourself is that you can no longer rob the 4th house. Does that make sense, people? If you're robbing the 5th house, the constraint that you're making on yourself is that you cannot rob the 4th house. So what is the house that you can rob now? You can rob the 3rd house for sure. So if you want to answer of maximum robbery 5, you can either choose to rob that house. If you choose to rob that house, how many gold coins are you accumulating? You are accumulating the gold coins at the 5th house because you're robbing it, right? So you're accumulating the gold coins at the 5th house. Now your problem reduces to finding the best gold that you can accumulate by robbing the first 3 houses. So you get maximum rob 3. This is one option that you have. That was you wanted to rob the 5th house. If you do not rob the 5th house, what is the option that you have? If I do not rob the 5th house, the gold coins that I'm robbing from the 5th house would be 0 because I'm not robbing it. And if I'm not robbing it, am I imposing any constraint of not robbing the 4th house? I am not. So I will just use 0 plus max rob 4. I have these 2 options. The best answer out of these 2 options I will take. So I will just say that the maximum out of these 2 would give me the answer. So either I can rob the 5th house or I can not rob the 5th house, and the maximum of these 2 would give me the answer. I hope things make sense to everybody here. Let me just very quickly dry run the answer. So I have these houses 27931. So I am defining my state max rob I as the maximum robbery that I can get from the ith till the end. So I want to compute the answer to max probability 2. So I have two options. So I will say the best answer for robbing the first till the fifth house would be two options, either to rob the first house. If I rob the first house, I will get 2 gold coins by robbing the first house. Plus, I will reduce my problem to a smaller problem of saying, let's now try robbing the third house, because second house can no longer be robbed. The second option that I had was that I can choose not to rob the first house, but I can now try robbing the second house. Does it make sense, everybody? This bigger problem gets reduced to 2 smaller problems. I can now solve this smaller problem M3 in the same way again. I can say either I can rob the third house or not rob it. If I rob the third house, I can say I will get 7 coins. Plus my problem reduces to robbing. This is 1, 2, 3, 4, and 5. If I rob the third house, my problem reduces. So I will get 9 coins. And my problem reduces to checking if I can rob the fifth house. So I will say plus M5. Or I can say that I will not rob the third house, and my problem reduces to finding the best for M4. Similarly for M2, I will say either I can rob the second house, which will give me 7 gold coins. And if I rob the second house, I can now try robbing the fourth house. Or I can not rob the second house and try getting the answer to the third house. Now you guys would appreciate that I need not compute this M3 again, because this M3 would be computed here automatically, right? So I will just compute this once and not compute this M3. So what will I do? I will try computing M5. M5 says you can either rob it or not rob it. I would always want to rob it because there is no house going forward. So this is a base case which will give me 1 gold coin. So 9 plus 1 becomes 10. The second option that I had was 0 plus M4. M4 would again be divided into a smaller problem of either robbing it or not robbing it. I hope it makes sense to you, right? So you start from the first, start dividing into smaller problems, and then you keep on actually going till the base case and making sure that every subproblem is computed only once. Okay? What are the initial values? Initial value for everything would be, let's say, -1. That is, you have not computed it. The moment you compute it, you update the value there. Okay? What would be the base case in this case? The base case would be that when you reach M5, that is the only house that you are left to rob. You would always want to rob it. Okay, so M5 would be equal to 1. This would be a base case. I hope this makes sense to everybody. Right. So let's actually move to the next question. The last question is as follows. The problem is that there is a party going on. Okay, there is a party going on. And the party can be attended by N people. So there are N people who can go to the party. Every person in the party has 2 options. One option is that he or she can enjoy the party all alone by himself or herself. Okay, every person has 2 options. So let's say person I has 2 options, either to enjoy the party alone or to enjoy a party in a pair with any other person. Does the question make sense? There is a party going on. The party can be attended by N people. Every ith person in the party has 2 options. Option 1 is that you can enjoy the party all alone by yourself. Option 2 is that you can actually pair up with any other person in the party and enjoy the party as a pair. Now the question actually asks you that how many unique ways are there for those N people to enjoy the party. Does it make sense? Okay. So which company this question was asked at? This question was, I myself asked this question several times at Direct Eye, and I've seen this question being asked at several other companies as well. So you have to figure out how many different unique ways are there for those N people to enjoy the house party. Okay, cool. So let's actually take some examples. Let's say N was equal to 1. If there is only one person, how many ways that person can enjoy the party? There is only one way. The sad way is that he can only enjoy it all alone. So number of ways would be equal to 1. Does it make sense, people? Now let's say there are 2 people. Example 2, N equal to 2. There are 2 people in the party. Let's say number 1 and number 2. What are the ways that these 2 people can enjoy the party? One way would be that the person 1 is enjoying the party all alone. Okay. And person 2 is also enjoying the party all alone. This is one way. Second way would be that person 1 and 2 have paired up and they are enjoying the party together. Does that make sense? Are there 2 ways here? The answer to this problem would be 2. That number of ways would equal to 2. Okay, cool. Now let's actually take another example of, let's say, what happens if there are 3 people in the party. If n is equal to 3, how many ways do you see the 3 people enjoying the party? Okay, cool. So 1, 2, and 3, how many ways are there for the 3 people to enjoy the party? Let's actually formulate them. Either all 3 of them can enjoy the party alone. The second option is that the person 1 and 2 are enjoying the party together and the person 3 is enjoying the party alone. Third option is that person 1 and 3 are enjoying the party in pair and person 2 is enjoying the party alone. The fourth option that we have is maybe 2 and 3 are enjoying the party together and 1 is enjoying alone. So there are 4 ways. This is 1, this is 2, this is 3, and this is 4. So number of ways in this question would be equal to 4. Cool. So we have discussed that for three people in the party, there are 4 ways to enjoy the party. Let's now actually try to see whether this problem can be solved using a dynamic programming approach or not. What were the features that we discussed? The first feature was optimal substructure. Do you see optimal substructure here? Let's try to figure that out. Let's say you already know the number of ways 3 people can enjoy a party, which we already know is 4. And let's say we already know the number of ways in which 2 people can enjoy the party, which we already know is equal to 2. Now let's say we know the number of ways 3 people can enjoy the party, we know the number of ways 2 people can enjoy the party. Can I actually figure out the number of ways 4 people can enjoy the party? Can I actually figure that out? To figure that out, do you try to answer the question that what is the element of choice for the 4th person? The 4th person, the first choice that he has is either to enjoy the party alone or he or she can pair up with anybody else. Okay? Other option is that he or she can pair up. If he enjoys the party alone, do you think the problem reduces to the number of ways 3 people can enjoy the party? Let's say we already know the answer to the number of ways 3 people can enjoy the party, which was 4. Now the 4th person comes, and if he's enjoying the party alone, can you just say that just because he's not doing anything but enjoying the party alone, the number of ways would just be number of ways 3 people can enjoy it, and the 4th people joining them and not doing anything, so that's why multiplied by 1. Does that make sense, people? So you can say number of ways 3 people can enjoy the party multiplied by 1 if the 4th person is enjoying the party alone. On the other hand, if the 4th person decides to pair up with somebody, okay, you guys tell me which all people he can pair up with. There are 3 people in the party already. I am the 4th one coming. I decided I want to pair up with somebody. I have 3 options in front of me to pair up with them. Does that make sense, everybody? There are 3 people already in the party. I am the 4th one. I want to pair up. I can pair up with any one of those 3. So what will I do? I will say that I have n-1 options to pair up. So if I'm solving the problem for 4th person, there are 3 ways for me to pair up with somebody. Okay. The moment I pair up with somebody, let's say I paired up with the 2nd person. What does that mean? It means that the 2nd person and I are occupied. We cannot pair with anybody else, but the remaining 2 persons can do whatever they want to. So if you see that whenever the 4th person is coming and he has 3 options when he wants to pair up, if he pairs up with any one of them, now 2 persons out of these 4 people are paired up. So the remaining people that are left are n-2. And if you already know the answer of solving the best answer for n-2, you will just utilize that, which in this case is equal to number of ways for 2 people to enjoy the party. You will multiply that by the number of ways you can actually leave out 2 people, which is n-1. These are the 2 ways that you see. These ways are mutually exclusive and exhaustive. You can just add these 2 ways to get the answer to how many ways 4 people can enjoy the party. So what did I do? I have just proven that this problem shows optimal substructure, because that is the first feature that I need to prove to see if a problem can be solved using dynamic programming or not. How did I prove it? I assume that, let's say I know the answer for W2. That is what say if there are 2 people in the party who are enjoying, how many ways they can enjoy. If I know the answer to it, let's say that is equal to 2. If I also know the answer to, let's say, 3 people enjoying the party, which is, let's say, 4, I already computed the answer to these 2 things manually. Now I am trying to utilize these two answers to compute the answer for 4 people in the party enjoying. So I am saying, can I actually get this answer using these two smaller answers? If I can do that, then I will prove that this problem has optimal substructure. So how do I prove that? I just said that for the fourth person, the element of choice is that he can either be alone in the party or can pair up with anybody else in the party. If that person chooses to remain alone in the party, that actually means that he is just joining the party, not changing any dynamics of the party. The number of ways would still be number of ways for 3 people to join the party. They can pair up, they can do whatever they want. I will just multiply 1 with that because the fourth person is just going to the party and not pairing up with anybody else, not changing any other dimension, not changing any other part of the problem. The other option that the fourth person had was that he can pair up. If he chooses to pair up, he pairs up with one person. The number of people remaining in the party becomes n minus 2, which is in this case 2. I already know the answer to that problem, that how many ways 2 people can join the party. I will multiply W2 with n minus 1, because for the fourth person, he had n minus 1 options to pair up with anybody. These are 2 mutually exclusive and exhaustive options. What is mutually exclusive and exhaustive? Mutually exclusive means that when you combine all these options together, you are not leaving. These 2 options do not have any common data point in them. So do we think that these 2 have any common thing in them? No, because one says that the fourth person is enjoying all alone. The other says the fourth person is pairing up. So there cannot be any duplicate answer in these 2 options. So these 2 options are definitely mutually exclusive. What do I mean by saying mutually exhaustive? Mutually exhaustive means that there is no data point which is outside these 2 options. Okay? Because the fourth person can either choose to enjoy alone or he can pair up. There is no other option. So these 2 are mutually exhaustive as well. Whenever you see cases being mutually exclusive and exhaustive, you can just add them up to get the final answer. So we add them up, we get number of ways 4 people can enjoy the party is number of ways 3 people can enjoy it, multiply by 1, plus number of ways 2 people can enjoy it, multiply by n minus 1. And this is how we solve the answer. Okay, we can generalize it and say number of ways n people can join a party would be equal to number of ways n minus 1 people can join it. So that the nth person is just going and staying alone. So you multiply it by 1. The other option is that the nth person decides to pair up with somebody. If the nth person decides to pair up with somebody, then the number of people in the party that are remaining to be decided is n minus 2, because 2 people have already paired up. N minus 2 figure out the number of ways, multiplied by n minus 1, because the nth person could have chosen to pair up with n minus 1 people. This is the recurrence relationship that I get. I have just proven that yes, this problem has optimal substructure. The moment I prove that this problem has optimal substructure, recursion can solve the problem for me. To move from recursion to dynamic programming, I need to look at the second feature, which is overlapping subproblems. Do I see the problems being overlapping? Do I see the problems overlapping? Yes, they are. Because when I will compute the answer for Wn minus 1, I will end up computing the answer of Wn minus 2 and Wn minus 3. And here also, if I'm computing Wn minus 2, and here also I'm computing Wn minus 2, why would I want to recompute it? I would just store all these n answers in an array or somehow maintain these states and utilize them to solve my answer. So yes, optimal substructure is also there and overlapping subproblems are also there. So that's why you will now move from recursion to a DP solution and you can solve this problem using DP. Let me do a dry run for this problem. Okay. So let me do a dry run. Before that, let me actually tell you what is memoization versus tabulation. Okay. So I would rephrase this question and ask that this question actually is about what is top-down versus bottom-up. I explained this briefly, but let me just explain that to you once again. Top-down simply means, so do you guys appreciate till this point in time that dynamic programming solutions essentially can be represented as a recursive solution plus doing some memoization. What do you mean by that? DP, I told you, has 2 features. Every problem that can be modeled into DP has 2 features. One is that you have optimal substructure. The other is that you have overlapping subproblems. Okay. The moment you say you have optimal substructure, you should be pretty sure that you can solve that problem recursively. Okay, because there is optimal substructure, you can divide a bigger problem to a smaller problem and solve the problem recursively. The moment you see that there are overlapping subproblems, you can go a step ahead of recursion and say that just because the states are being repeated, I would just do memoization, which is nothing but having the values of the answers of those states saved and not computing them again. So that will DP in this way, nothing but a recursive solution, but throwing in memoization. This is something that we call as a top-down approach, that you just write the recursive code and just throw in memoization, because in the recursive tree, you will be seeing a lot of duplicate states. So this is one way of solving a DP problem. The other way is solving a bottom-up approach. Bottom-up approach basically is that you start with your base cases or base case, and utilizing whatever information you have, you compute the answer that you have for the next big state that you can compute. Okay, so using the base case, you compute a bigger answer. Now using all this data, you compute an even bigger answer. Using all this data, you compute even a bigger answer, and so on and so forth. So you are basically not solving anything recursively, but you are writing an iterative solution, that you are iterating from a base case answer and building solutions iteratively as you keep on going with bigger ends or with bigger problems. Okay, this, some people call this as tabulation. What does that mean by calling it tabulation? It means that you just have a table ready with you, which can be a 1D, 2D, 3D table. In every problem that we discussed today, it would be a 1D table, because we discussed 1D DP problems today. What does that mean? 1D DP means that the state, DP state, can be represented with one variable. That is what we mean by 1D DP. Okay, so tabulation means that you just create a table in which you say that these are the states that I want to compute. You fill the values for the base cases, utilizing them. So let's say you fill the values for the base cases, and utilizing them, you compute a bigger answer. Then you compute, utilizing all these things, a bigger answer, utilizing all these things, a bigger answer, and so on and so forth. So you just keep on filling your table, or in other words, you just do it the bottom-up approach. This is the second way of solving DP problems. So I hope this question should be clear now. Let's now come to dry running this problem. Okay, so let's now come to dry running this problem, and let me actually dry run this problem using the bottom-up approach, because top-down we have discussed very extensively. Let's actually discuss this using the bottom-up approach and try to dry run it. Okay, dry run the problem of party using the bottom-up approach. So everybody in the class knew that for n equal to 1, the number of ways for one person to enjoy the party is equal to 1, right? Now, number of ways for two people to enjoy the party is 2. We discussed that one, either both of them can enjoy the party together, or both of them can enjoy the party alone. We also discussed that we know the answer for what if there are 3 people in the party. How many ways can 3 people in the party enjoy? We knew that answer as well. We said that the answer was 4. So now let's say we only know the answer to way equal to 1 and way equal to 2. Now let's say I want to compute the answer for way equal to 3. I've already proven that this answer can be computed. It has optimal substructure, has overlapping subproblems. So DP would be a way to go about it. So what would I do? Now let's say I know that one person is there in the party, and if only one person is there, there is one way. There are 2 people, there are 2 ways. Now the third person comes. The element of choice that this person has, so let me call it E or C. The element of choice that this person has is either to enjoy the party alone or to pair up. If he decides to enjoy the party alone, people, you tell me that the number of ways for 2 people to enjoy the party would still remain, because those 2 are still in the party. And this third person is just going on and tagging all alone. So you will say that the ways for 3 would, in this case, would be ways for 2 people to enjoy in whatever way they can, multiply by 1, because the third person is just tagging along. The other option that he had was to pair up. So what options does he has to pair up? He can either pair up with the person 1, or he can pair up with the person 2. Does it make sense, people? If he pairs up with person 1, how many people are remaining in the party to enjoy? I am the third person. I am paired up with the first person. So he's also busy. I am also busy. Only the second person is remaining. So that would mean that I would reduce my problem to finding number of ways one person can enjoy the party. Similarly, if I chose to enjoy the party, pair up with the second person, then I am busy, the second person is busy, only the first person is available. That would also mean that there is only one person in the party remaining, and there is only one way for him to enjoy. Ways one for him to enjoy. So you see that for pair up, you have ways 1 plus ways 1. How many times are you adding ways 1? That is the number of people who are remaining in the party. So in other words, you can just call this as number of ways one person can enjoy the party multiplied by 2. Right? So what do you do? For 3, you get the answer by number of ways 2 people can enjoy the party, which is 2 multiplied by 1, plus number of way 1 people can enjoy the party, which is 1 multiplied by 2, which makes it 2 plus 2, which is 4. So number of ways 3 people can enjoy the party is 4. So everybody please appreciate how we are tabulating. We started with the base cases, W1, W2. We now came to W3 using those 2 answers. Let me now compute the answer for ways 4 as well. Okay. How can I compute the answer for ways 4? Again, look at the element of choice. The element of choice that I have is the 4th person can either enjoy alone or the 4th person can pair up. If the 4th person enjoys alone, he will say that there are 3 people remaining in the party. Whatever ways they can enjoy, let them enjoy. I will just tag along and you will just multiply it by 1. The other option that he has was to pair up. He could have paired up either with the first person or with the second person or with the third person. If he pairs up with the first person is gone, 4th person is gone, 2 people are remaining in the party. They will enjoy the party in ways 2 ways. What if he pairs up with second person? Again, ways 2 ways. Because 2 persons in the party are remaining. We can let them enjoy in ways 2 ways. 3, if you partners up with 3, again, ways 2. So what is essentially happening? You are multiplying ways 2 with nothing but 3, because there are 3 people in the party apart from the 4th person. So you say for ways 4, my value would be ways 3 multiplied by 1 plus ways 2 multiplied by 3. Ways 3, I already know the answer was 4, so I will say 4 into 1. Plus ways 2, I already know the answer was 2, so 2 into 3. I say 4 into 1 is 4, 2 into 3 is 6. I say there are 10 ways for 4 people to enjoy the party. Okay, cool. So let's now actually come to the last question that I saw. So the second last problem that we had was that there are n houses. You want to figure out the best way you want to maximize your robbery so that every house has some gold coins. You want to maximize your robbery such that the moment you rob a house I, you can no longer rob the house I minus 1 and you can no longer rob the house I plus 1. So this was the constraint that we had. I said, again, let's look at the problem as a combination of, as some states. Okay. So let me define one state for you. Let me define a state which tells you that the maximum coins that you can get. So let me just move it and define a state for you. That is the maximum coins that you can get from looting the first to the nth house. So maximum coins that you can get from looting the first to the nth house. Let's say I want to compute this answer. Does that make sense? I want to compute that what is the map. Let's say I have a problem of finding the maximum coins that I can loot from the first till the nth house. Now I say that to look at this problem, you again have an element of choice. When you are at the first house, you can either to choose to loot the first house, that you can loot the first house, or you can not loot the first house. People, if you loot the first house, do you think you will get some gold coins? If you loot the first house, do you think you will get some gold coins? Yes, you will get some gold coins. How many coins will you get? You will get the coins that were there in the first house. Now, the moment you have chosen to loot the first house, your problem reduces. Your problem says, earlier the problem was to get the maximum loot from first to nth house. I have chosen to loot the first house. My problem reduces to a smaller problem. What does it reduce to? I have chosen to loot the first house. There is nothing left to loot in the first house. Just because I have looted the first house, I can no longer loot the second house. So my problem reduces to finding the best answer from looting coins 3 to n. Okay. So let me not call it coins I. Let me just call it a reward I. That if you choose to loot the ith house, this is the reward that you get. So reward 1. Reward 1 plus the subproblem of coins 3 to n. Similarly, if you choose not to loot the first house, then what is the subproblem reduced to? If you are not looting the first house, are you getting any loot amount? No, you are not getting any loot amount. So you will just add a 0 to a subproblem. Your problem now reduces to finding the best loot that you can make from the second to the nth house, because the first house you have not looted, and if you did not loot the first house, you can actually still afford to lose the second house. So just by looking at this, you will realize that yes, there is optimal substructure, and I can represent my problem in a recurrence format by this. So if I want to figure out 1 to n, I can say it would be reward 1 plus coins 3 to n, or the best second option that I had was to not loot it and reduce into a problem of coins 2 to n. These are the two options that I had. I want to choose the option which will give me the maximum. So what will I do? I will explore both these options. Whatever comes out to be the maximum of the two, I will return that as the answer. Okay. So now this is the recurrence. This is from 1 to n. Let me just generalize it. So it becomes coins I to j. If I have the house from I to j, I want to loot them. Or let me actually call it I to n, because n is going to remain there forever, the way we have described this problem. Coins 1 to n would equal to, one option is that you actually loot the ith house, you get the ith reward, plus you reduce the problem into I plus 2 से लेकर n तक, or you choose not to loot the house plus coins I plus 1 से लेकर n तक. You take the maximum of the two. Now this is the recurrence relationship. The moment you arrive at this recurrence relationship, you know that this problem can be solved using recursion. Okay, you know that this problem can be solved using recursion. Now, before that, let's make sure that we also know the base cases. So what are the base cases? You see that this definition fails to hold true when you are at the last house. Because if you are at the last house, do you think that you can actually go to the n plus 2th house? No, because that house does not exist. So if you are at the last house, that should be a base case, because this recurrence relationship will not be able to define it. So what should be the base case? One base case would be coins n to n. What does that mean? That is a subproblem which says that there is only one house to be looted, nothing else is there. What would be the best answer that you can get? My submission would be, if there is only one house, what should you do? You should drop that house, right? Because there is nothing better that you can do. So coins n to n would equal to be the reward of looting the nth house. So this is one base case that you can see. Now you guys tell me, if I am at the n minus 1th house, will this recursion help me then also? It will not, because if I am at the n minus 1th house, I will be forced to go to n minus 1 plus 2, which will be n plus 1th house. That house does not exist. So even for n minus 1, I should have a base case. So the second base case that I would have would be that what is the best answer for for looting the houses from n minus 1 to nth house. Now my summation is that if you have only two houses, n minus 1 and nth, can you loot both of them? No, you cannot loot both of them. Should you loot none of them? No, you should not loot none of them. At least you should not loot one of them. In fact, you should exactly loot one of them. If you should exactly loot one of them, which one of them will you loot? My summation is that simply loot the house which has the maximum reward out of them. So if the n minus 1th house has the maximum reward, loot that house. If the nth house has the maximum reward, loot that house. So yeah, now you know that you have a second base case as well. Do you require a third base case? So does this problem hold true for n minus 2? Yes, this recursion hold true from n minus 2th house, because from n minus 2 you will be forced to go to n minus 2 plus 2, which is n, and that is still a definition which is defined in this recursion. So that's not an issue. So these two base cases should be sufficient. So till this point in time, we have discussed that yes, recursion can solve our problem. Now you see that a lot of states would be repeated here. If you just solve this using recursion, a lot of states would be repeated. I am leaving that as an exercise for you guys to figure out that how these states will be repeated. I will give you a hint. How to figure that out? Just build a recursive tree and see that a lot of states are being computed again and again. So what do? You memorize those states. Okay, you memorize those states. That's it. The moment you memorize those states, you just solve this recursive question, add that memorization, you get the answer. You get that answer top down. If you want to solve that answer bottom up, what do you do instead? You start with the base cases. So you start with, what if I only had the last house? The answer will be reward n. What if I had the second last house and the last house? The answer will be maximum of two of them. Now if I have the answer to these two cases, can I actually figure out the answer from n minus 2 to n? So what I'm saying is, let's say I know the answer if I only had this house to loot, then what would be the best answer? So let me just actually take an example, real life example. So let me take an example and see what would be the answer there. 2, 7, 9, 3, and 1. So let's say I know the answer. This is my base case, right? The last one is my base case. The answer would be that you can get only 1 coin, right? So the answer to 5 would be 1. The second last is also a base case. The answer to 4, as we discussed, would be maximum, that you can either choose to loot this one or this one, maximum of 3, 1, which happens to be 3. Now you come to this point. If you are actually doing it bottom up, so you have the base cases. Using the base case, you solve a bigger problem that you can just solve using the base cases. So if I have these 3 houses, what is the best thing that I can do? I have 2 options. Either I can choose to loot this or not to loot this. If I choose to loot this, the second option is choose not to loot this. If I choose to loot this, I will get 9 coins because I'm looting it. And just because I'm looting it, I cannot loot the 4th house. So I will be forced to only consider the answer for the 5th one, which I already know this one. So this will be 10. One option gives me answer 10. Second option is I do not loot this house. So I will get 0 coins from this one. But I can still manage to loot the 4th one, which gives me 3 coins. So the answer would be 3. So I take the maximum of 10 and 3. So the maximum is 10. So I know that for this, for answer 3, the maximum answer that I can get is 10. Now using these 3, I can compute for this. Either I can loot it, not loot it. If I loot it, it would be 7 plus answer of 4. If I not loot it, it would be 0 plus answer of 3. Answer of 4 is nothing but 3. 7 plus 3 is nothing but 10. Or you can say 0 plus answer 3, which is nothing but 0 plus 10, which is 10. You take the maximum of 2, which is 10. So you say even for this, answer of 2 is also 10. Now you are left with this one. You again have 2 choices, either to loot it, not loot it. If you loot it, you make it 2 plus. If you loot it, you get 2 coins just because you're looting it. It becomes 2 plus answer 3. Or it becomes 0 plus answer 2. 2 plus answer 3 is 10. Answer 3 is 10, right? Sorry, answer is 10. 2 plus answer 3 is 12. So one option is 12. Or you say 0 plus answer 2, which is 10. The maximum of 10 and 12 is 12. So you say that if for the first house the answer is 12, so now you know the answer that if you want to loot from the first till the nth house, the best thing that you can do is get 12 coins. Okay. So today, what did we discuss? We discussed what is dynamic programming. We now understand that any problem which shows optimal substructure and overlapping subproblems is a problem which can be modeled into a DP solution. We know that the moment a problem shows optimal substructure, it can automatically be solved using recursion because you can divide a bigger problem into smaller problems. Now, the moment apart from showing optimal substructure, it also shows overlapping subproblems. You can essentially store the subproblems answers and utilize them the next time you see them. So now you actually move from recursion and go to a dynamic programming solution. Okay, so DP in one way is nothing but recursion plus dynamic programming, recursion plus memoization, because you see some problems being repeated. Okay, this is one way to look at it. The other, this is the top-down approach. Bottom-up approach would be that if you have proven that you have optimal substructure and overlapping subproblems, start with the base cases, utilize those base cases, and get the answer to the next case that you can get, and then utilizing all this information, get the answer to the next thing that you can get, and so on and so forth. You keep on building your answers, you will get the entire answer. Okay, this is the bottom-up approach that we have. Apart from that, let me explain you some more things. Then we also discussed that how to figure out whether a problem can be solved greedily or not. The problem can be solved greedily If by just looking at something without looking at what holds for you in the future, if you can make a greedy choice, which will always give you the best possible answer. If you can make such a choice, a greedy solution will work. Okay, if you cannot make such a choice, you are bound to explore all possibilities. Then you should think the DP way. How to think the DP way? Look at the element of choice. Look at any element. Look at what element of choice do you have. Either you can include it, not include it, do something with it, not do something with it, and so on and so forth. The moment you look at the element of choice, you can, looking at the element of choice, construct a recursive definition of the problem. You can construct a recursive solution. You can just create a recurrence relationship for that problem. The moment you do that, then you need to figure out, do you see overlapping subproblems in that recurrence? If you see overlapping subproblems, just memorize it, you get a DP solution. So this is just in brief what we discussed today. We discussed several questions today. This was the basic building block class of DP. Stay tuned to Scalar Academy and keep a tab on all the videos that we keep on sharing with you guys. Hello everyone. We are going to take our discussion from there and discuss some more interesting problems and try to build an intuition that how you would be able to solve any problem that you see for dynamic programming, and how would you able to solve any such problem. What is the way to approach any DP problem? Okay, cool. So I would just reiterate a couple of things that I said in the last class. I said that problems which can be solved using dynamic programming show two primary features, right? One such feature was that the problem is going to show optimal substructure, and the second property that the problem is going to show is going to be of overlapping subproblems. Just taking a minute to redefine these things. So optimal substructure basically mean that you are trying to solve an optimization problem. You want to find an optimal solution to a bigger problem. You can figure out the optimal solution to that bigger problem using the optimal solutions to one or more smaller such problems. Okay, so you can figure out an optimal solution to a bigger problem using the optimal solutions that you have for one or more smaller such problems. This is what is called as the property of optimal substructure. The second property is overlapping subproblems. Overlapping subproblems means that yes, you have actually, so this basically in a way means that you can define a recurrence relationship to solve your optimization problem. Overlapping subproblem basically mean that, okay, you have defined a recurrence, you can very well solve your answer, get an optimal answer using a recurrence relationship, but you can also see that so many of those states are going to be repeated, right? You are going to see so many states which are being repeated again and again, and you would want to utilize that information, store it somewhere so that you avoid recomputing the same states again and again. Okay, so this basically takes you from the recurrence, brings you to DP, because you are avoiding recomputing same states. Cool. If you keep this in mind, theoretically, you know what DP problems are. Okay, now let's try to actually build upon that and solve several questions and see how very intuitively you can answer any question, use any question which can be modeled into DP. You would be able to model it if you just go through these videos. Okay, cool. So let's look at the first question of the day. The first question of the day is as follows. You are, let's say, given a n. Okay, you want to figure out the number of bit strings of size n following a condition. Okay, so let's just take it one by one. You are given a number n. You want to figure out the number of bit strings of size n following a condition. Let's forget about the condition for now. Let's simply look at n and number of bit strings. So what is a bit string? A bit string of size n is a string of size n where every element is either going to be 0 or 1. Okay, so a bit string is simply a string where every element can either be 0 or 1. Okay, cool. So let's try to solve a very, very trivial question first of all. If you're given a n, can you figure out the number of bit strings of size n? Is that very, very easy to solve? Yes, that is very, very easy to solve, because let's say if you have n is equal to 3, what does that mean? It means that you have 3 places to fill. Every place can either take a 0 or a 1. So every place basically has 2 options. And irrespective of whatever option I take here, I still have two options for the second element. I still have two options for the third element. So basically, the number of options that I have is 2 into 2 into 2, and this will repeat n times. So basically, the number of bit strings of size n would be 2 power n. I hope there is no doubt till here. The number of bit strings of size n would be 2 power n. Okay, cool. Now, once this is done, let's now look at the specific question that we had. The specific question that we had was that we want to figure out the number of bit strings of size n such that no two consecutive bits are ones. What does that mean? That means that there are no two consecutive ones in the bit string that you have. Okay, cool. So yeah, so we were now discussing that the question is you want to figure out the number of bit strings of size n which do not have any consecutive ones. Okay, cool. So let's try to figure out the number of such bit strings. So let's look at n is equal to 2. So basically you have two options to fill, and you cannot actually have consecutive ones. Okay, so now 0 0 is a valid bit string which follows the definition that we have. 0 1 is 0 1 a valid bit string? Yes, 0 1 is also a valid bit string because there are no two consecutive bits with ones. Is 1 0 a valid bit string? Yes, 1 0 is also a valid bit string. Is 1 1 a valid bit string given the condition that we have? No, it's not valid because I see two consecutive ones. So the answer for n equal to 2 is going to be 3. Okay, now let's actually look for n equal to 3. When n equal to 3 you have three options to fill. 0 0 0 is perfectly valid. 0 0 1 perfectly valid. 0 1 0 perfectly valid. Is 0 1 1 valid? No, it's not because I see two consecutive ones being repeated. Then 1 0 0, is that valid? Yes, that's valid. 1 0 1 totally valid. 1 1 0 not valid because I again see two consecutive ones. And then 1 1 1 of course not valid because I see two consecutive ones. So the answer for n equal to 3 would be 1 2 3 4 5. So the answer to this would be 5. So we now know that for n equal to 2 the answer is 3, then n equal to 3 the answer is 5. Cool. Once we know that, now let's actually try to figure out a DP solution of going about it. Okay, before that, do you see optimal substructure here? What does that mean? If by chance you have the answer to a smaller n, let's say you know the number of ways you can build n equal to 4, can I somehow use that information to figure out the answer for n equal to 5? Maybe yes. Does that make some sense? So you can use, it seems from this question that you can use the answer to a smaller problem and try to figure out the answer to a bigger problem using the answers to a smaller problem. Okay, cool. Okay, it does seem that it does have some optimal substructure. Now let's look at some very, very interesting points that I feel that always help me while coming up with a DP solution. Okay, so first of all, you guys would realize that in DP you talk about states, right? You actually have a state for which you have an answer, and then you use that state to figure out an answer to a bigger problem. Does that make sense? Right. So it's important to look at states. So the very first thing that I generally ask myself is that what will a state represent in this DP solution? Okay, what will a state represent here? What does that mean? We will see in this question. What will a state represent here? The second question that I try to ask myself is what parameters are going to be there in a state? Okay, so to define that state, what params do I require? Okay, the third question that I try to ask myself is that what is the element of choice here? What is the element of choice in this question? Okay, what do you mean by element of choice? It simply means that what is the choice that you have to take so as to figure out the entire answer. Okay, so we'll see it one by one. First of all, let's come back to this question. You want to find the number of bit strings of size n with no two consecutive ones. Cool. Now, what will a state represent here? Okay, so let's say I come up with a state which is dp of, let's say, I, which actually represent that if I had a n size bit string, let's say dp of I represent the number of ways I can have a bit string conforming to this definition from from, let's say, the 0th. Okay, so let's say there are two ways of going about it. You can either build it from left to right, or you can build it from right to left. Let's try to see that we would want to keep on building from right to left, let's assume. Okay, so what would I say? I would say the number dpi is basically the number of ways you can have a bit string conforming to this definition, which starts from the ith index and end at the n-1th index. Does it make sense? So you have indices from 0 to n-1. dp of I, let's say, represents number of ways you can form a bit string which conforms to this definition, which starts from I and end at n-1. Does that make sense? Does this state make sense, folks? dp of I means the number of ways you can have a bit string from starting from I to n-1, given it satisfies the given constraints that you had. Cool. Now, if this is what my dp state is, can you guys actually figure out what will be the global answer? What will be the final answer that you're talking about? So dp of I basically means number of bit strings conforming to the definition above, starting from I to n-1, right? If this is what my definition is, then the entire answer, which needs to start from 0, end at n-1, you would understand the final answer is going to be dp of 0. I hope it makes sense to everybody, because the final answer, we would want it to start from the 0th index. So 0 to n-1 ke liye, dp of 0 would give me the final answer if this is how I'm defining my states. Cool. So this, I now know that how a state is represented here. Now, to define that state, what params I require, that I also figured out that we require a single parameter, which is I, which actually here means the starting point. Cool. Now let's discuss what is the element of choice. Okay, let's now discuss what is the element of choice that I have. So you guys tell me, what is the element of choice that I have at the ith index? Would you agree with me that I have two elements of choice? I can either fill a 0 here, or I can fill a 1 here. I hope it makes sense to everybody. I have two elements of choice here. Either I can fill a 0 or I can fill a 1. Cool. If I fill a 0, now I need to figure out how does my question change thereafter? Okay, if I fill a 0 here, how does my question change thereafter? So let's assume I'm filling a 0 here. Does that impose any condition on the remaining answer? Does that impose any condition on this bit or this bit or this bit? It does not, right? Because my question was that I cannot have two consecutive ones. So the moment I fill a 0 here, I am not filling any, I'm not imposing any condition on the following bits. Okay, so it means that if I'm filling a 0 at this position, the remaining things can still have all the possibilities that they had before. So I can say that I am reducing my answer to dp of I plus 1. Does that make sense? I am saying that if I just put a 0 here, the problem that I have is to find a number of ways would still be dp of I minus 1 only, because whatever is there pending thereafter, you have not imposed any new condition there. Okay, so it's dp of I plus 1. The second option that you had, what if I filled a 1 here? Okay, what if I filled a 1 here? If I filled a 1 here, do you see I am imposing some conditions thereafter? Yes, I am, right? If I fill a 1 here, what am I imposing something on the I plus 1th index? I am, right? If I fill a 1 here, the I plus 1th index must be a 0, because it cannot be a 1. The moment the I plus 1 index also becomes a 1 when ith is 1, it simply means that you have not conformed to your definition. Okay, so this must be 0. Now I am imposing a condition here at the I plus 1th index. Do you see myself imposing any condition on the I plus 2th index, folks? I'm not, right? Because the moment I fill a 1 at the ith, 0 at the I plus 1th, the I plus 2th would simply can take again a 0 or a 1. I'm not imposing any condition on I plus 2. I hope it makes sense, right? So if I'm filling it at I 1, then at I plus 1, I must fill a 0. At I plus 2, I can fill anything. So my problem actually reduces to saying that I am filling a 1 at the ith index, which has one way of solving it, multiplied by I am filling 0 at the I plus 1th index, which is again one way of solving it, multiplied by dp of I plus 2, because I plus 2 can still take all the possibilities, and that is a subproblem that I have. Does it make sense to everybody? So we discussed that yes, here we have two options here. One option is that I can either have a 0 at the ith index, or I can have a 1 at the ith index. If I have a 0 at the ith index, it simply means that I am having a 0 here, 1 multiplied by whatever is remaining can still take every possibility, so dp of I plus 1. Or the other option that I have is fill a 1 at the ith index. The moment you fill the 1 at the ith index, the I plus 1th index must have a 0. So 1 multiplied because you want to have 1 at the ith index, 0 because you want to have 0 at the I plus 1th index, multiplied by dp of I plus 2, which simply leaves you with the remaining problem. And these are the two options that you had at the ith part, either to fill a 0 or to fill a 1. Now, one very interesting thing that you guys should know, that these two options that I had, 0 and 1, these two options are nothing but mutually exclusive plus mutually exhaustive. What does that mean? That means that mutually exclusive means that if you are filling a 0 at the ith index versus if you're filling a 1 at the ith index, no matter what you do thereafter, these two bit strings are going to be different. Does that make sense? If I'm filling a 0 at the ith index or I'm filling a 1 at the ith index, no matter what happens thereafter, these two bit strings are definitely going to be 0. So that's why mutually exclusive. Then the other thing is mutually exhaustive. Mutually exhaustive means that there is no other option other than filling a 0 or 1. If you just take into account filling a 0 and take into account filling a 1, there is no possibility which is left outside the scope of filling 0 or 1. Okay, the moment you see that your states, that your possibilities are mutually exclusive and exhaustive, you can simply consider that considering these two things is going to not overcount and neither undercount, right? Whenever you say it's mutually exclusive, it means that you are not overcounting. So it means you are not overcounting. Whenever you see it's mutually exhaustive, then it means you are not undercounting. I hope this thing makes sense to you guys. This is very, very important. Okay. Okay, cool. Now, this is what we have. Just because these are mutually exclusive and exhaustive, you can simply now add these two things and you will get the entire answer. So your entire answer looks something like this, that dp of I can be reduced into 1 into dp of I plus 1, which is you were filling a 0 at this point, or you can fill a 1 at this point, which will make it 1 into dp of I plus 2. So this is the recurrence that I have seen, and this actually solves the entire thing for me. Okay, does it make sense to everybody? So this actually solves the question for me. I have got the recurrence relationship, and look at the 3 points that I mentioned. I utilize these 3 points to understand everything about the question, and I've figured out a solution to it. Now, the only thing that is remaining is that once you have a recurrence relationship, you need to figure out the base cases, because base cases are those cases which are trivially easy to answer, and you would not want your because your recurrence would not be able to define those cases, and those are trivially easy to answer. So you would want to define them yourself. So looking at this recurrence, can you figure out what cases is my recurrence not able to define? You would agree with me that one such case is dp of n minus 1, right? Because this recurrence to work, it requires I plus 1th and the I plus 2th index. And for n minus 1, n does not exist, which is I plus 1, and n plus 1 also does not exist, right? It's 0 to n minus 1 indexing. So dp of n minus 1 will not be able to explain using this recurrence. So that's a base case that we want to define, which means that you have only a single element, because n minus 1 would be a single element. Number of ways that you can fill a single element given this definition, we already solved that for n equal to, or we did not solve it, but for n equal to 1, you would realize that you have basically 2 ways. You can either fill a 0 or you can fill a 1 here, right? So you will say the base case dp of n minus 1 is equal to 2. Then let's say, is there any other state which will not be able to be explained by this recurrence? Yes, dp of n minus 2 will also not be able to be explained, because it requires I plus 1 and I plus 2. So if that is also not equal to, we can explain. So you can say n minus 2, n minus 1. It basically boils down to having 2 elements. You can either fill a 0, 1 in both of them. So we figured that out, that 0, 0 is possible, 0, 1 is possible, 1, 0 is possible, 1, 1 is not possible. So for dp of n minus 2, the answer would be 3. So these are the 2 base cases that I have. Now let's actually look, can I actually figure out n minus 3 using this recurrence? Yes, I can very well do it. So that is not a base case. Does that make sense to everybody? Now I have a recurrence relationship. I can very easily write the code for it. So let me just write the code also here. This is a recurrence solution. Cool. So we would want to say define a recurrence function int, let's call it solve. What will it take as input? It will take as input a integer for okay. So it will take as input the I for which you are solving it right now. So int I, comma, with that it will also include the DP state vectors that you have. Okay. So there are two ways here, right? Understand it. In the recurrence, you are only looking at the I plus 1th and the I plus 2th solution only. Does it make sense? You are not looking at anything else. You're only looking at by the I plus 1th and the I plus 2th solution only. But for now, let's assume we are having an entire array which stores every DP state from DP0 to DPn minus 1. Does it make sense? But you know that you can actually improve it and only have the I plus 1th and the I plus 2th solution stored. That is something that you can do using the bottom up solution. But I am doing the top down solution because I see several of you are asking for the top down solution. Cool. So int I, that is I am taking a decision for the ith index, and a vector, let's say, of integers, and let's call it DP. So basically you have a DP ka vector in which you are going to store everything that you pre-computed already. Okay. Before coming to this function, you would have to initialize this entire vector with, let's say, minus ones. Okay. So let's say you initialize this entire vector with minus ones because it means that this state has not been computed yet. And after that, you initialize the base cases. So you say DP of n minus 1, you can say it's going to be 2, and DP of n minus 2 is going to be 3. So you define these two things. Okay, cool. Now, in this solution, you can simply say, first of all, let's do a sanity check. That what happens if the I that you have received, let's say you also had a n, that for which thing you are actually trying to solve it, what is the maximum size. So first of all, you check if the I is greater than equal to n. That is just a sanity check because this is never possible. So you can simply say return -1, that you have just given me a wrong input. Okay, cool. After that, I've already mentioned the base cases here, so I need not mention it there. Otherwise, I would have mentioned the base cases here. Whenever you are writing a recurrence relationship, you must first of all take care of the base cases. I have taken care of the base cases outside this function already, so I need not write it here. Cool. After that, what will I do? I will now just look at whether the particular DP state has been already computed or not. Okay, so I will say if DP of I is not equal to -1, what does it mean? It means that I've already computed that DP. If I've already computed that DP, would I want to recompute it? No, I would not want to recompute it. So what would I do? I would simply return DP of I. Else, if I've not recomputed it before, I'm looking at this state for the first time. If I'm looking at this state for the first time, I will then solve it. So what will I do? I will then say, looking at the recurrence that I have, DP of I plus 1 plus DP of I plus 2. So I will say return solve. I will call this solve function for I plus 1 comma n comma DP plus solve I plus 2 comma n comma DP. This is the code which is going to solve everything for us. Okay, and the initial call that I'm going to make to this function is going to be solve 0 comma n comma dp. Cool, because the final answer is given by this particular state. I hope this is clear to everybody. We can move to the next question now. The next question that we have is this. You have a matrix of size n cross m. So you have a matrix of size n cross m, and you now want to figure out, so for every index that you have, you can only go either in two directions. So let's say you are here. There are two options that you have. From any index, you can either go to the index on your right, let's say this index A, or you can go to the index on your down, which is B. So from every index, there are two options that you have. Either you can go to the index on your right, or you can go to the index on your down. There is no other option other than these two options. Okay. Now you want to figure out the number of ways to reach from the start to the end. Okay. This is very simple solution that you just want to figure out the number of ways you can reach from the start to the end. And from every index, there are two possibilities that you have. Either you can move to the right index or you can move to the down index. Does that make sense to everybody? Now, this question is a very simple question to solve. Let's forget about DP and let's just try to figure out how you can potentially solve it. I would suggest that if you just want to figure out the number of ways, let's try to look at it from a PNC perspective, okay? Permutations and combinations perspective. You would realize that if I want to reach from start to end, I essentially have to make m minus 1 moves on the right, and I have to make n minus 1 moves down. Does that make sense? I want to make m minus 1 moves towards the right and I want to make n minus 1 moves downwards. Okay? Now, does it matter in what order do I take these moves? I can potentially take them in any order. Does that make sense? I can potentially say that I will take all the down moves first. So I will go from here to here, from here to here, and then I will take all the right moves. Or I can say that I will take all the right moves first and then take all the down moves. Or I can say that I can just take a random sequence of down or right moves. So I can take a down, a right, a down, a right, a down. So you can essentially take any such ordering and all of them are going to take you from the start to the end. So the problem actually boils down to figuring the number of ways to arrange these m minus 1 and n minus 1 steps. Does it make sense? So people, there are m minus 1 steps to your rights. This is m minus 1 times. And you have n minus 1 steps to your down. This is n minus 1 times. You would essentially need to figure out any such permutation of these m minus 1 and n minus 1 steps would do all these things for us. Okay, so what do? I will simply permute all the possibilities. So I will say m minus 1 plus m minus 1 ka factorial. This will give me the permutations of all the possibilities here. You divide it by m minus 1 factorial and n minus 1 factorial. Why? Because m minus 1 of them are the same and n minus 1 of them are the same. So this solution will give you all the ways from the starting till the end. Okay, but still I would want you guys to solve it using the DP approach. Why is that the case? We would still want to solve it using the DP approach because this solution, which was very simple, which is very simple, is very fine to do, but you can actually figure out some complex problems which you would not be able to solve simply using permutations and combinations. Does that make sense? Cool. So if this is what you already have, this you already know how you can actually figure out a DP solution. Let's try to look at it. Okay, again, remember the 3 steps that I told you before. There are 3 steps for any question in DP would be like this. The first step would be that what will a state represent? Second would be what all parameters do I require to represent a state? And third would be that what is the element of choice that I have? Okay, to answer these 2 first questions, that what does a state represent, you need to actually go back to the optimal substructure definition that we had. You want to represent your state in such a manner such that the solution to a bigger state can actually be utilized, can actually be computed utilizing solutions to smaller states. So you would want to define your states in such a manner that a solution to a bigger state can actually be represented using solutions to smaller states. Okay, so here my submission would be that again there are 2 ways because this is a problem which is symmetric from both ends. I can either build a solution from the top to down or I can build a solution from the last index to the first index, right? Both of them are equally symmetrical to me. I can choose any such option, but I would say, let me define my state in this way. If I am I comma j, I want to reach this end. So let's say dp of I comma j represents the number of ways to start from I comma j and end at end. Do you see it as a very good candidate of representing a state, because keeping in mind the optimal substructure that we had, if I know the solution to figuring out the number of ways that I can have from this cell to this cell, can I hope to utilize this to figure out the number of ways for, let's say, cells on towards the top right, top left? Or I can actually spend some more time in explaining this, because this is very, very interesting, right? So you potentially are building a state keeping in mind the optimal substructure problem. You're building a state which will help you to figure out a recurrence relationship using this optimal substructure property. That you now have dp of I comma j, in my definition, would be number of ways that you can start from I comma j and end at the end. Okay. Now, if this is what I am representing my state as, let's try to look at, so we now know what is the state represent. We have figured that out. Second thing, what are parameters do I require? I figured that out. I comma j are the two parameters that are required to represent a state here. The third problem that we have is, what is the element of choice? Okay, so you folks tell me, if I am at this position, what is the element of choice that I have? Right? Or if I have at any position, what is the element of choice that I have? That is defined by the question itself. I have two elements of choice. Either I can move towards the right, or I can move towards the down. Does it make sense to everybody? Does it make sense to everybody? Either I can move towards the right, or I can move towards down. There are two options that I have. Are these two options choice element of choices? Either I can take a step, or I can take a B step. Now you guys tell me, are these element of choice both mutually exclusive and mutually exhaustive? Yes, these are, right? Because if you take a right and if you take a down, no matter what you do thereafter, these are going to be two different approaches. Similarly, if you take a right and take a down, there is nothing remaining outside of this, right? Cool. So these are both mutually exclusive and exhaustive. Now we want to actually figure out how to utilize this element of choice to define the recurrence relationship. Okay, so I would say from dp of I comma j, I had two options, either to do a or a b. If I do a, what does it mean? I am actually going to a smaller problem, which is dp of I comma j plus 1. Does it make sense? If I am going from a to if I'm going from dp of I comma j to a, it simply means that I am going to dp of I comma j plus 1. So I will say dp of I comma j plus 1. If I'm going to the b, right, if I'm going from I comma j to b, it means that I am reducing my problem to figuring out the number of ways of reaching from b to e. Does that make sense, folks? Number of ways of reaching from b to e, and that by my definition is going to be dp of I plus 1 comma j. I hope it makes sense. So what I'm doing, I am making a bigger problem and reducing it to two smaller problems here, right? How am I doing that? I am saying, if I wanted to figure out, let me just take a minute more so that everybody appreciates what DP solutions are. Just give me a minute more, okay? So this actually represented number of ways to reach end from I comma j. I can potentially write this as, this will be equal to number of ways to reach end from A plus the number of ways to reach end from B. There are two ways here. If you can divide your bigger problem into smaller problems, this is how you would want to do it. And the moment you understand it, you understand how a DP solution very beautifully captures this thing and solves it for us, right? So I have just written dp of I comma j would be equal to dp of I comma j plus 1 plus dp of I plus 1 comma j. Okay, cool. Now this is what my recurrence relationship looks like. Let me just write it. dp of I comma j would be equal to dp of I plus 1 comma j plus dp of I comma j plus 1. Now this is my recurrence relationship. Now looking at this recurrence relationship, I would want you guys to answer, and also looking at the definition that a state here means, I would want you guys to answer what state will give me the final answer. I'm pretty sure that you guys would be able to figure out that the final answer would be given by dp of 0 comma 0, right? Because I actually want to reach from the 0 comma 0th index to the end. So this state will give me the final answer. So this will be my final answer. Now what is remaining? The base cases are remaining. So let's try to look at the base cases here. Look at this recurrence again. Figure out which particular states will not be able to define, we will not be able to define using this recurrence relationship. Okay, so try to understand that. This is what my states ka matrix looks like. At every point in time, I am going to the right and going to the down. So tell me for which states it will not be possible to go to the right or go to the down. If I am not wrong, these are the states where I will not be able to go towards the right, and these are the states where I will not be able to go towards the down. Does it make sense? So it means that these states are not, we cannot explain these states using this recurrence relationship. So all these states should be our base cases. And to find the answer to them, it's very trivial. Base cases are very trivial to answer. You guys tell me, what will be the answer for this dp of this state? It will be 1, right? Because I just need to figure out the number of ways of reaching from this cell to this cell only. It will be 1. Tell me for this cell, number of ways to reach from this cell to the end. Again 1. So for all these cells, the number of ways is going to be 1. There is only one option that you can take. Just take down, down, down and reach the end, right? Because there is no right to take. Similarly, for all these cells, again, the options are only 1 because you can only take right, right, right. There is no option to go down. Okay, so these are the base cases that I have, and all of them are initialized by 1. The moment you do it and you write this recurrence relationship, you solve your question. Let's move to the next question that we wanted to discuss now, and which is just a simple modification of the problem that we just saw. Okay, now the problem is that you still have a matrix at hand. Let's build a matrix 72105 57128. Let's say 68239. Let's say 15351, and let's say 29470. So you still have a matrix at hand, but you will see that the matrix now has numbers filled in it. What does these numbers represent? We have this matrix. Now again, we want to reach from the starting cell and we want to reach the ending cell. Okay, the problem is still the same, that you want to reach from the starting cell to the ending cell, but it's not as if you want to figure out the number of ways. The problem now is that you need to figure out the minimum cost path from the start cell to the end cell. What does that mean? It means that whatever path you take and whatever cell you visit, the cost of that path is the summation of all the cells that you visit. Okay, so cost of path you take from start to end is equal to the summation of cost of every cell that you visit. This is the problem that you have, and you want to minimize this cost. You want to print what is the minimum cost that you could have had if you wanted to solve this question, reach from the start to the end. Okay, this is what the question is. Now again, from any cell you can either move to the right cell or the down cell. These are the only 2 options that you have. Do you guys think that just by looking at the things that we solved, that we did for the last problem, can you actually solve this problem as well? Let's try to look at again those 3 points and see how we can answer those 3 points to get a solution to this problem. Okay, the first point was how to best represent a state here. I would say you can still represent the state here using the same approach as we did there. You can say min c, which is minimum cost of I comma j, will tell you the minimum cost of path from I comma j to end. Let's say this is what my state represents. This is the answer to the first question. Okay, secondly, let's look at the answer to the second question. The answer to the second question was, what parameters do you require to represent a state? Again, the parameters here would be I comma j. These are the parameters that are required. The answer, question 3 was, what is the element of choice that I have? The element of choice that I have is again that you can either go to a right or you can go towards a down. Again, are these 2 elements of choice mutually exclusive and exhaustive? Yes, these are again mutually exclusive and exhaustive. Okay, so let's try to define a recurrence here. I would say that if I am at a minimum cost I comma j, if I want to find the answer to this, I would tell you that there were two options, either to move towards the right or to move towards the down. If I move towards the right, the sub problem that I will be having would be minimum cost I comma I plus I comma j plus 1. Okay, and if I move towards my down, the sub problem would be minimum cost I plus 1 comma j. Does it make sense, folks? There are two options. If I actually take the path towards my right, this is what my question is going to look like. If I take the path towards my down, this is what my question is going to look like. But do you think, and if I want to find the minimum cost, which path will I take, folks? Let's say I know that from I comma j to reach the end, there are two options that I have. Either I can go towards my right or I can go towards my down. These are the two options that I have. Both will take me towards the end, but both will have different costs. How will I get those costs? I will get those costs using this dp function. Which path should I take, folks? If I want to minimize my answer, which path should I take? The path that gives me the minimum cost. I should take that path. So I will just do a minimum operation on the answers of these two dp's. I will just take the path which is the minimum out of these two. Okay, and whatever path is the minimum, I will just add the cost of being at the I comma j cell, right? Because I am at the I comma j cell, I will just take the cost of that cell. If I add these two things, I will get the dp solution to minimum I comma j. And this is how I represent it. This is how I represent it. Then I can just say that the final answer to this question would again be minimum cost of 0 comma 0. What is meant by the cost? Okay, Rahul, by cost I simply mean that if you actually go to a cell, whatever is the number written at that cell, that is the cost that you have to incur. Okay, cool. Now Abhishek says, please explain the base cases for me. Okay, Abhishek. So look at the recurrence again and try to look at the states which you will not be able to explain using the recurrence. Okay, try to answer that. So let's say this is what my numbers look like. Let's say this is what my numbers look like. Would you agree that only these are the cells, that is the bottommost cells and the rightmost cells, I cannot explain using this recurrence? Because my recurrence wants me to take me to the right and the down. And I will not be able to take the right for these cells. And I will not be able to take the down for these cells. Right? And now I want to figure out the minimum cost of reaching from any element till the end. This is what my DP states represent. So let me build my DP array here. And let me try to fulfill my DP answers to these base cases. So I will tell you that if you want to reach the end from this cell and this cell's cost is 0, the total cost of that path will be 0. So the DP solution to this cell would be 0. Now you tell me, if I want to reach the end from this cell to this cell, what will be the DP solution? It will be get the cost at this and then take the answer for the remaining. So it will be 1. Here it will be 10. 9 plus 1 is 10. Here it will be 18 because 8 plus 10 is 18. And here it will be 23 because 5 plus 18 is 23. Similarly, for this particular row, the answer at this cell will be 7. This cell will be 14. This cell would be 18. This cell would be 27. And this cell would be 29. Okay. So Abhishek says, Abhishek has a question. Can I solve this problem greedily? The problem that we just said. This problem cannot be explained greedily. The reason being is that greedy solutions basically mean that you can take a decision which path to take without looking at what holds for you in the future. Abhishek or everybody in the class answer this, that if you are at, let's say, at this point, let's say you are at this point at 7, can you take a decision of which path that you can choose? So you can either choose a path that takes you to this 1 cell or the path that takes you to this 8 cell. Can you make a decision that from 7 you should always go to 1 because 1 is a smaller number? You cannot do that, right? Why you cannot do that? You cannot do that because 7 to 1 You are only encountering +1 to go to 1, but you never know. Maybe the path from 1 to the end will be very, very costly. So you cannot take a decision here without looking at what holds for you in the future. So that is why you cannot actually solve it using a greedy solution. You need to actually know what happens for you in the future. So a greedy solution here would not be possible. Okay. But at the same time, once you know whatever happens thereafter in the matrix, and you have stored the answers to them, then you can simply take the choice which will give you the minimum answer till the end, and that's perfectly fine. And that's exactly what we did in this solution. Cool. Let's actually move to the next question that we want to discuss today. So the problem is as follows: that let's assume that you can buy and sell one stock. Okay. Alok, I can explain that to you after the end of the class. So just hang on for a bit. Let me define this problem, try to solve this, and then I can try to answer your question as well. Cool. So the problem here is that you, let's say, are given the prices of a share at every day. Okay. So let's say this is day 1, day 2, day 3, and so forth, so on and so forth. So let's say the price of that share on day 1 is $3. It's $3 on the second day. Let's say let's talk in rupees. It's 5 rupees on the third day. It's 0 on the fourth, 0 on the fifth. Let's say 3 rupees on the sixth, 1 rupee on the fourth, and 4 rupee on the last. Does it make sense? So you basically have the prices of these shares at different days. Now the question is that you can essentially buy this share and sell this share. Let's call that buying and selling a pair a transaction. So you can perform some transactions here. Transactions basically mean a pair or a tuple of buy and sell. So you can buy a share and sell it. And notice that there are no put call options here. You can only sell it when you have bought it before. So you can buy a share on one particular day, sell it on some other particular day. Does it make sense, folks? And you can repeat this transaction, let's say k times. You can repeat this transaction k time. But the constraint is that you cannot say that I will buy it twice before I sell it once. So the moment you buy it, the only option that you have now is to sell it. When you will sell it, only then you can buy it. What does that mean mathematically? It means that at any given point in time, you can only hold 1 unit of stock. Okay, so the condition here is at any given point in time, you can hold at most 1 stock unit. So you cannot just buy twice and then sell it. So you will, the moment you buy it, the first thing that you should do thereafter is to sell it. Only then you can buy it again. Okay, cool. So this is one condition. The second condition that you have is that you will always first buy and then sell. So you will always first buy and then sell. Right. So these are the two conditions. We want to figure out the maximum profit. You want to figure out the maximum profit that you can do after at most k transactions. This is what the question wants you to figure out. Let's now try to look at a very, very simple case. Let's look at a very, very simpler problem. This is a problem actually is that you can actually do k transactions, at most k transactions. The simpler problem would be, what if k is exactly equal to 1? What if you can only do one transaction? Can we try to figure out an answer to that? Can we try to figure out an answer to saying that what would be the best way if I could only have done one transaction? That is one buy and one sell. So let me just write the array once again: 3, 3, 5, 0, 0, 3, 1, 4. Okay, so let's look at this array and say I can only buy it once and I can only sell it once. What would be the maximum profit that I could have got? Okay, now you folks tell me, if you would want to maximize your profit, you would want to buy at the lowest price and sell at the highest price. Does that make sense? You would want to buy at the lowest price and sell at the highest price. So you will want to buy at lowest possible plus sell at highest possible. Now this is what intuition that you guys would be getting, but can you actually just figure out the maximum from the array and from it subtract the minimum of the array? You cannot do that, right? Because the problem is if you just look at the maximum of the array and the minimum of the array, there is one more condition that you must buy it before you can sell it. But if you just look at the maximum and the minimum, the problem would be that you can essentially have a problem where you are buying in the future and selling right now. I hope it makes sense to everybody. Let me take a very simple example where you would realize that, that is not possible. So let's assume the stocks, there are only 2 days. The stock was priced 7 units on the first day and 5 units on the second day. Now you want to figure out the maximum profit that you can have if you can buy it once and sell it once. The answer to this problem would be 0. That you would not want to buy it at all and not want to sell it at all because the price is a decreasing trend and you cannot buy it at 7 and sell it at 5 and make a profit. So you would prefer not to buy it and the answer would be 0. But if you just take the maximum here would be 7 and the minimum here would be 5. If you just subtract the max minus min, it will be 7 minus 5, which will give you 2 units of profit. But that's a wrong answer to take. You're right, you cannot have 2 units of profit because you need to buy it before you can sell it. So the answer to this would be 0 and not 2. So you realize that you cannot simply find the maximum and the minimum from the array and just subtract them to figure out the answer. I hope this is clear to everybody that this solution will not work. Now, the point is that we would want to somehow figure out the solution. This simple greedy approach will not work. What will we do now? My summation is that let's look at the array properly. Okay, my summation is let's look at the array properly and try to figure out some pattern. I would say let's store 2 states here. One state here would be what is the minimum price at which I can buy it, assuming I bought in the first I days. Does it make sense? The first state that I would want to have is minimum I, which will say what is the minimum price at which I could have bought it if I was buying it in the first I days. Does it make sense? Minimum price at which I could have bought it if I bought in the first I days. Does it make sense? So you folks tell me, if I can buy in the first 1 day, what is the minimum price? It would be 3. What is the minimum price if I can buy in the first 2 days? Again 3. What is the minimum price that I can buy in the first 3 days? Again 3, because I could have bought at price 5, but I can already I can buy at price 3. So I would want to buy at 3 and not at 5. Okay. Then till the day 4, what is the minimum price at which you can buy it? It's 0. Till 5, what is the minimum price at which you can buy it? It's 0. Till 6, what is the minimum price? Again 0. 7 minimum price, again 0. 8 minimum price, again 0. The minimum price at which you can buy till the ith position. Okay, so this is how you would figure out what is the minimum price at which you can buy it. Let me now also compute an array for you, which is the maximum price till the ith index if I wanted to sell it. What is the maximum price till the ith index if I wanted to sell it? But this array, this minimum I represented it from 0 to I. The maximum I will want to represent it from I to n minus 1. So I want to figure out that what is the maximum price at which I could have bought it from the end. So you would tell me if I want to fill it from the end, it would be 4 that I can sell it at 4. It would be still 4 that I can sell it at 4. It would be still 4 that I can sell it at 4. 4, 4, and now it becomes 5 because I would prefer to sell it at 5. 5 and 5. So this is what my array looks like if I look at from the end till that point in time. Now, just because I want my buy to be first and sell to be later, I can essentially go to every index now and look at a difference between min I and max I, and I will get the So I will subtract them and get the answer. Why will that work? Because if I look at any I here, it will mean that the minimum price at which you could have bought it from the starting till this point is 0, and the maximum price at which you could have sold it from the end till this point is 4. And these two things together satisfy all the conditions. You are buying first, selling later, and you are buying at the minimum price, selling at the maximum price. So what will you do? You will just traverse over this array and figure out the difference between max I and min I in all these indexes. So what will I do? Let me just rub a few things here so that things are clear to you and you can understand it properly. So let me just rub a few things here, and now let me show to you the difference array. Okay, so let's look at the difference array. The difference between here and here would be 2. That if I want to do it at the first index, it would be 2, second index 2, third index 2, fourth index 4, fifth index 4, sixth index 4, seventh index 4, and eighth index 4. What is the maximum out of all of them? The maximum out of all of them would be 4. So you can potentially say that the maximum profit that you can have, if you can only do this transaction once, it would be 4. The next thing that we wanted to do was look at k is equal to 2. If you can do an operation twice, if you can buy, sell, and again buy and sell, what would be the maximum profit? But let's do it in the next class. And then we would want to optimize it to answer for any generic k, that if I can perform a transaction k times, what would be the best answer that I can get? And we are going to discuss these two things in the next session. Hello everyone. So in today's class, we are going to discuss the class of problems which is called as knapsack problems. Over the last couple of sessions, we have discussed several problems that we can solve using the DP paradigm of solving problems. And today we are going to discuss a specific class of problems that is called as knapsack problems. Okay. So yeah, let's begin today's class. How many of you know what knapsack problems are? So let me first of all start the class by defining what are knapsack problems. And once you know the definition, you would be able to appreciate that yes, this is a specific kind of very niche kind of problem set that we hope to solve using the concept of dynamic programming. Okay, so first of all, knapsack problems are basically optimization problems. What is meant by optimization problems? That is, you're trying to optimize a particular construct within some constraint. Okay, so you're trying to optimize something within some given constraint. There is a constraint that is given to you, and you're trying to optimize some other value based on that constraint. Okay, cool. In these knapsack problems, these problems are in general exponential time. Okay, in general, you will require exponential time to solve these problems. I hope you guys understand what is exponential time, right? So something which is not polynomial, right? So you are having a value raised to some power. Okay, so this is exponential time in terms of the input parameters that you get. But these problems become very, very interesting because there is some other constraint in the problem which is other than the number of the problem size, which makes these problems solvable in polynomial time. Please understand this very, very carefully. In the set of knapsack problems, there is some constraint. We will see what this constraint is in different knapsack problems. There is some constraint which is other than the size of the problem, which makes the problem solvable in polynomial time. Now we are going to see what kind of a constraint we are talking about here. Okay, cool. So keep these things in mind, and do not worry if you did not get it completely at this point in time, because now I'm going to define the problem for you, and then looking at that problem, we are going to fall back to these points that I just wrote, this definition, and see if that problem actually falls into this template or not. Okay, cool. So let me define the problem for you. Here is the problem. Let's assume, unfortunately, you are a robber. Okay, that's a very unfortunate thing to assume, but let's assume you are a robber. Okay, good. Now you go to a supermarket. That supermarket has n products. Okay, there are n items in that supermarket. Okay, cool. Now every item in a supermarket, you would realize, has some value associated to it. Does that make sense? What is the value? Let's assume the MRP. Okay, so every item has some value. Let's assume the first item costs rupees 60. The other item has the value of rupees 100. The third one has, let's say, 120. Fourth one is 50. Let's assume the sixth one is 70. And the last one is, let's say, 20. These are the values of those items. Okay, every item has a value. Not only that, but you would also realize that every item also has some weight. Does that make sense, folks? Every item will also have some weight associated with it. So let's call it the weight. Okay, so let's say the first item was weighted 10 grams, let's assume. The second one was 20, third one was 30, fourth one was, let's say, 5, sixth one was, let's say, 52, seventh one was, let's say, 100. Okay, so there are different weights given to different items. Okay, so every item has a value associated, every item has a weight associated. Cool. Now the problem that you're trying to solve, just because you are a robber, the problem that you're trying to solve is basically that you want to rob some items of this supermarket, but you brought with yourself a bag. And let's assume you are somebody who wants to save the earth and does not believe in, let's say, using plastic bags. You got a good big bag made out of clothes from your house, right? So even though you are a robber, but you are a robber with your own set of beliefs, right? And you do not want to hurt the environment, and you have a bag, cloth bag that you brought with yourself. Okay, cool. Now, if you have a cloth bag that you brought with yourself, let's assume that bag had a weight, a maximum weight that it can take. Okay, so that bag has an inherent maximum weight that it can hold at any given point in time. If you add any more item beyond this maximum weight, your bag is going to break and you are going to lose all the items. Does that make sense? So let's assume this is the problem. You go to a market, there are n items, you want to steal some of the items. Every item has a weight, and there is a bag that you got to steal those items, and that bag has an inherent maximum weight that you can put. Okay, now I would just mathematically define this problem for you. I have given it intuitively. Let me just define the mathematical problem that we are trying to solve here. Okay, the mathematical problem that we are trying to solve here is that, of course, you would want to maximize your loot. Does that make sense? So you would want to maximize your loot. Okay, so let's assume out of these items there are n items. Okay, let's assume I stole some of those items. Okay, so you would want to maximize your loot. What does it mean? You want to maximize the value of your loot, right? Maximize the value of your loot. But there is a constraint. The constraint is that the items that you looted, the sum of their weights should be less than equal to the maximum weight that your bag can have. I hope it makes sense, right? This is the optimization problem. The constraint that you have basically is that is the sum of values, sum of weights of the items you stole should be less than the maximum weight of the bag. I hope this is crystal clear to everybody. Let me just write it once again. So you want to maximize the summation of values of the items you loot. Okay, looted items. So just sum over the values of the looted items. You want to maximize this such that the summation of weights of the looted items is less than equal to WP. I hope now the problem should be clear to everybody. The problem should be clear to everybody in the class. This is the kind of problem that we are trying to solve. Now think about this problem, and the first thing that you should ask yourself is, can I solve this problem greedily? Okay, this is the first thing that you should ask yourself. Can this problem be solved greedily? And I would want you guys to take a minute and see, can you solve this problem greedily? And let me just state one thing here, which may not be very clear otherwise. The one thing that I wanted to state here is that this problem is a real life, let's say, a 0-1 knapsack problem. What does that mean? That means that you can either pick an item completely or you can not pick an item at all. Okay, so you can either pick an item one time or 0 time. That is, either you can say I will pick the complete item one time or I will not pick that item at all. I hope this makes sense. Now, can you guys think about whether a greedy solution will work here? Okay, think about it for a minute. Right. So the answer here, folks, is that the greedy, let's try to evaluate whether a greedy solution will work for us or not. Okay, greedy solution. I would have told this to you guys in the previous classes that I have taken online. You would have seen that greedy solutions work for problems. So what is a greedy solution? Greedy solution says that you are taking a decision which seems best to you at this point in time. What does that mean? That let's assume you have a sequence of numbers, or let's assume you have a big problem that you have. You are just taking a decision at this point without looking at what is there in the problem going forward. Just looking at a particular point, taking a decision that what is the best solution. That solution would look to you the best option at that point in time, but will also guarantee that if you keep on taking that best solution at that point in time, the overall solution that you get is also going to be maximized, also going to be optimized. What does that mean? It simply means that you are building a solution taking local optimizations, which is going to yield to you the global optimization. Okay, cool. So let's try to look at this problem here. The point is that you would want to maximize your global value of the loot that you had. Okay, now my question is there any way in which you can just look at this item and figure out whether this item should be stolen or not? The answer to that would be that no, you cannot do that, because no matter what parameter you apply, let's say you apply a parameter which tells you that amount of value that you can get per unit weight. So what does that mean? So that would mean that the first item would give you a value of 6 per unit weight. If you guys are able to understand that, you get the value 60 with 10 grams of weight. So you get 6 value per unit of weight. Here you get 5 value per unit of weight because you have 100 value with 20 weight, 5 value per weight. Here you have 4 value per weight. Here you have 10 value per weight. Here you have 70 by 52, which is going to be 1.4 something. Okay, and then you can have 20 value with having a weight of 100. Okay, so that basically gives you the value of 0.2. Now, can you take a decision here just by looking at, let's say, these things and saying that just because this value has the greatest value per unit weight, I would want to go with that item? The answer to that is no. You cannot make that decision no matter what kind of a ordering you do. The reason being that there is another bag. The moment you take some item, you remove some possible weight from the bag, right? So you have assumed that you have filled that bag with some weight. Okay, and now going forward, there may be a scenario that you are left with some weight in the bag that you can never fill. On the other hand, if you chose not to include the value which was giving you the best option at that point in time, maybe you can select some combination of items going forward which would maybe completely utilize the weight of the bag and give you the maximum value. Does that make sense to you guys? So these kind of problems, when the landscape is changing with every decision that you take, and with every decision that you take, the further options that you have in that problem change drastically, you would not be able to come up with a greedy solution. I hope it makes sense, right? Cool. So first of all, we just discussed that a greedy solution will not work in this case. Okay. One thing that you guys would, again, I'm repeating it again, based on my last sessions, I would have said that if you see a problem where a greedy solution won't work, then the other option that you have is trying to explore every possibility. What does a greedy solution do? A greedy solution sort of gives you one option or a couple of or a constant number of options at every step, and you say that, okay, I'm only going to take these options and these are the greedy best option, and I will not be worried about what happens if this does not work out. This will always work out. But whenever the greedy solution does not work, the other option that you have, so if this does not work, the other option that you have is to explore all possibilities. To explore all possibilities. And whenever you see a problem which is forcing you to explore all possibilities, what does that mean? So in this problem, just because I cannot take a greedy decision, I will have to explore every possible option, whether to pick 60 or not to pick the first item, whether to pick the second item or not to pick the second item, whether to pick the third item and not to pick the third item. And these are not independent events. These are consecutive events. So if you pick the first item, then do you want to pick the second item or do you not want to pick the second item? Or let's say if you pick the first item, did not pick the second item, do you want to pick the third item or do you not want to pick the third item? So these are consecutive decisions that you are taking, and these kinds of decisions, if you want to explore every such possibility in any decision, then one possible way that you should think about is the class of DP. Okay, is the paradigm of DP, dynamic programming. I'm not saying that every problem that where you want to do explore all possibilities, DP would be working, but this is one possible thing. If you are, let's say, giving an interview and you see a problem which really does not work, you are forced to explore all the possibilities there, then it should come to your mind, can I model this problem as a DP solution? You will not be able to do it for every problem, but for some of them you will be able to do it. Okay, I hope I have made myself clear. Now for DP, I told you that there are two very important parameters that you need to see if a problem has, only then it will be able to broken down into a DP. These are, do you have optimal substructure? That is, can you use the answer to smaller problems to solve the answer to a bigger problem? And the second thing was, do you see overlapping subproblems? So can you actually say that once you end up doing this, so this is something which takes you the recursion way. So you can build a recursive solution there, because if you just can use the answers to smaller problems, you can build a bigger answer. You can use recursion out there, right? This takes you recursion way. But the moment you see that in all the states that you get in the recursion, if there are repeated states that you are getting, it makes the problem dynamic programming problem. Okay, you can afford to not compute those repeated states and solve the problem in a very, very fast manner, right? Now, I am pretty sure that for some of you, this may seem a bit too fast, but I would request you guys to look at the first two videos that we did, and I explain these things in great details. And I'm pretty sure that once you look at those videos, you'll be able to understand what we are talking about here. Okay, cool. So we realized that this problem, first of all, cannot be solved greedily. Now, can I look and see whether a DP solution will work here? Okay, cool. So you guys tell me. Let's look at a smaller problem here. So let's assume if you had the answer to problems from here to here. That is, let's assume there were only 3 items and you know what is the best loot that you can get, or what are the different loots that you can get at different weights. Can you utilize that answer to take a decision for the 4th one, right? So I will just try to explain it using the recursion tree. Just a minute, right? So let me just try to define this problem using a recursion tree. Okay, cool. So what is the point that you have here? So let's assume you have different options to take. At the very first step, let's say you have an option of either picking. So let's say you are at the first element, I is equal to 1, and the weight in the bag is, let's assume, the weight maximum at the moment, because you have not included any item. The weight of this bag is available. So let me call it weight available is the maximum weight of the bag, and you have to take a decision for the first item, and the value that you have aggregated till now is 0. Does that make sense? Before you have done any decision. So let me define the arrays once again, and let me maybe have a smaller array this time around. So this is the value, this is the weight array. These are the 2 arrays that we had, value and the weight array. The values were 60, 100, 120 and 50, and the weights were 10, 20, 30 and 5. Right. So these are the values and the corresponding weights. And let's assume the weight of the maximum weight that you can put in the bag is, let's assume, 50. Right. Now at the first position, let's call it 1, 2, 3, 4. At the first position, before you go to the first position, your value aggregated is 0 because you have not selected anything, and the available weight in the bag is weight maximum, and you have to take a decision for I is equal to 1th item. Now you folks tell me, what all options do you have at the first item? The element of choice that you have is that you have 2 options. Either you can say that I am going to select the first item, or you can say that I am going to not select the first item. Does it make sense to everybody? If you select the first item, can you define these 3 parameters for this new state for me? I am pretty sure that you can. You have taken a decision for the first item. What is the next item that you will have to take a decision for? For sure, you will have to take a decision for I is equal to 2. You have chosen to include the first item. Can you tell me what is the value aggregated till this point in time? The value aggregated till this point in time would be the value of this item. Does that make sense? Because the value previously was 0, I have chosen to include the first item. The value aggregated till this point in time would be the 60. Okay, so this is done. You have to take a decision for I is equal to 2 now, and the weight available that is there in the bag. So you guys tell me. Initially, the weight available was 50, right? Now you have included the first item. The weight of that item was 10. So can you tell me the weight available now? The weight available would be 40. 50 minus 10 is 40. So this is how you take this. This becomes one state. If you chose not to include the first element, can you tell me what to do now? So you have taken a decision for the first element. Now what is the element that you need to take a decision for now? The second element, right? So you have taken a decision for the first element. Now you need to take a decision for the second element. Value aggregated before was 0. You chose not to include the first element. The value aggregated till this point in time will also be 0, right? And then the weight maximum, the weight available before was 50. You did not select the first item. The weight available will still remain 50. I hope it makes sense that this one state now boils down to these two states, right? Now let's look at this state. You have to take a decision for the second item. So again, you have two options. Everybody in the class, understand please. Again, you have two options. The option one that you have is you will want to select the second item. The second option that you will have is that you will not want to select the second item. If you want to select the second item, you would agree with me that now you need to take it for I is equal to 3. The value aggregated till this point in time would be equal to 60 was till this point in time. You are selecting the second element, which will make it 160, right? So you make it 160 is the value that you have chosen to steal till this point in time. And let me also define the weight available. The weight available would be 40 was before this. You just included a value, a weight item which has the weight 20. Now your weight becomes 20. The available weight becomes 20. I hope you guys are able to understand how this recursion tree can be built. Whenever you see a problem which has at least the optimal substructure, that is here what we are doing to compute the answer of this, we are actually using previous states. Does that make sense, folks? Does that make sense? So basically you will understand that whenever you have optimal substructure in your problem, the way to go forward would be to draw a recursive tree. Once you draw a recursive tree, I will tell you how to take the problem forward. I'm sure everybody is with me that you define this problem. So the moment you understand there is optimal substructure, you draw this recursion tree. Once you draw this recursion tree, you see how the states are being modeled, and then you can move ahead and see if DP can be applied there or not. Cool. Now for DP to be applied, I told you one problem is optimal substructure that we already see while building this recursive tree. The second problem that we have is overlapping subproblems. If you have overlapping subproblems, then you can make an argument saying that this problem can be solved much better in a much more optimal manner if I choose to actually utilize the if you see overlapping subproblems, that is there are subproblems that you already computed and you need not compute now. Looking at this problem, do you see that there are so many overlapping subproblems? The answer to that can be figured out by looking at the number of unique states that you have in this recursion tree. So try to find out number of unique states in this recursion tree. Try to find that out, folks. So you tell me, every state here is defined by 3 parameters here: value aggregated, I, and W max. Okay, there are 3 parameters: value aggregated, I, W max. I can say that I can model this as an output thing, that this is something which the state stores. The parameters are only 2. That let's say the ith element for which you are taking a decision for, and the weight available in the back. So let's assume these are the 2 parameters that you have. If you have these 2 parameters, to figure out the number of unique states that you can see in this recursion tree, you will have to figure out the number of values the first parameter can take multiplied by the number of values the second parameter can take. I hope you guys understand that. So what I am doing here, I am saying figure out the number of unique states in the recursion tree. You will have to figure out the different parameters that you have. Once you figure out the different parameters that you have, you can utilize those parameters and figure out how many values the first parameter can take, multiply that with the number of values the second parameter can take, and you can understand how many distinct states will be there in this DP recursion tree, So you guys tell me, the first parameter is I, that is for which element you want to take a decision for. How many different values can I take? I will be equal to 1, 2, 3, 4, so like n tak. So you would be able to understand that I can take n values. Okay. Now can somebody tell me how many values the second parameter can take? What is the second parameter? The second parameter was basically the available weight. It will start from W max, that is At the beginning, you had every single unit of weight available, which is W max. But at every step, you are either going to at least going to reduce the weight by 1 if you are taking some element. Does that make sense? If you're traversing the tree on the left side, you're definitely going to reduce one value, at least 1 unit, because I can assume that every element in this supermarket at least had 1 unit of weight. Okay, it did not have fractional weights, it had natural number weights from 1 से लेकर किसी भी weight तक, right? So you will understand that the number of values the second parameter can take would be equal to the weight max. If you multiply these two values, you get n into W max. So these are the number of states that you can have. Okay, so these are the number of states that you can have, and this is what you see at this point in time. But the problem is that this n can be very large, the number of states can be very large, and you will not be able to, you may be at a position where you are not able to solve the answer. Okay, so let me just wait for a while. If there is any big doubt that you guys have, I would be very happy to answer it. So the argument that I'm trying to build here is that this problem, just because the kind of the problem that we saw here, right? The problem that we saw here, the constraints that we saw here, we got this W max because our bag had a maximum, weight. If the bag did not have a maximum weight, then you guys would agree that I can potentially have n values for the very first state and so many different values possible for let's say infinitely many values possible for the W, right? So you can just keep on saying that I will just keep on selecting. I can just take any decision, and whatever weight it becomes, it will become that weight. But try to look at the problem again. Try to look at the very first 3 points that I wrote at the beginning, right? So let's look at these 3 points that I wrote at the beginning for knapsack problems. It's an optimization problem. In general, it would be exponential time, but there is some constraint which is apart from the size of the problem, which makes the problem solvable in polynomial time. And now let's try to understand that particular sum constraint that I was talking about. Okay, the sum constraint that I was talking about here was that you have this constraint that you can have a bag with a maximum weight, right? The bag has a maximum weight. Does that make sense to everybody? The bag has a maximum weight, and exploiting that particular value tells me that the number of unique states in this recursion is going to be n into W max. Does that make sense to everybody? So what you can see is, just because you had that parameter, that there is a maximum weight for the bag, which makes it n into W max. Cool. Using this, exploiting this constraint, we would actually this will actually help us to model this problem in polynomial time. Does it make sense to everybody? I hope it does. Cool. Right. So we have discussed this. We have discussed this recursion tree. We now understand that these are the states that we had, and this tells me the number of unique states in the DP, and which makes the problem solvable in polynomial time. That's great. Now, once this is done, once we realize that there is a optimal substructure there, once we realize there is overlapping subproblems there, that is, there are some unique number of states that you can get in this DP is going to be very, very less than the overall states that could have been there. Now you know that a DP solution here would work. Good. Can you guys help me write the recurrence relationship for this DP? And if you guys have seen the first 2 classes, you would realize that we have discussed that very, very extensively, how to actually figure out the recurrence relationship for a DP, right? So what do we do? First of all, we figure out the parameters that defines a state. So first of all, we figure out the params that define a state. Then we would have discussed that we want to see what value does a state give. Basically, what is the physical significance of the value? What is the physical significance of the value of the DP state? Once we know that, we can actually figure out which state will give me the final answer. Which state will give me the final answer? And then you can figure out what is the element of choice that you have, right? At every step, what is the element of choice? And using this element of choice, you can actually build the recurrence relationship. So let's try to answer these questions that we see and see how we can solve this question for us. Okay. So first of all, the params that define a state, we already discussed that. Look at these states in the recursion tree. Can we figure out what params are required to represent a state uniquely? We would understand that what I that we are taking a decision for with the value that is available in the box, in the bag till that point in time, these two params define the state for me. Does that make sense? If I have these two params, I can uniquely identify a state for me. Okay, cool. So if I have these two params, I can uniquely identify the state for me. So first of all, the params that I have is the I for which I am taking a decision and the weight available in the bag. Second thing, what is the physical significance of the value that your DP state is giving? So you guys tell me. Let's just look at this recursion tree. The value that I am getting at different states. Can you tell me, looking at this recursion tree, what does this value represent? That value actually represents that if you are taking some decisions from the 0th element till that particular ith element, what is the maximum value that you can get? Okay, why I'm saying the maximum? Because you tell me, if I'm taking a decision for the first element and that actually boils down to taking a decision for the second element, I had two options for the second element. So basically, so you can understand that here I am taking the decision for the first element, I have two options. For the second element, I have again two options, and so on and so forth. At every state, just because you want to maximize your total value, you would want to take a max of the two options that you have. Does that make sense to everybody in the class? To get the final answer, you will have to take the maximum of every option that you have at every state. Does that make sense to you folks? Right. If it does, you will realize that yes, at every state, the value that you are getting would be the maximum value that you can get from taking a decision from the 0th. If I'm building it from left to right, it would be from 0 to ith. If I'm building it from right to left, it would be from ith to nth. And you guys can actually fall back to the previous two videos to appreciate that we can build these kinds of symmetric problems from both ends. Okay, so the physical significance of the value. So let me try to build it from left to right. The physical significance of that value would be what is the maximum value you could have looted in the, let's say in the elements from I, from 0 to I. What is the maximum value you could have looted in the elements from 0 to I, if the weight that you consumed in the bag was equal to W maximum minus W available, if this is how we go about it. Or let's say if the weight available in the bag, weight still available in the bag is W available. I hope it makes sense to you guys, right? If this is what my physical significance of the state is, can you answer the third question for me? Which state will give me the final answer? The state that is going to give me the final answer is going to be, because the ith, the first, okay, so the state that is going to give me the final answer is going to be dp. I just need to fill these two arguments here, right? So what would be the value of these parameters which would give me the final state? So just look at the problem, just look at what is physical significance. The first parameter I means from 0 to I. So at the end, you will have to take from 0 to n. Does that make sense to everybody? So it would be dp of n without a doubt. The second thing is, what is the weight available that you see is possible, right? If you are building up with the weight available, you can see that at most the weight available should be 0. Does that make sense to everybody? This may not give you the final answer because 0 may not be there at all. So you can actually build and say that the dp of n, and whatever I get, I will take the maximum of it. So let me actually now, rather than focusing here, let me actually build a recursion, and then this thing will be very crystal clear, and how I can actually make it boil down to a single state and not even to a combination of states. So let's just wait for a while, and let me just take the element of choice, build the recurrence, and then we will come back to it. Okay, cool. So yeah, dp of element I with some weight available, right? You want to solve this. You tell me, if I means from I se lekar n tak, you have already solved the problem. Okay, if I means you have already solved the problem from I se lekar n tak, now which side will this fall back to? I hope you guys can able to understand that we can build it from left to right or right to left. Both of them are equally valid. Let's try to do it anyway. Okay, so we have dp of I comma weight available. Okay, now we have two choices. Either I can say that I will pick the ith element, or I will not pick the ith element. These two decisions are mutually exclusive and mutually exhaustive. The moment we understand this, we appreciate that yes, just by looking at these two, I would be able to get the complete answer without any doubt. Cool. The first option that you have is pick the ith element. If I pick the ith element, can you figure out that this dp now should actually boil down to I plus 1? Because I have taken a decision for the ith element, do you understand that I will now, let's say, take the decision for the I plus 1th element? Let's say I'm building from left to right. I could have built it from right to left as well, but let me just say I am building it from I plus 1. So, okay, so you can do it both ways, Shobit. So if you are picking the ith element, you can either say that I will boil it down to I plus 1, or you can say I will boil it down to I minus 1. No matter what you do, you will get an answer, but the final answer will be different in different two states. So let me just do it with I plus 1, and I will explain you at the end that how we could have done it with I minus 1 as well. Okay, Shobit? Cool. So let's say pick the ith element. If you're picking the ith element, let's say dp of I plus 1. This is what your problem boils down to. And the weight available would become weight available presently minus the weight of the ith element. Does that make sense to everybody? Right. After that, do you understand that this would be the dp, and the value that you're going to get in that state is going to be plus value of the ith element. Does that make sense? Cool. This is one option. The other option was not picking the ith element. If you are not picking the ith element, it will again have dp of I plus 1, because just because you have taken a decision for I, let's now move it to I plus 1. The weight available would still remain w weight available because you are not taking anything, plus the value that you're adding would be 0. Does that make sense to everybody? These are the two choices that we have. To get the answer, I will just have to take the maximum of these two. So I will just take the maximum of these two. This is what will define the solution to me. Now, if this is how I went about the problem, you guys tell me which element will give me the final answer. You tell me which element will give me the final answer. If my dpi is using dp I plus 1, dp I plus 1 will be using dp I plus 2, dp I plus 2 will be using dp I plus 3. Can you figure out which state will be using everything? Can you figure out which state will be using everything? The answer to that would be that dp of 0 would be using everything. Does that make sense to everybody? dp of 0 would be using everything. Now, once dp of 0 is something that is using everything, at the beginning, you tell me what is the maximum weight available that you have. The maximum weight that is available to you would be weight maximum of the bag. The maximum weight available to you would be weight maximum of the bag. Now, if you call this dp with this value, it will compute the values automatically inside, and this will give me the final answer. This gives me the final answer. If I chose to build it from the other way around, I could have just said, I will just write it here so that everybody appreciates in the class. I can just say, otherwise I would have said, if I'm picking the ith element, my problem reduces to dp of I minus 1 because I'm building from here to here. Okay. If dp of I minus 1, this is what my problem boils down to. If I'm trying to solve it the other way around, the value available, the weight available would still be weight available minus weight of the ith element, plus the value would still be value I say add ho jayega. Okay. If I do not pick it, my dp state otherwise would become dp of I minus 1 weight available plus 0. And if this was how I was defining my dp, can you figure out the state which has the value of everything? Can you figure out the state which has the value of everything? Because I falls to I minus 1, I minus 1 falls to I minus 2, I minus 2 falls back to I minus 3. Which state will have the value of every such state? The answer would be dp of n comma weight available. I hope everybody in the class, so I've seen so many people getting confused in this so many times. In maybe different interviews that I've taken, I've seen people getting confused in this. And this is something that you should not be confused if you just understand how you're building your answer. So this would be the final answer in this case, and this would be the final answer in this case. We have discussed it, right? Cool. We have discussed it. To solve it, you can just have two options. You can just do it bottom up, or you can do top down. We discussed that in top down, you just have to write a recursive solution. You first take the base case and you just write the recurrence and you will get the answer. In bottom up, you will just start from the base case and see, using the base case, what is the next element that I can compute, and just compute in that order. Okay, I'm not going to write the code because I want to discuss several other things in the class today, but I hope everybody in the class appreciates this. Cool. One last thing. The moment you define your DP in a different manner, the base case also changes, right? The base state also changes with the different ways in which you are taking it. The base case basically means that looking at the recurrence, what is the value, what is the state that you cannot fill by looking at the recurrence? Okay, so what is the base case? Please, people, appreciate it this way. The moment you appreciate it this way, you will never be confused in base cases. Base cases basically means that the case that cannot be defined using the recurrence for us. The case that cannot be defined using the recurrence for us. In this case, can you figure out which case cannot be defined using the recurrence? Because for every state, I am using the I plus 1th value. So can you figure out for which state I plus 1 does not exist? For the nth state. Does that make sense, folks? For the nth state, the I plus 1 value does not exist. Folks, are you with me? I hope you are, right? So one is, for the nth state, this would be the base case in this case. So you would just fill dp of n, let's say weight maximum. That is, you do not choose it, it would be 0. If you chose the nth state, you have two options at the nth state, right? If you chose the nth state, then it would be w max minus weight of n, and the value would be value of n. Does that make sense to everybody? Right. And similarly, for the other case, you will have for first as the base case, and you can fill it. Cool. Let's now move ahead. This is the first thing that we did. In the meanwhile, let me now bring your attention to another kind of knapsack problem. And then we will try to appreciate, first of all, whether we can solve it greedily or not. Okay. Let me just take you to another knapsack problem. And I would want you guys to tell me whether we can solve it greedily or not. Let's assume this problem that we just discussed is called as 0-1 knapsack. Now let's say I am discussing something which is called as fractional knapsack. What does that mean? That means that let's say you are still a robber, you are still going to a shop to rob something, but let's assume this is some kind of a grocery shop. Okay. And what do you mean by a grocery shop here? What is the difference? The difference is again that you have, let's say, different values. You have n items here. Every item has some associated value with it. And with that, you can essentially have every item will have a weight also. Okay, every item will have a weight also. Now, looking at this array, the only thing that changes is that initially it was 0-1, that you can either select an element completely or you can not select an element at all. Here it's a fractional knapsack, which simply means that you can select any item x number of times, where x is a real number between 0 to 1. Does that make sense, folks? So you can actually take any fraction of any element. The moment you can take any fraction of any element, can you answer this for us now? Can you see if we can solve a greedy? Can we solve it greedily? Think about it for a minute. Right. And yeah, several of you understand that yes, you can solve this problem using greedy approaches. The point here is why you can solve this problem using greedy approach is that you can just start with the bag. You can just start with the item which gives you the maximum utility per unit cost. Okay. So what do? You start with the item that gives you maximum utility, or here the utility means value per unit weight. Okay, that gives you the maximum utility, maximum value per unit weight. Why this will work? This will work because if I am selecting something that gives me the maximum value per unit weight, I am making the most out of that weight. Does that make sense? If I am selecting a value which gives me, item which gives me the maximum value per unit weight, I am definitely making the most out of that weight. This is one argument that I'm building. Just because I am selecting the maximum, I'm making the most out of that particular weight that I just gave for the first item that I selected. The point is, whatever value is remaining, whatever weight is remaining for my bag, I can fill that also in the best possible manner because I am allowed to take fractional items. In the previous question, the problem was if I am trying to optimize for this particular weight and I'm selecting an item which gives me maximum weight per unit value, maximum value per unit weight, the problem is maybe I will be left with some weight which becomes a dead weight. I cannot fill anything in that dead weight. This was the problem. Here the point is that you will never be left with any dead weight because you can always fill it with the thing which is with anything which is the next best thing in a fractional manner. I hope I have made myself clear to everybody that this problem, the problem of fractional knapsack, can be solved greedily. Good, folks. We discussed that. Let's now move to the third problem of the day that we want to discuss. That problem is called as zero to many knapsack problem. Okay, let's discuss the third problem now. The third problem is there is another kind of knapsack problem which says zero many knapsack. Let me define the problem for you guys. The problem is again that you want to select some items which will maximize the value for you and given satisfying a constraint on the maximum weight. But this time around, you can essentially select an item from 1 to infinitely many number of times. Does that make sense? So let's assume the first element had some value 100, second had some value 120, this had 60, this has 40, this has 30, and the weights were, let's say, 10, 2, 20, 25, and 30, right? Now the point is that you can choose to select any element n number of times. You can either select that element 0 times, you can either select that element 1 times, 2 times, 3 times, n times. Okay, so you can select any element n times. The point here is just because you can select any element n times, the first answer that we discussed would not be sufficient here, right? Because the element of choice changes. Let's just wait for the element of choice. First of all, you guys tell me, can you solve this greedily? You cannot. Think about it, take it as a homework and figure out why you cannot solve it greedily. This is very simple to make an argument for. Cool. Let's. Okay. So now the problem is that you have zero to many knapsack. Okay. Now let's first of all try to build a recurrence tree. That is how it makes every problem simplified. Let's try to look at the recursive tree. Again, let's say you start with making a decision about the ith element. You again have a available weight which starts with W max, and you again have a value aggregated which starts with 0. Now you tell me the options that I have, the element of choices that I have. Either I will not select this element, that is I will select it 0 times, or I will select it 1 time, or I will select it 2 times, or I will select it 3 times, and so on and so forth. Does that make sense? Just because you have so many different options, let's try to formulate all these states. So if you take it at element 0 times, your problem now reduces to solving for I is equal to 2. Your value aggregated still remains 0. And your weight available still remains weight max. Let's assume you are taking it for 3 times. You're taking an element 3 times. What does that mean? That you're again now taking a decision for the second element because you have decided how many times you're selecting the first element. Your value aggregated is going to be value aggregated, that is what is the present value aggregated, plus 3 times the value of the ith element, right? And your weight available would be weight available, which was previously available, minus 3 times the weight of the ith element. Does that make sense to everybody? Shobit, the question here is that you can select any item n number of times. You can select an element 0 times, you can select an element 1 time, select an element 2 times, 3 times, n times. Right? There is no limit on how many times you can select an element. Does that make sense, Shobit? Can you actually figure out for me what is the maximum number of times that you can select an element? You can keep on selecting an element till the time your weight available is still greater than or equal to 0. Does that make sense? You can keep on selecting an element till the time your weight available is still greater than 0. Right? I hope it makes sense. Cool. So now we discussed this. This is one way of building the problem. But you see that this is very difficult because you do not know the fan factor. Do you know the fan factor already? You do not know the fan factor. You will have to take a loop and maybe select them one by one. That's still solvable. You can write a recurrence relationship for it, no doubt. But I would want to make you guys understand, look at this problem in a way which is more intuitive and which will make you a lot happier. Okay. So do you want me to look at it in another way as well? Okay. Let's actually look at it in another way as well. So this is one way to look at the problem. This problem can also be looked at in a different manner. Okay. The different manner is this. First of all, you take a decision for the first element. Value aggregated till this point in time is 0. The weight available at this point in time is W max, and you're good to go. Now, rather than saying that you have so many different choices, let's assume that there are only 2 choices. One choice is that you do not select this item. That is, you say that I am not selecting this item. The other choice is that let's say I am selecting this item. If I do not select this item, it would be very easy to understand that I would go to I is equal to 2. My value aggregated would still remain 0. And my weight available would still remain W max. Okay. The other option is that I choose to select it. If I choose to select it, you would agree that my weight available would become weight available minus weight of the first element because I chose to select it. My value would become value aggregated plus value of the first item that we had. But just because I only gave the option till this point in time to select this element once, but I could have essentially selected this element multiple number of times, I would still keep the I of my state equal to 1. Why would I still want to keep it 1? Because I would want to give that choice again, whether do I want to select the ith element or not select the ith element. If I do not select the ith element now, if I reach to this state, do you understand that from the beginning till this state, I have selected the I is equal to 1 times, and now I am moving to I is equal to 2. So I now know that if I wanted to select I equal to 1 times, I will choose this path. If I choose the I is equal to 1 again, would you agree that from this to this, I have already selected I 2 times, and I again give myself an option of not selecting it and selecting it. If I do not select it now, then I move to I is equal to 3, I is equal to 2, because now this state will represent that I have selected I is equal to 2 times. If I still select it, that means that I've already selected it 3 times and I'm again giving it a choice. Does that make sense to everybody? Does that make sense to everybody? This is a very, very intuitive way of understanding this problem in a slightly different manner. That at every state, you can either choose to select that element or not select that element. If you do not select that element, it would simply mean that, okay, man, I'm not selecting that element. Let me take a decision for the next element. If I choose to select an element at that point, I am still leaving the scope of selecting it 1 more time, 2 more times, 3 more times down the line. Does that make sense to everybody? This actually would, in my opinion, would actually make you a lot more happier and would allow you to understand this problem at a much deeper level. Cool. So let me just write the recurrence relationship for this as well. Let's say you have again 2 states to represent your problem, dp of I and dp of w, or dp of I and weight available. You can say that again you are going to take a maximum out of the 2 choices that you have. What are the 2 choices that you have? The first choice is that you do not select it. The second choice is that you do select it. If you do not select it, it would make it dp of I plus 1, because I did not select it. Let me now take a decision for the second element, and w max still, because I did not select it, plus 0. Okay, this is one option. The other option is that if you wanted to select it, you will say again, not go to dp of I plus 1 here, still remain at dp I, because I will want to give it chances further down the line also to select this 1 more time, 2 more times, 3 more times, and my w max, so this is w available, sorry, this is w available, this will not change. In this case, it will change because I have selected it 1 time, and the available weight would reduce, so it would become w available minus weight of the ith element plus the value of the ith element. Does that make sense to everybody? And if it makes sense to everybody, let me actually define. So I would just want to maybe discuss one more thing, which you would most likely not find at so many different places on the internet. Maybe this thing you will find at so many different places, but I just try to explain it in a much more detailed fashion. But I can maybe take 10 more minutes to explain to you something else, which maybe you will not find very easily at different places. Okay. So let's actually try to look at a variant of these problems. And before looking at the variant of these problems, let me actually take you back to the very first definitions, that the very first points that I wrote about the knapsack problems. Knapsack problem is a class of problems in which you are trying to solve some optimization problem. Generally, it is going to take exponential time, but there is some constraint which is apart from the number of elements in the array, size of the problem. There is some other constraint that actually makes this problem solvable in polynomial time. Okay, it actually makes your problem solvable in polynomial time. Good. So let me try to make you guys appreciate that constraint till this point in time was weight of the bag. Does that make sense to you guys? We were piggybacking on the weight of the bag to solve this problem in polynomial time till this point in time. Does that make sense? Because we were using the weight available as the second parameter, and that gave us fixed number of unique states, and that enabled us to solve this problem in polynomial time. Before actually that, let me explain to you what is the time complexity of this algorithm. Let me give you a formula that is going to help you all across in DP problems. The time complexity in any DP problem, the time complexity in DP problems can be very easily figured out using a way. The way is that you first of all look at the number of unique states and you multiply the number of unique states with the time taken to compute one state. The moment you keep this formula in mind, you can solve the time complexity of any DP problem very easily. Okay, how so? So let's look at in this example. So how many states do you have here, folks? How many different states do you have? Unique states. We discussed that we had two parameters here. The first parameter was I. It can take n different values. The second parameter was, the first parameter was n. The second parameter was weight max, because that gave us the upper bound on the second parameter, the weight. So n into w max is the number of unique states. And can you tell me the time that it takes you to solve any state? You are just taking a maximum of two different states. Folks, does it make sense? The time that it takes you to solve one state here is just taking a maximum of two different states, and taking a maximum of two different numbers is just the order one computation. Does that make sense to everybody? So basically it becomes n into w max into order one, which makes it order of n into w max. This is the time complexity of the knapsack DP problems that we discussed till now. Does that make sense to everybody? So this is how you compute the time complexity. Now let's actually come to the second thing that we want to discuss, a variant of this problem, and let's try to look at it. So we appreciate that we were able to solve this question in polynomial time only because of this parameter w max, which helped us solve this. Let me now instead give you a problem where this w max would be too big for you to solve it in n into w max time. Okay, so let's assume that maximum weight of the bag is very large. So let's assume, let's say weight maximum is of the order of 10 power 9. Okay, weight maximum of the box is, let's say, 10 power 9. Number of elements in the market that you are trying to loot is, let's say, 10 power 3. You guys tell me, can you solve this problem now in the approach that we just solved? Can you solve this problem in this way? We cannot. Do you appreciate why we cannot? Because the time complexity of our present approach was n into w max, and that would make it 10 power 12. And can we solve a problem which takes 10 power 12 iterations? We cannot. So this kind of a problem we will not be able to solve based on the things that we discussed till now. So what is the fundamental thing that we can see here? The fundamental thing that we can see here is that the parameter on which we are piggybacking is no longer kind to us. We can no longer piggyback on that parameter to solve this problem, right? So now let's try to look at some other parameter on which we can piggyback and solve this problem. Let's assume the other parameter on which we can piggyback is this. The other parameter was the value of any item. They are telling us the value of any item is going to be less than equal to 10 power 3. Now please appreciate, this was also a possible parameter, right? But we chose to make that parameter as a value. We chose this weight max as the parameter in the previous solutions. We piggybacked on this, but here this will not allow us to piggyback. Can't piggyback on this now. If I can't piggyback on this, let me try to piggyback on something of this. Folks, is it making some sense? Is it making some sense? Knapsack problems basically looks for a parameter which you can piggyback and solve that problem in polynomial time. Here, let me try to piggyback on value of elements and let me try to solve it somehow. I am sure that you guys would be getting some sense of it, and once I complete it, you would be able to appreciate it completely, and you would not see this being talked at different places very easily. Cool. Let's move ahead. Okay, cool. So the value I is less than equal to 10 power 3. So you tell me, folks, if I am solving this problem, what is the maximum value that I can hope to get? Let's assume there was no constraint. The maximum, the upper bound to a value, maximum value, upper bound to these maximum value that I can get, value aggregated that I can get, would be just the summation of all the values. Does that make sense? If I just do the summation of all the values, that can be the maximum value that I can get. Does that make sense, everybody? I cannot get a value more than it because I'm selecting every single item. Let's assume this is 0, 1 knapsack. I am selecting every single item, and the maximum value that I can get is summation of all the values. Right? Now, let me define my problem this way. The recursion tree still looks the same, that you have I, you have a value aggregated, and you have a weight available. But this time around, I am not using these two things to define my state, but instead, I am using these two states to define these two parameters to define my state. So my state would be something like this: dp of I, comma, the value aggregated. Okay, and the value, the answer that this is going to give you is going to be, let's say, what is the minimum weight that you will have to fill in the bag to get value is equal to value aggregated from 0 to ith elements. You would want to figure out the minimum weight. Here you do not want to maximize anything. You want to minimize the weight because you are filling weight now, assuming that you have the value filled. Does that make sense to you folks? So you are filling weight now. So what is the minimum weight that you will have to fill in the bag to get a value of value aggregated from element 0 to I? How will I write my recurrence? I will again write my recurrence like this only: dp of, let's say, I, comma, value aggregated would be equal to, I have two options, either to select that element, not to select that element, the same options I have. If I select ith element, my problem will boil down to dp of I minus 1 because I have taken a decision for the ith element. Now I have to take a decision for I minus 1th element. The value aggregated that I have till this point in time, folks, the value aggregated till this point in time would be value aggregated minus the value of the ith element. What does that mean? I am essentially trying to see whether this value I would be able to aggregate or not till the end. The moment this becomes a 0, I will be able to aggregate. Folks, is it making some sense? This is one option, that you can select the ith element. The other option is you cannot select the ith element. In that case, you would be dp of I minus 1 and your value aggregated will remain the same. Now, I have purposefully left this problem a bit open-ended. I would want you guys to spend some time, think in that direction, this direction, and see how you can solve this problem by piggybacking on the summation of value aggregators. Folks, does it make sense? Let me just give you one hint. Here, maybe the final answer will not be given by a single state, but you will have to maybe traverse on a collection of states to figure out the final answer. This is just a hint that I gave you. Think about it yourself, try to solve it. If you guys are stuck in this specific problem, you can reach out to me over LinkedIn. Yes, you will have to minimize the weight here, because the point is that you are actually defining your problem. If I have this much value, what is the minimum weight that I would require? This is still an optimization problem. You would still want to optimize on the maximum value with the minimum weight. Does it make sense, folks? In the previous approach, we were trying to do maximizations of values. Do you understand? Here, we would want to do minimizations of weights. Folks, does it make sense to everybody? Here we are going to take minimizations on weight because I am getting this value. What would be the minimum weight that will allow me to get this value? This is what makes sense, right? You would not want to define your problem saying that what is the maximum weight that would be required to get this value, right? Instead, you would want to say, what is the minimum weight which can allow me to get this value? Does that make sense to everybody? Abhishek, does that make sense to you? Right. So you would want to figure out the minimum weight that can give you that answer, that can give you that value. Cool. Thanks a lot, everybody. I hope you guys enjoyed the lecture.
Okay, let us begin with the very first session on dynamic programming of 21 days of code. This is not going to be a theoretical session. I'm just going to solve 3 problems that you guys had suggested over the LinkedIn page. Let me just give a brief about what DP is. DP is very similar to what recursion is, or divide and conquer is, so as to say. Basically, when a solution to a problem can be achieved by solving the same problem with smaller inputs, and then you solve the original problem by combining the outputs of the smaller problems, that is what is known as DP. In DP, there are 2 important properties: that the problem should be overlapping. What is meant by overlapping is that one state can be reached from multiple other states. And how to identify a DP problem? The best advice will be practice as many DP problems as you can. It's only practice with which you will easily be able to identify that, hey, this is a DP problem. And then in a DP problem, the different possible states are almost fixed. As far as my experience goes, no more than 8 or 9 different states exist of DP. Okay. Akhil, how to find number of states of DP is also dependent upon the question, and the intuition gets clear to you only when you practice. There are some very nice articles about DP that are present on Code Forces or Top Coders, so do read them. They will also help you identify what are the possible DP states that are generally asked. Okay, but without practice, you won't be able to identify that, even if you have studied a lot of theory. Okay, so for DP especially, I suggest you to solve as many problems as you can. Okay, so today we will be taking one problem from simple array DP, one from 2D string DP, and let us say one from uh, greedy or DP. Okay. So one question is by Debarun. The difficulty that I face most about DP is that how to convert a memorization solution to a bottom-up solution. That's a very good question, Debarun. What I personally do, since the time I have started solving DP problems, I always solve them from beginning in a bottom-up fashion. I don't do it this way that, hey, first I code a recursive solution, a top-down solution, and then memorize it and then convert it to bottom-up code. I never do that. I always try to create DP state in such a way that I can directly start with a bottom-up code. As I told earlier, there are no more than 7 or 8 popular states of DP. So do read those articles that are mentioning that, okay, what are the different possible DP states, and then things will get clear to you. Okay. So what I will suggest to you is, when you are solving a problem, solve it anyways, and then at least see the solution of it in a bottom-up fashion as well. Okay, so because when you have seen the solution to it in a bottom-up fashion, then you can remember it for always, and then when a similar pattern comes, you can directly apply that. Okay, so let us start with, so first people ask us to solve the longest increasing subsequence problem. Okay, let us do that. So this is the longest increasing subsequence problem, and let us solve it. So the problem says that we have to find the longest increasing subsequence of a given array of integers A. So basically we will be given an array of integers. The length of the array will be almost 2500 in worst case. And we have to find a subsequence of an array in which the elements are in strictly increasing order. Okay, strictly increasing order means the next element should be greater than, not greater than, equal to, right? Okay. And as this is a subsequence and not a subarray, so it need not be what we say contiguous. So that is also fine. And we are only asked to find the length of the longest increasing subsequence and not generally what the exact subsequence is. So we are just asked that what will be the length of the longest increasing subsequence. For example, in this array A, we can choose 1, 2, and 5. So this is the longest increasing subsequence. 1 is smaller than 2. Similarly, 2 is smaller than 5. And what is the length of this subsequence? It is 3. So we are just asked to return 3. By the way, this is a very popular problem. This is a very well-known problem. And there are 2 different kinds of solutions possible to it. This problem has one order of n square solution that is quite easy and is based upon what we say dynamic programming. And there is also an order of n log n solution to this. Okay. This is based upon what I think it is more like binary search solution. Okay. As today's class is a DP class, I won't be discussing the second order of n log n solution, but I can just send you guys the link to resources where you can study about that. Okay. But do try this because the binary search solution, once it hits you, is very good for you. Okay. Or actually, let us try to solve it in order of n log n way as well as today. Okay. Let me answer what the other questions are. How much time should I give on DP? Like 1 month? Akhil, yes, 1 month. I mean, like 1 month of solving only DP problems is fine. I mean, like it depends upon how many different problems you solve of different difficulty. If you keep on solving easy problems, you are never going to improve, right? Try to solve those problems that you were not able to solve initially. Try to grow with every problem. Okay. And other than practice, any other thing can we do? Harsh, I mean, for DP, your mind works like a machine learning model. The more practice you will give to it, the more accurate it will get with DP. Okay. I mean, like practice is the best thing. And you see a solution, always implement it, and then also read. I mean, like then also make sure that your mind is totally able to visualize that solution. Okay. Okay, let us start with this problem. So we are asked that, hey, we are given an array A and we have to find a longest increasing subsequence of this array. Awesome. So how can we do that? Okay. Suppose I know that, okay, I want to see that, hey, can I include, let me actually rewrite this array again. And let me rewrite this array. Okay. 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 So now at every iteration, I will try to see if I can include that particular element, in my longest increasing subsequence. Okay, let us see how we can do that. So suppose, can I include 0 in a subsequence? I can include this 0 in a subsequence only if there already was a subsequence in which the last element was less than 0, right? Okay. Is there any subsequence before it that has the last element less than 0? No. That means this 0 will create one more subsequence, will create another different subsequence of size 1. Okay. Then I go to the number 8. Now I try to see if I can have a subsequence that can have 8 as the last element. When is that possible? That is possible only if before this I had a subsequence that had a number less than 8 as the last number. Okay. What are the subsequences before it that have a number less than 8 as the last number? This is a subsequence that has what we say 0 as the last number. So I can put 8 ahead of it. So what will be the length of subsequence that will be at 8? It will be 1 plus 1, which will be equal to 2. Great. Now I go to 4. Now I will try to include it. When can I include? I can include it only if uh, there was a subsequence before it that had a number less than 4 as the last number. There is only one subsequence that was ending with 0. So the answer will be 1 plus 1, so which will be 2. Okay. Then you go to 12. Now, how many subsequences are there before this number 12 that end with a number less than 12? There are 3, right? This subsequence ends with a 4. This subsequence ends with a 8. This subsequence ends with a 0. So, either I can add 12 after the subsequence that ends with a 0, or I can add 12 at the end of a subsequence that ends with 8 or that ends with a 4. As we see that this is the largest length of a subsequence that ends with a number smaller than 12. So I will add 12 after this. So my answer will become 2 plus 1, which is 3. Now I go to 2. This is the only subsequence. So my answer will become 1 plus 1, which is 2. Now I go to 10. What are the subsequences? This is a subsequence. This is a subsequence. This and this. Out of these, the largest is 2. I mean, like the largest one has a length of 2. So my answer will become 2 plus 1, which is 3. Great. Now I go to 6. What are the subsequences that have a number less than 6 as the last number? This, this, and this. Out of these, the length of the largest one is 2. So this one will also become 3. Great. Then I go to 14. Then I will see here all these subsequences have the last number as less than 14. Then out of all these, which one has the smallest length? Which one has the largest length? This has the largest length of 3, right? So my answer here will become 3 plus 1, which is 4. Okay, I hope now the intuition is clear. So what we can do is, we can create a DP table. Let me just write the size of A. Then I will create a DP table of the same size. What is the value of the first index going to be? The value of the first index is always going to be 1, right? So I can say dp0 is 1. That is the base case. Now my answer is, initially it is 1. Then what I do, I say for int I equals to 1, I less than n plus plus I. Now I try to find all those DP states in which the last number was less than the current number. So what I will do, I will say for int j equals to 0, j less than I plus plus j. If array j was less than array I, that means the largest, the increasing subsequence at that number ended with something lesser than the current element, then I can say that dpi is equal to max of dpi, comma 1 plus dpj, right? Basically, the length, what was the length of the subsequence at that particular number plus adding the current element. Okay, great. So now my answer will become max of answer, comma dpi, because I have to find the largest length. And finally, I can return answer here. What is the time complexity of this? This is order of n. This is also order of n. So the time complexity will become order of n square. I think the answer should be correct. Let us test it. What is the issue? Is it less than or is it less than equal to 0, 4, 6, 9, 13, 15, 0, 4, 6, 9, 11, 15? Return an integer in longest increasing subsequence or unique, and in which the subsequence is as long as possible. Okay. Here I am returning 14, but the expected output is 15. For int j equals to 0, j less than I. Max of dpi. Initially it will be 0, comma 1 plus dpj. That is also fine. Is it less than or is it less than equal to? Because it says find the longest increasing, find a subsequence of array in which the subsequence elements are in strictly increasing order. So that means the elements are always increasing. I mean, like, equal to is not allowed. But in this particular question, the answer is coming out to be 15. Why will that be the case? That will be the case when int I equals to 1, I less than n plus I. I say if aj is less than, let us say, what if aj is less than equal to, what will be the output then? Then also my question returns 14. Okay, so that is not the issue. There is some other issue then. I created a TP of size n. Initially my answer is 1. Then I say for int I equals to 1, I less than n plus I. Okay. Then I iterate over each the element of array I. And then I run a loop from j equals to 0 to j less than I. Okay. That is also perfect. Then I say if array j is less than array I. Okay. Then I update my TPI, so which is this TPI, to max of TPI, comma, I mean, like, what was the value presently there, and 1 plus TPJ. So that is also fine. But the answer here is 15. Let me try to debug this code as to why this is happening. Let me say that I output my TPI at each stage. This is coming 14 and 14. This is correct. So this should be 14 and 14. That is perfectly correct. And I'm not getting 14 anywhere else. So that is also fine. But I am getting this as 0. Okay, now I got the issue. Initially, the stage of dpi will be 1, right? So initially, each of the element will be dpn, comma 1. That I have set the default value should be 1, right? If it is the only element of dp, then the answer should be 1. So I always had actually off by 1 error. I forgot that. So I mean, like, if that element is the smallest element, like in the case of, suppose, what if say that -1 would have been here, then -1 would have been the single element. There would have been no element smaller than this, right? So the dp state here should be 1 and not 0. So now we will be correct. Correct. So we got this as well, and let's move to the next question. That was wildcard pattern matching. Actually, there are two questions like that as far as I remember in interview bit. That is the regular expression match and regular expression match 2. Which one do we want to solve? Let us try to solve the regular expression match 2. Okay, let's try to solve this. Okay, so I'm not sure if any one of you has ever seen regex before, but what regex allows you to is basically to find all the strings in your directory that match a particular pattern. Okay, so basically we are asked to implement a very similar function to how regexes would be working, where the possible values in a regex are fixed. Like here we are told that we have to implement a regular expression matching algorithm that can support a dot and a asterisk. What dot means? A dot can match any character, any single character in my in the whole string. So basically, let me say that does dot match A? Yes, that is true. Okay. Does dot match B? Yes, that is also true. But does dot match AA? No. Okay. So a full stop can match only one character, any character. Okay. A full stop can match one occurrence of any character. Okay. Then the second unique character given to us is asterisk. And asterisk can match 0 or more of the preceding element. What it means is that suppose we have A star. A star can match A, it can match AA, it can also match AAA, and so on. Okay. So this is what asterisk means. One or more than one, 0 or more than 0 occurrences of the previous character in my regular expression pattern. Okay. So for example, does this string AA, does this pattern match A? No, because though this A is equal to A, but then there should also be a second A, but it's not present in the string. Okay, so the very first one is a string, the second one is a pattern, but the same thing holds. This matches. This doesn't match because the string is AAA, but the pattern is only 2 A's. So it doesn't directly match. Now, double A, does it match A star? Yes, it does. Why? Because A star is equal to single A. It is also equal to double A. It is also equal to triple A and so on. So, does AB match star asterisk? Dot asterisk? It does. Why? Let us say, what can this dot represent? This dot can represent A. This dot can also represent B, right? And similarly, this can also represent C. That means, what can dot asterisk represent? Dot asterisk can represent AA. It can also represent BB. It can also represent CC, right? So that is why dot asterisk is true, right? Matches 0 or more of the preceding element. Yeah, preceding element is a full stop, so it can match precede 0 or more than 0 occurrences of previous character, which is anything. So it can match 0 or more occurrences of anything. So basically anything can be A, so it will match A. It can also match AB, it can also match AC, and so on. Okay, cool. Now let us try to solve this using dynamic programming. So we are given a string. Let us say that this is the string and this is the pattern. Okay. Now let us try to, like whenever a string problem is given to you, there are multiple string problems like longest, like even any 2D array DP problem, you have to, like normally what happens is that, or even longest common subsequence problem as such in strings. So what you always do, like let us say that we have a string like A, B, C, D, A, and also another string like B, C, E, F, G. Suppose you are given two strings and you try to apply a 2D DP problem. You always try to apply 2D DP in the form of prefixes. That what is common between the prefix of the string A up to index 4 and string B up to index suppose 2. Okay, you always try to compute this. What is common between the first string for up to index X and the second string up to index Y? That is the common pattern in all the 2D DP problems. Adil, yes, a star can match an empty string also, right? I think it should be. I'm not really sure. Let me see. Can star match an empty string? But I think star is, like if there is only a star, then that means there is no preceding element. Okay, so Adil, if there is only a star, that means there is no preceding element. Then the pattern is invalid actually. Okay, because a star is valid only if there is a preceding character. Okay, so I think then the string, then your pattern will actually be invalid. That is what I hope, but let us see. Okay, now, so I will like following this pattern, we will try to create a DP state of two things. That means string till I satisfies the pattern till j. Okay, so I will try to create a DP state where I will say dpij represents true if the string till index I satisfies the pattern till index j. Okay, okay. Always, like this is one suggestion. Like whenever you are trying to solve a problem using DP, try to represent your DP state in some English sentence. Okay, after you have represented an English a DP state in English sentence, then you can easily find what we say. Like DP, like the state relations. Which states will it depend upon? Does A match C star A star B? Yes, it actually does. Why? Why? Because there can be zero occurrences of C. Okay, because I'm like B is nothing but zero occurrences of C. Then two occurrences of A and one occurrence of B. So then it will match. Because a star can also represent zero occurrences of the previous character. So C star will basically just change to an empty string. So that is why it will satisfy. Okay. So now I will try to create a Boolean DP state. How can my DP state be? Let me say that the length of my string is n, and my length of the pattern is p dot size. Okay. Now I will try to create a 2D DP matrix. So I will try to create a DP matrix of vector of bool, I can say, because I only have to represent true or false DP, which will be having number of rows equal to n plus 1. Why n plus 1? While doing DP problems, I personally like indexing by 1 to avoid out of bound array checks. Okay, that is why I always create a DP array of size n plus 1, and this will be a vector of pool of size m plus 1. For those who are not familiar with what we say the C++ syntax, this is creating nothing but a DP matrix of n plus 1 cross m plus 1 dimension. Okay, this is doing nothing but this. Great. So will okay, let us say that let us talk about two strings, and let us say that we have a string like this, and this is my pattern. Okay, does nothing match nothing? I mean, like when there is nothing in the character and nothing in the string, does nothing match nothing? It does, right? So what I can say is dp0 0 is true. I mean, like nothing matches nothing. So if I talk about indexing, I am starting 1 base indexing. So 0 will be here, 1, 2, and 3. So basically 0 0 is representing does nothing match nothing. Okay, great. So now we have taken care of the base case. Now I will try to solve the whole question. Okay, and let us take care of other scenarios as well. The others will always be false. Now I will try to see if the string till index I matches the pattern till index j. Now, what are the different scenarios? The very first scenario is character at index I, at string I, is equal to character at pattern j, right? Okay. First of all, before that, let us take care of the special characters in the pattern, because that is where an issue can happen. Okay, so I can say that if pattern j minus 1 is equal to dot, then I will handle it separately. Else, if this pattern is b, right? Yes. If bj minus 1 is equal to dot, then I will handle it separately. Also, if bj minus 1 is equal to, what do we say, a star, then also I will handle it separately. Else in this case, pattern j is a character, is an English alphabet. So that means it should match the si, right? It should directly match the character at string at ith index, right? Okay, so that means I can say that if string I minus 1 is equal to pattern j minus 1, then only I can say dpij is equal to 2. Sure, Adil, I will try to draw it after I have coded it, and then I will try to rerun with a test case. Okay, cool. Acha. So now once the character that I'm trying to match in the pattern is not a wildcard character, then that means I can only match it with a character, right? Why? I can match this A of the pattern with only an A of the original character, correct? I mean, like I can match this A only with an A from here. Is that correct? So now let us try to see. So that is the one thing. Now let us see what we will do if bj minus 1 is equal to a full stop. If it is a full stop, then what I can do? A full stop can match with one occurrence, with exactly one occurrence of any character. Let us assume that the pij will be equal to nothing but dp of I minus 1, j minus 1. What this means is, let us say, like the jth character of pattern matches uh, matches ith character of string. Suppose if the jth character of the pattern matches the ith character of the string, then basically I have to see if whatever the characters were there in the pattern before the jth character match whatever the string was there before the ith character. Okay, nothing else. The problem becomes interesting if we are taking the wildcard character into consideration, right? Because wildcard character can actually match 0 or more than one occurrence of the previous character, right? Okay. Now let us try to see how we can do that. First, we try to find that what is the character that came before P. Okay. What is the character that came in the pattern before this star? What I mean is that for this case, it should return me a C. For this case, it should return me a full stop. For this case, it should return me a full stop. Similarly, for this case, it should return me an A. Okay. What I can say is that I think actually the previous element with the first character, right? Yeah, it will always be the previous character. I'm like, we assume that the patterns are defined. So I can say that previous character is equal to what we say, the B j minus 2. Okay. Okay. So what are the cases now? The first case is that if the string at ith minus 1 is equal to the previous character. What does this mean? This means it matches one occurrence of the preceding character. Okay, so what the problem reduces to, the dpij will be equal to nothing but dpi minus 1 j minus 1, because it has matched one occurrence of the previous character. Okay, awesome. Then what are the other cases? The other case is that it is not equal to the previous character. Then that might happen that ai minus 1, it might actually happen that if the previous character is equal to dot, if previous character is a full stop, like in this case, the previous character was a full stop. So that means it will definitely match it, right? In that case, it will definitely match it. So in that case, I can say that dpij will definitely be equal to dpi minus 1, j minus 1. That thing is clear. Then I will say else if a minus 1 is equal to the previous character, then also this is correct. But is there any other case in which this can be true? In this case, dpij should be false, right? Because it should not match with anything else. Else dpij should be equal to false, right? Can it match with something? What if there are multiple C's and then there is a star? Let us take care of a case like, let us say that there is a C, there is a star, and then I have this C, 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 C. So now when I will be computing this and this will match. Now when I will be computing this and this won't match. Okay. Then when I will be computing this and this will be equal to dpi minus 1. This matches till this. This is also true. When I will be computing this and this dp state, then I will get this is equal to this matches this, which is false, right? This can also match this. So actually, I should return dp else if a minus 1 is equal to the previous character, dpij is equal to dpi minus 1 j, because this will take care of the second occurrence of it as well, right? Take care of multiple occurrences. Like star can match multiple characters. This thing will take care of this, right? Am I missing anything else? And finally, I will have to return dpnm. But is there anything else that I seem to be missing? So I can say that if there is a full stop, then that means the particular characters definitely match, and then the only thing reduces to a smaller subproblem. So that is fine. If it's an asterisk, I'm like, let us take care of this case at the end. Else, I'm like, both are English characters, then they should directly match. There is nothing better that we can do, right? Because there is an English character there, there's an English character there. So then they should definitely match. So dpij will be equal to actually dpi minus 1 j minus 1. Why? Because these characters definitely match, and whatever came before this should also match whatever came before this. So this will be the state here. Now let us take care of this important thing. If the previous character is a full stop, then it will directly match. It will definitely match, right? Yes. Okay, else if a minus 1 is equal to the previous character. Else if a minus 1 is equal to the previous character, that means these both are matching, then this problem reduces to, I'm like, multiple occurrences of that, right? Yes. And okay, suppose then I am saying dpi minus 1 j. Okay, this matches this. So let us actually try to create the dp table for this thing. This cc matches this c star. Now when I try to match this thing with this thing, I will say that this C matches this C. So the problem reduces to if this particular thing matches this particular thing. That is true, and then it will be true. Now when I say that if this matches this thing, okay, now this thing is matching this thing, so that is good. And now I will try to check if this thing is also going to match this thing. But then here I will be having an issue. How should I make sure that this is true, right? So I should make sure that if there is a previous occurrence of a character, then that can also be a 0, right? An asterisk can also be a previous occurrence of a null character, because this asterisk can also represent that there was no occurrence still here, right? Yes. Then dpij will be equal to dpi minus 1 j minus 2. If the previous character is a full stop, that is correct, but that can also be a previous occurrence of nothing. So that is true, then that is true. What are we missing here? This particular case is a very difficult case to handle, so as to have all the cases. The bj minus 2 will be the character that was just preceding the asterisk, right? And that character can be a full stop. That means it should match with any character, okay? But I might or might not want to match it, right? If I try to match the ith character of string with this full stop, then the problem reduces to this problem. Or I might not like to match it. If I don't like to match it, then the problem reduces to dpi j minus 2, right? J minus 2 will make it 0 occurrences of the pattern of this character and the string till now. This makes sense. Okay. I now in this case I say if a minus 1 is equal to the previous character, then either I will like to match it, and then the problem reduces to this, or I will not like to match it, right? Or I will say that I don't want to match it, or this is equal to dpi of j minus 2. In that case, if we take care of this string, this problem will be equal to either I match this C with this C, then the problem reduces to dpi minus 1j, which will be equal to matching this C with this C star, okay? Or if I match this C, or this reduces to dpi of j minus 2, which will be false. Now when I try to match this and this, either I will match both of these. If this is equal to this, the problem reduces to dpi minus 1j. dpi minus 1 will be this and dpj will be this. How can I match this? I should somehow make sure that this is true, right? I think that is the only case that is left. I mean, like, if we match this, how should a C star match a C? because this can mean a one occurrence of C. So as this matches this, the problem can also reduce to matching dpi minus 1 j minus 2, right? Or dpi minus 1 j minus 2. That will be one thing. dpi minus 1 j minus 2. Why this? This will mean this is non-occurrence of this. This is the second occurrence of this, or more than second. This will means this was the only occurrence of it. Okay, and this thing will mean what? This thing will mean zero occurrence. Correct. Now this should be correct. Now the only question comes: can our pattern be something like this? C star 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 star. Then I can also say that while first let us say that can that case happen? Wait a moment. In previous index is equal to what we say j minus 1, while previous index is greater than equal to 0 and pattern previous index is equal to star. I will try to minus previous index. So now my previous character will be nothing but b of previous index. Now if the previous character is a full stop, the problem reduces to either I will match it. Now this j will be nothing but, I think let us actually first try to see if what all cases does it pass. Let us then try to see. So we are failing at this case, and why? Because this is a zero occurrence of this and this should match, right? And A, B star C means zero occurrence of this. So this should return to you. Let's actually take this case and then see how we are going to create a string. So our 2D table will look like A, and this will be C, and then this will be A. Just let me declare a 0 0 as well. This will be a A, this will be a B, this will be a star, and this will be a C. Does an empty string match an empty string? Yes, it does match. Now I try to see if all rest are 0. If I try to see does A match A, this will go into this particular scenario, right? Does A match A? This will be the scenario when ai minus 1 is equal to bj minus 1. So this will be nothing but equal to this. So this thing will become 1. So that is fine. Right? Now the problem is, does A match A comma B? No, it doesn't, because B is also a character and B is not equal to A. So this will not match. Then the question is, does A match A B star? Right? So here we will try to see that we have a star, we have an asterisk here. So the previous character is a B. Is a B. Yes. We go into this case, else case. Correct. We found where the issue is. dpij is either equal to dp of I minus 1. Okay. So I can match none occurrence of that. I mean, like, then it will be equal to dpi comma j minus 2. What it means is that it will only match 0 occurrences of previous character, right? And it should match the 0 occurrences of the previous character. So now this particular case should be correct. Let me take it as a custom input. Yep. So that case we have handled now. That thing is perfectly correct. This can only match 0 occurrences of the previous character. This means this will match dpi minus 1j, which will match more than 1. I mean, like first or second to greater than 2, greater than equal to 2 occurrence of the previous character. This will match 0 occurrences of the previous character, and this will match the first occurrence of the previous character, only one occurrence of the previous character. Now this makes sense, but if there is multiple stars, then it might fail. But first we have to see if there can be multiple stars, right? Rest all should be fine. Yes. And now the question is, will it pass submit case? Can there be multiple stars together? There should not be, but can there be? I mean, like, it's not specified in the input. Let's try to submit it. A, B, C, D is not matching A dot star, C dot star, and this. Interesting. What are we following? Here we have told dpi minus 1. Okay, we have taken care of this case. We have also taken care of this case. We didn't actually improve this, right? This was the dpi minus 1 j minus 1 means one occurrence of the previous character. Okay, dpi j minus 2 means more than one occurrence of the previous character. This can also be zero occurrences of the previous character, right? Or not. If previous character is equal to this, then the problem reduces to either I will match the previous character with this, then that is fine, or I will reduce the problem to matching this with something else. Let us try to take this case and then see where we are failing. A, B, C, B, C, D, and A dot star, C dot star D. In this case, this dot star is representing this B, and this dot star is representing this B and C. Okay, B, if it is a dot, if the previous character is a dot, then it can match any number of previous characters, right? Yes, then it can actually match any number of the previous characters. So then we just have to find one of the previous indexes where it can match. So that means this is equal to another order of n loop, right? This will be another order of n loop where I try to see if anything matches till here. I mean, like if there is any part of this substring till here that matches this particular index, because baki sabko, because other things I will just satisfy with this stuff, with this full stop. That makes sense. So the only question reduces to this, that if there was any star here, right? So then the answer will be to false, let us say. And I can say that for int I equals to 1, I less than, let us say I is equal to 0, I less than equal, I less than, what is my current character, I less than, for int L is equal to 0, L less than I plus plus L. That means if there was any character where dp of L j minus 2 was true. So was n is equal to tp or equals to tp L comma j minus 2. What I mean by this is, was there any pair like this, that hey, I mean, like when I'm trying to match this ABCBC with this thing, okay, I will try to see if there was any pair that matched till here in this particular string. After that, everything I will match with a full stop. Okay, so TPIJ will be nothing but was any. This has increased my time complexity, but hopefully should satisfy this case, right? This should satisfy this case. Correct, it does. So now, is there anything I'm missing? Because then I haven't still found that if there can be multiple characters. Interesting. Can there be? First, let us try to submit it and then we will know. Let's first try to test and then we will submit. Am I missing any other case? I don't know. Cool. I got it correct. There is not a case of any character, any star, any multiple stars together. But I mean, like, I hope you guys were able to find, I mean, like, how we actually found the approach. What were the different test cases that we had to see? Okay. And still we missed out on some of the edge cases. Okay. I will take up the doubts on this question as well as at the end. But let us solve one more question for the day that people had requested, and then we will take on doubts. Okay. What is the next question? The next question is the max sum path in binary tree. Let us do that question and then we will take the doubts. So in the max sum path in binary tree, we are given a binary tree that is rooted, right? I think we are given a, yeah, we are given a tree node. So I mean, like if you are given a tree node and then it's a DP problem, that is still an easier problem. Why? Because you know the root of the tree and that helps you in some things. So we are given a binary tree T and we have to find a path in the tree of the maximum sum. Okay. And the path can start and end at any node. So by the way, I mean, like, what is the definition of a path? A path is a sequence of nodes such that no node is repeated more than once. So there is no cycle. It's a simple path. Okay. So now let us try to take care of, let us see the examples first. In this example, the largest path starts from this 2, goes up to 1, and then comes down to 3. So the weight of the path is 2 plus 1, which is 3, plus 3, which is 6. So 6 is the answer. In this case, what is the maximum sum path? The maximum sum path is only this node minus 10. Okay. The maximum sum path is nothing but only this node, which is minus 10. Okay. Acha. Now let us try to see that, hey, let us try to see, can we include a particular node in the path? How can we know? What will be the weight of the path if we include that node in the path? Okay. If we include this node in the path, that means either I will have a path from the left side that will join it and a path from the right side that will join it. What I mean is that suppose there was some tree like this, that here is a 1 and here's a 2 and here's a 3, then here is a 4 and then here's a 5. Okay, so when I try to include the upper wala 1 in my path, then I will join it with one path that was coming towards upside from the left hand side. What was the weight of that path? That path was 3 to 2 with having a weight of 5. Similarly, I will also join it with a path that will start at 4 and will end at 5. That will only be in the right hand side of the subtree. This is also a very popular problem, by the way. So I will also join it with a path that is from 4 to 5 and having a weight of 9. Okay, suppose the path on the right hand side, these nodes were minus 4 and minus 5. These nodes were minus 4 and minus 5. Would you ever want to include these nodes in the path? No, right? Why? Because their sum will be less than 0. And that will be bad for me. I don't want to subtract anything from the path. That is a very bad thing for me. So I will always add the maximum path on the right side with weight greater than equal to 0 and the maximum weight path on left side with weight greater than equal to 0, because otherwise it's going to reduce something from my weight. So I don't want to do that. So let me say that I can make a recursive function that will return me the maximum weight of the path from the left side node and the maximum weight of the path from the right side node. So what I do is that a max path node, which is past a tree node. Okay. In this case, I always try to write the code along with the solution because that makes more sense. I will say, the base case is that if A is null, in that case, I can just return 0 because there is nothing. It's a 0. Okay. Else, what I will try to do. First thing, I will try to find what is the maximum path on the left hand side, which will be equal to max path node on A left. Similarly, I will try to find the right path, which will be equal to max path node on A right. We will always try to have the paths have a weight greater than or equal to 0, right? So I can make it the left path is equal to max of 0, max path node of A to left. And similarly, max of 0, max path node A ka right. Interesting. Now, what should I return? I should return the value at A plus left path plus right path. That is the maximum path weight that will end at my current node A. Correct? Great. So that thing makes some sense. In fact, if I know this thing, then I don't need to do anything else, right? I can just paste this thing here. I don't need a separate function as well. And I think this should work directly. Oh, this is max path sum now. So, and then let's try to test it. This doesn't work. Why doesn't this work? Given a binary path tree, we have to find the maximum path sum. The path may start and end at any node in the tree. Okay. The number of nodes are 10 to the power 4, so the integer overflow will never happen because the maximum path will be 10 to the power 7 something, so that is fine. If A is null, I'm returning 0. Here I'm returning something very big. That is also not going to happen. Interesting. A eval plus left path plus right path, right? That I am not doing wrong. That is correct. If left path is this, I have to say max of 0 comma this. I think I did return correct, right? I think yes, this was an addition issue. What happened? The expected return value is 7347. Okay. And I'm returning something 93,096. Okay. If A is null, I return a 0. Else I try to find what is the max path sum on the left side. Okay. And I also try to find what is the max path sum on the right side. Okay. And then I return the value at that plus left path length plus right path length. That also seems to be fine. But why my answer is coming as wrong? Can I have a path from up to down? Yes, I can have that. And what I will return? Yes, I got the issue. What I will like, what is the issue with this is, suppose your tree is like this, then what we are doing wrong is this thing. I'm like, we can't have it in this function. We should have another function, which says int max path ending here. Okay, int max path ending here is this, given a tree node value at A. So now I try to find what is the maximum path in both of those subtrees. So this, okay, I try to do the exact same thing. Now if A is equal to null, I do this, and this is the same thing. Okay, now I will have a global answer variable, which will be initially, let us say, int min. And I will say that answer is equal to max of answer, comma, what I got from here. I'm like, that is a triangular path, right? That is a triangular path. But now I can't return this path. For example, suppose there was a 2 here. There was a, let us say, a 7 here. Okay. This 7 needs to know a very straight path that will be ending at 7. So it can't include a path that will be 3 to 1 minus 4 minus 5. It should be one straight direction path, right? So I will return the A plus max of these two, max of left path, comma, right path. Okay, because now I need only a one direction path. I don't need a cross and a straight line path, right? That is wrong. So answer is equal to int min. So I will always have to set it in when I start the function. So answer will be int min. That makes some sense. Then I will compute the left path, I will compute the right path, and I return this. Great. So I will just do a what we say max path ending here of A, and then I can finally do return answer. That should be correct. That should be correct. Earlier I was passing this thing completely there, which is totally wrong. Answer is equal to max of answer eval plus what is the issue here? Okay, I missed a semicolon. Did I miss anything else? No, seems fine. Return a val plus this. This is correct. I think this was the answer that was supposed to be written. I'm not really sure, but this seemed to be what. Yes. Yep. So I hope you guys were able to understand that what my function was returning was a path that could be like this and then something here. So this was a triangular path, which is not correct. So then it will cause an issue up on the upper side. Okay. So then I try to let me submit it and it should be working. Great. We got 389 out of 400 points. Interesting. Let's briefly watch the n log n solution of the longest increasing subsequence, and then we will end the lecture. Okay. Acha. Now suppose you are creating a subsequence. Okay. Now let us say my subsequence is like this. I mean, like, I'm not going to explain that solution in a lot of depth because we can discuss it in the section that we will be discussing. I mean, like, we can have a separate video on discussing this as well. In fact, that will be a very good thing. We can upload a video there to the channel. But I mean, like, I will still try to give a kind of an intuition to this. Okay. Suppose we get, I mean, like, we are trying to create a longest increasing subsequence. Okay. When we get a zero, our initial subsequence will be only zero, right? This will be the initial subsequence. Okay. Now, when we get a 8, where would you like to put this 8? You would, I mean, like, it makes total sense to put this 8 here. Correct? Okay. Then we get a 4. Now, we try to see where can we put this 4. This 4 should, I mean, like, replace a particular number, right? This 4 should replace a previous number. This 4, I mean, like, by the way, do you guys, I mean, like, guys, try to see that this particular array that we are creating is sorted, is always sorted. Okay. Now we try to see which 4, I mean, like, which 4 can go where. Out of these two, 0, 8, 0, 4, which is a better thing to take? 0, 4 is always a better thing to take, right? Because 0, 4 can later be expanded to 0, 4, 7 of size 3, but 0, 8 won't be able to. So 0, 4 allows us more scope to expand it, right? So what we do is we try to find the first number in the current increasing subsequence that is greater than 4. Okay, so we find this 8, we replace this 8 by 4. And what is the length of the current subsequence? It is still 2, right? What is the length of the current largest subsequence? It is still 2. Great. Then we go to 12. We try to find the first index that is greater than 12. There is no index. So that means we put 12 here. Now, what is the length of the largest subsequence? It is 3. So basically, try to see that the array that we are maintaining is storing the length of the largest subsequence. That will be our answer. Now we go to 2. We try to find the first index that is larger than 2. We find this is 4. We replace this 4 with 2. What is the length of the largest increasing subsequence till now? It is still 3. And by the way, if you would have seen till here, the length of the largest subsequence is 3, right? Great. Now we try to put 10. We put 10. We find this is the best place. We replace this by 10. And what is the length of the largest subsequence till now? It is still 10. And also, if you would have seen, the length of the largest subsequence till this place is also 3, right? Okay. Now we go to 6. We replace this 10 by 6. Now we go to 14. There is no number that is greater than 14, so we put 14 here. And what will be the length of the largest subsequence now? It is 4. And you also see that the length of the largest subsequence is 4 here. Okay. Now let me try to write the code, and then the other things will start becoming more clear to you. Okay. So let me comment out this code. This was the DP code. And let me write the binary search code now. Initially, my current array will be empty. Okay. Then I will say for I equals to 0, I less than n plus plus I. First thing I will check if array I, if if current array dot empty or array I is greater than what we say current array dot back. If any of those two cases is true, in what does that mean? If these two cases is true, that means I will push the current number, right? Because here 14 was larger than whatever was here, that means 6. So I just pushed back 14. I increased the size of my current array with 1. Okay. Then what is the other case? In the next case, I will try to find first index that is greater than or equal to the value greater than equal to AI. Okay. How can I do that? as the current array is always being maintained in a sorted order. I mean, like if you would have observed this above thing, this would have always been maintained in a sorted order. I can binary search this. I can say L is equal to 0, R equal to 0. Then I say while L is less than equal to R, mid is equal to L plus R minus L by 2. If array mid is greater than equal to array I will say I mean like index is equal to mid, R is equal to mid minus 1. This is normal binary search, okay? Else L is equal to mid plus 1. I'm basically trying to find the first index that has the value greater than or equal to mid, okay? So I will say int is equal to minus 1. And what I do after this, I just change my current array int to array I. Okay. What should R be? R should actually be equal to current array dot size minus 1. Awesome. And finally, I can just return my current array dot size, because that was always storing the length of the largest increasing subsequence till now. Let us try to test it. Yep, and this is correct, and this is submit. Now what did I do? Shit. Okay. Again, I am failing at this case. Oh, I have a runtime error. Why do I have a runtime error? I say current array dot empty or array I is greater than current array dot back. That is fine. Am I anytime in? Yes. Okay, I have to find the very first index that is greater than or equal to the current number. Okay. Can the index be minus 1? Can it happen that all the numbers are greater than or equal to the current number? In that case, I will just return 0, right? In that case, I will just return. Okay, when can index be minus 1? This can be minus 1 if all the numbers in the array are smaller than. So yes, if all the numbers are smaller than that. So I can say if index is equal to minus 1, that means all the numbers in the array are smaller than that number. Then this will be happening, right? If index is equal to minus 1, when can that happen? That can happen only if all the numbers are smaller than that. All the numbers are smaller than that, because if there was any one index that was greater than or equal to AI, then I would have changed my index to that mid, right? And I'm saying that all the numbers, all the indexes are smaller than that. Else if array mid is greater than equal to array sorry, we have to actually check else if current array mid. Okay, so this is the issue. It should be current array mid. Let us test this. So we just had a naming issue. And if we were checking array mid, we should have checked current array mid. This, I mean, this is running wrong. That is another issue. I say that okay, and I can then set the current array mid is greater than equal to AI index is equal to mid. If current array mid is greater than equal to AI, then that might or might not be the first index. Then I try to reduce it. Okay, current array dot pushback is correct. My current array is the array L is equal to 0, R is equal to current array dot size minus 1. That is perfectly fine. I say while L is less than equal to R, I try to find mid. I try to see what is the number at that mid index. Is it greater than or equal to the current number that I'm going to add? If it is greater than, for example, suppose I was going to add 15 here, I go to 6. Is 6 greater than or equal to 15? No, it is not. So I will have to search here. Is 14 greater than equal to? Yes. 14 is also not, so I will go here. So let us say that we were trying to add a number 3. Let us say we were trying to add a number 3. I try to see here. I mean, like, is 6 greater than equal to 3? Yes, it is. So it can be the answer, or the answer can be somewhere here. Correct. So, and I'm returning the current array dot size. That makes some sense. That makes the sense. But why is the answer 14 in? Why is the answer 4 in this case? The answer should be something like 14. So I try to find the first index, then index is equal to mid. If index is equal to, this should not be happening. Oh, this is correct. Yep, you're correct. Because I had added that if condition while debugging, I forgot to remove that. That was the issue. Correct. We got all the points correct. I think many people don't know that this problem can also be solved in n log n in this small code only. Okay, so in this small code, so that was a new thing.
So today's session is on the dynamic programming day 2. So here I have the questions, and the questions demand that has been made is of buy and sell stock 2. So let's dive into that question. Okay, let's get started. Say you have an array A for which the ith element is the price of a given stock on day I. Okay, you have to design an algorithm to find the maximum profit. Now you may complete as many transactions as you like. That is, buy one and sell one share of a stock multiple times. However, you may not engage in multiple transactions at the same time. That is, you must sell the stock before you buy again. Okay. So let's actually see the example and let's see what it means. So we have an integer array which represents the day-wise stocks that are available. Now the output is 2. That means, so here it says that we have bought the stock on day 0, that means 1, and we have sold it on day 1. Okay, first of all, let me name them. So let's utilize this space. Let's say we have so this is index 0, 1, 2, and index 0 we have 1, 2, 3. So we bought the stock on day 1, on day 0, and we sell it on day 1. So we get the profit of 1, right? And if we buy it on day 1 and sell it on day 2, so that will be again be a profit of 1. So that means total profit is equal to 2. So that is what this example is saying. And if we look at the next example, so we can buy the stock on day, so it says that buy the stock on day 1, that is cost is 2, and sell the stock on day 2, that is at this, right? So that means the profit is 10 minus 2, and that is 8. Now the thing it says is that we can buy and sell multiple stocks, but the constraint is that we cannot keep on buying the stock and keep storing it with us and with the intent of selling it later. We cannot do that. So please understand this problem. Many people feel confused with the problem. So it says that once you have bought the stock, first you have to sell it, and then only you can again buy it and then sell it, right? So that's what the problem is. So let's say we have 7, 1, 5, 3, 6 and 4. Okay, these are the prices of the stocks on days. So 0, 1, 2, 3, 4, 5 are the days. Now let's talk about the brute force solution first. Okay, now the brute force solution would be that I can buy the stock, right? So I can buy the stock here, and then I can see that when can I sell the stock. Okay, so if I buy the stock at first at 0th day, then can I sell the stock at any day? No, right? Because this stock is greater than, has a greater value than any of the stock, right? So therefore I cannot simply sell this stock. Let's move to the next element. Now on the next element, if we buy the stock, then we can sell it on day 2, we can sell it on day 3, on day 4, day 5, right? So now the possibility is that let's say I sell the stock on day 2, so that will give me a profit of 4, and plus now there is a sub problem, isn't it? So I will add the cost to the sub problem, and the sub problem is of 5, 3, 6, 4, isn't it? Now this is the sub problem that I can try buying this stock and sell it on the further days. So just what I have discussed now will be applicable to all the sub problems. Okay. So this is the case when I have sold my stock of 1 on day 2, that is at the cost of 5. That will give me a profit of 4. Now, if let's say I sell the stock on day 3, so that will give me the profit of 2, and I have a sub problem which is 3, which is 364, right? Likewise, if I sell the stock on day 6, so that will be a profit of 5, and that will be giving me the sub problem of 6 and 4, right? And if I sell the stock on day 5, so the profit is of 3, and I will get the sub problem of 4, right? So this is it. Now this will happen with every element, okay? So as I move to 5, this will happen with 5 as well, that I can, so first of all, when can I sell this stock of 5? So I can sell it on day 4, right? So that will give me a profit of 1, and the sub problem is of 6 and 4. So for 5, that's it, right? Then we will move on to the next element, and 3 can be sold on day 4. So that means give me a profit of 3 plus 6, 4, and I can sell it on day 5. So profit is of 1, and the sub problem is this, right? So likewise, I can keep on going on, and that will give me these sub problems for every element, okay? Now the thing is that there are n elements, and if you see from this visualization that I have created in here, so if you see on the first level, we are, for n elements, we are having n iterations, we are having n possible cases. So that will give the time complexity of order of n square, right? Yes. So Goyal TY, yes, you can. So if you are buying a stock on first day, and if you are selling the stock on the second day, then you can immediately buy the next stock on the second day, okay? So if you see from the problem that has been given on the platform, then you'll be clear, okay? Cool. So now for n elements at the first level, we are having n possibilities. So the time complexity is of n square. Now this is happening n times, isn't it? For every element, this could happen n times in the worst case. So that is the first level, right? And now such that I'll be having the next level, having n elements, n possibilities for n elements, right? Then again at the next level, I'll be having n elements, and so on. So that will be like n into n into n, and so on. So it will be n to the power n. The time complexity is of n to the power n, which is very huge, okay? Which is very huge. So now let's see how can we optimize this using DP. So this was the brute force approach. Now let's see. So we have 7, 1, 5, 3, 6, 4. Okay, let's say this is my DP array, and here this I'm going to do in bottom up fashion. Okay, I have a 1D array. Now if let's say I have only a single stock, then is there any point of so there won't be any profit, right? Will there be any profit? No, right? Can we make it 0? So here we can put the value 0. Okay, we can put the value 0. Now, so basically at DPI, I will say that it will be nothing but maximum profit we got by doing transactions only till that ith position. Okay, so if let's say I am here, then this is the, let's say, the last point where I will be calculating the profit for, and that I'll be doing for every element. Okay, cool. Now I am at this index, I am at this position. Now the thing is that either, so basically we are actually taking it in a way that what profit can I achieve on this ith day. Okay, so I can either sell a stock or I don't sell a stock. If I don't sell a stock, that means whatever is present over here will be my answer. Okay, but if I sell a stock, then I'll be actually moving from the first location till the I minus 1th location to check if there is a value which is lesser than this value on which I can, so let's say I am at index this. Okay, now for this index, let's say this is I and J is at this position. So basically either I do not sell any stock on this day, or let's say I sell a stock this on this day. Why am I able to sell stock J on this day? Because J is lesser than I, right? Element at J is lesser than I. So that I have to keep on checking. So there are two possibilities now, that I can sell a stock on one day, on that particular day, or I cannot sell a stock on that day, right? So here what we'll get, so the idea is that for I which goes from 1 to n minus 1, okay, and let's say this is our DP array, and DP0 will be initialized to 0. Now we'll be doing for j which goes from 0 to I minus 1, okay, what we'll be doing, so also what we have to take, so we have to take that when we are not considering the element, so in that case whatever is the answer at dpi minus 1, we will have that, okay, we will have that. Now this is the case when I am not selling the stock on that particular day. Now when I have to sell, so I'll be moving through this loop. What I'll be doing is dp of I will be equal to maximum of dp of I, okay, comma deep ai, that is the so wait a minute, it will be whatever the profit is at dp of j plus a of I minus a of j. So this is the additional profit that I have got while selling the stock on day I that I have bought on day j. So this is the profit, and this will be added to whatever was the profit on dp of j. Is that clear? Is this thing clear? That whatever was the profit on jth day, that will be added to the profit that I have achieved now, okay. So this is what the idea is, and this we'll do for all the elements, cool, and the time complexity would be order of n square, right? We have two loops. So from order of n to the power n, we have actually come to order of n square. Are you guys able to relate that why it's order of n square now? How are we processing through this? How are we moving through this? Is it fine, guys? Cool. So let's code it quickly, and then we'll move on to the more optimized solution, okay? So let's quickly code it. So we are taking an array, right? So int dp, first of all, let's consider the size as well. Okay, so here I have int n where I'll take the size. Then if n is equal to 0, or if n equal to 1, then we'll return 0, okay? Cool. Now let's move ahead. Let's create our dp array, and let's initialize all the elements to 0. So dp of I is equal to 0. Now moving forward, so we are going to all the elements starting from index 1, okay? So starting from index 1, we go to all the elements, and what we'll do, we'll put the dp of I is equal to dp of I minus 1, that is when we are not selling the stock on day I, okay? But when we are selling, so we have to check that when that stock was bought, okay, we will go from 0 all the way when j is less than I and j plus plus. Now, so it will be nothing but dp of I is equal to maximum of dp of I comma dp of j plus a of I minus a of j, okay, and then we'll simply return dp of n minus 1. Let's see if this works. Cool, it worked. Okay, so we have actually got the partial points. Now this can be further optimized. Okay, let's see the optimized case now. So here, let's move forward. Now this can be further optimized if we make some observation. Okay, so what I'm doing over here, I am actually, whatever was the profit on day j, I am adding it to my current profit, right? Okay, so here we have this solution. Cool. Now dp of j plus dp of I minus ai minus aj we have. Now if I tweak this a little, so what will I get? I will get AI plus dp of j minus aj. Can I write it like this? Can I write it like this? Okay. So now so basically we have to increase our profit. Okay. To increase the profit, I want this to be increased, and for that I want this to be increased, right? So to increase this, that is the difference shall be increased. Okay. So for that we can maintain. So we were just iterating through the j loop to get this difference, so that this could be maximized. We were checking for which j value is this difference maximum. Now instead of iterating through that j array, we can actually keep on storing the maximum value of this till now. Okay, till now. Does that make sense? We were only moving our j loop for checking that for which value of j are we getting this, are we getting this as the maximum, so that our complete the complete value is maximum, right? So instead of going to each jth position, we can actually store this particular value in a variable, and then we can keep on updating that variable. Yes, the greedy method is of order of n time complexity, and we'll also see that how this can be changed to order of n time complexity. Okay, Ankit, does that make sense? So let me just code this thing now, or let me just code it. If you guys still have any issue, we can discuss it. Okay, so let's just proceed now. So here basically we have to change, we have to remove this loop. Okay, so for that basically we have to keep on storing this particular value, as in we have dp of j plus, we have this here. Now I am changing it a little to get a of I plus dp of j minus a of j. Now I am trying to store this value. So here I can maintain a maxi variable, let's say, which is initially is equal to 0 minus a of I, a of 0. Okay. So basically this will be gone. This will be gone. And we have maxi is equal to, sorry, first we have to update the dp of I. So dp of I is equal to max of dp of I, comma, a of I plus maxi, right? So basically here this value has been replaced by maxi. Okay, and also we have to update our maxi variable, max equal to maxi, comma, dp of I minus a of I. Okay, and here we go. So now we will simply, so here we have actually eliminated the jth loop. Does that make sense to everyone? Now let's see if this works. Let's see it, and here we go. Cool, we have actually got the solution correct. We have got all the points. So now this is the solution of order of time complexity is equal is so time is order of n square, right? Sorry, order of n, and space is order of n only, right? Order of n. But the space can also be optimized in this case. The space can be optimized. If you carefully notice over here, then we have, so basically dp of I is equal to dp of I minus 1. For every ith position, we are reliable on this dp array, because we want dp of I minus 1. So if we store somewhere this dp of I minus 1, and if we utilize it in some way, so then we can, actually do it in just order of one space. Now I want you guys to try that thing. So here we are at time of order of n and space of order of n. So let's move on to the next question, and the next question is minimum jumps array. So this is a very important question. So given a array of non-negative integers a of length n, you are initially positioned at the first index of the array. Each element in the array represents your maximum jump length at that position. Return the minimum number of jumps required to reach the last index. If it's not possible to reach the last index, then return -1. Okay. So the first and the only argument that we have here is of integer a. Now let's see what the problem says with the help of an example. So we have 2, 1, 1, and the array is 2, 1, 1. So the output is 1. Why? Because the problem says that from index 0, we have to reach the last index. So we can take simply the jump of 2 to reach the last index. So the element at that position signifies that how many jumps we can take at max. Okay, we can take the jump of 1. We can take the jump of 2 for this particular variable. Here we can take just the jump of 1. Again, we can take the just the jump of 1. So let's say I have 2, 1, 2, 3, 1, 1, 4. Okay. Now let's maintain the DP. So here we are going to do the DP thing. So this is the bottom of DP that I have taken. So basically, if I talk about the brute force approach in this case, then what we'll do, we will check till all the, so whenever I am at some position, I can go to, from here, this is 2. So I can go jump to here, or I can jump to here, right? Then I will again call for this part as well as this part. Okay, till the position that I can jump for the first element. Then after jumping to, let's say 3, I will call for rest of the sub problem, and after jumping to 1, then I will call for rest of the sub problem. So this will go on for every element, right? So this is the brute force solution. Now let's talk about the DP solution. For DP solution, we have created the DP array. Let's name it 0, 1, 2, 3, 4. Okay, so basically the DPI signifies that till that particular position, how many minimum number of jumps we can take. Okay, so DP of I tells the minimum jumps we can take from 0 to I. Okay, so if we are standing at this position, then we don't have to take, so considering this position as the last index, we don't have to take any jump. So this will be 0, right? Now if I am at index 1, then from index, so so to calculate the number of jumps to reach index 1, that means, so let's name it here 1, 0, 1, 2, 3, 4. Okay, if I want to go to index 1, then I have to start from 0 till I minus 1. Okay, I will check that from index, so let's start J from here. I will check that if from this position I can go to this position or not. How to check that? We will do it in a way like 0 plus, that is the index J, plus A of J. If it's greater than equal to I, that means we can move from index J till index I. So this is 0 plus 2, that is 2. It's greater than equal to 1. Here 1 is I. So we can move from this element to this element, and we will get what? We will get nothing but the cost, the jumps we need to reach at this position plus 1. Does that make sense? Now we come, we are done with these positions. Now we go we place our I at here, and J will again be placed at 0. Okay, so from 0, can we move to this? So this is nothing but 0 plus 2, and that is 2. 2 is greater than equal to 2. We are at index 2 now. So yes, so that means there will be nothing but 0 plus 1. So 1 will come over here. Now our J will move to this position. Let's see if we can from J till I. So this is nothing but 1 plus 3, that is 4. It's greater than equal to 2. So yes, we can jump from this position, that is from this position to this position, and that will be nothing but whatever is present at this position plus 1. So we have to check that if dp of I is equal to max of dp of I, comma dp of j plus 1. So right now dp of I is maximum, then dp of j plus 1, so it will remain 1. Okay, and this we will go on till the loop is completed. Okay, let's first code it up, then we will complete the array. So we have, so we'll take the size of the array, and if the size of the array is equal to 1, that means only one element, so we'll return 0. If the size is equal to 0, but if the first element is equal to 0, in that case we will return 0, right? We will return 0. Sorry, if n equal to 1, we will return -1, because if we cannot take, if we cannot reach to the end element, okay, sorry, this will be -1. That means we cannot go, right? Now let's move on. Let's dp is equal to dp of n. Now dp of 0 be 0. So for int I equal to 0, so sorry, we'll start with 1. I less than n I plus plus, and dp of I shall be initialized to int max. Cool. Now what we have to do, we have to run our second for loop, that is int j is equal to 0 till j is less than I and j plus plus. Then if, okay, so dp of I is equal to maximum of dp of I, comma, we have dp of j plus 1, okay, and we will at the end return. So if the last element was reachable, that means if dp of n minus 1 is equal to int max, right? So that means it was not reachable. In that case, we will return -1, else we will return dp of n minus 1. Okay, where did it fail? Okay, so we actually didn't check the condition here. The condition needs to be checked, that if a of I, if j plus a of j is greater than equal to I, and also we have to check that if dp of j is not equal to int max. Why? Because it's a possibility that we could not reach dp of j, right? So in that case, but if we can, so we will calculate, right? Now let's see. Okay, sorry, this should be minimum, right? Okay, we actually have got the partially correct solution, because the thing is that this is also possible. This the solution to this problem is also possible in order of n. That is the greedy approach. I want you guys to explore that approach. Okay, here we have discussed the so if anyone has any doubt, you can ask in this particular solution. So Alind, we are adding aj to j because we are checking that if from jth position, if we are able to go to I or not. Okay. Why are we doing j plus a of j? Because we are checking that if from some position, will we be able to go or not? Okay. So if we are at this position and we are trying to jump to this location, we won't be able to go because we can only take at most 2 steps. So that's why we are checking j plus, that is, this is 0. So 0 plus 2, that is 2. It's lesser than the index I. Let's say I is here, and therefore we cannot jump till here, and therefore we are checking the condition. Okay, is that clear? Sure. Let's move to the next problem. And next problem we are taking is of edit distance. Okay. The problem is, first of all, it's very important. So the problem says, problem is important because it is asked in many interviews. Okay, it's very common, and you should definitely understand it, like how it works. So let's dive in the problem. So it says that given 2 strings A and B, find the minimum number of steps required to convert A to B. Okay, each operation is counted as 1 step. Now you have the following 3 operations per word permitted on a word. The first is, it says that insert a character, okay, delete a character, and replace a character. So to convert a string A to B, I can do these three things, okay, and I have to find the minimum steps that I can take to convert one string to another string. For example, in the input, let's say we have A, B, A, D, and we want to convert it to A, B, A, C. So here we can simply replace D by C, right? And that will give the cost of what? 1, right? Now here in this case, it says that the cost is 2. Why? Because here we are replacing S with T, that adds to the cost of 1. Then here we are actually inserting, so after converting this S to T, we will be inserting I. Okay, so that will add up another 1 and the cost will be 2. Okay, so is the problem clear to everyone? So basically we have to convert a given 2 strings are there, right? So we have to convert string A to string B. We can make 3 possible conversions with each character, that we can replace a character, we can insert a character, and we can delete a character. Okay, so we have to do it in minimum possible time, minimum possible steps. So let's see. So let's say I have Sunday over here and I want to convert it to Saturday. Cool. So what can we do here? Day at the end are same. So now we can actually convert this sun to Saturday. And what we can do? We can, so this is also same, right? So that means we are left with UN and ATUR. So we can insert what? So guys, here we are going to do it using 2D DP, the bottom up approach. Okay. Here I have actually, so we are trying to convert this string to this string. Okay. Let's see how we'll proceed. Here we are going to convert this string to this string. We have to consider the empty cases as well. When let's say this string is empty, so this is that case, and let's say this string is empty, so this is that case. Now, if we want, so this is what we have to convert in. So let's say if we want to convert this to this, what we'll have to do? What should be the output here? It shall be 0, right? I don't have to do any operation. Now, if I want to convert this empty string to S, in that case, I have to add one character. If I want to convert this empty string to S and A, for that I have to add 2 characters. Then 3 characters, 4 characters, 5 characters, 6 characters, 7 characters, and 8 characters, right? So that's what I have to do. Now, what if we have to convert this string to just an empty string? In that case, we have to delete one character. Then we have to delete 2 characters, right? To convert Sunday to empty string, we have to delete 3 characters. To convert sun, we have to delete 3 characters. To convert SUND to empty string, we have to delete 4 characters, then 5 characters, and finally 6 characters. Okay, so this is the base case. This is the base case. Now, the point is that whenever, so at some, if we are standing at some position, right? Let's say we are standing at some position, then we are actually trying to do what? We are trying to see if I want to get the answer till that particular position. That means I want to get the answer for this and this, right? Answer for this and this part. Then what should I do? So please note that this is, let's say, the box and we are standing at here. Okay. Now this is the case. So this is the case when I'll be ignoring the current characters. Okay, when can I ignore the current characters? When the character at this place and this place are same, then we can ignore them and we can take whatever the value was previous, right? Whatever the value we had, so we can take this value. We can take this value, okay? We can ignore and we can, so let's say I have, so this and this are same, right? This and this are same and the corresponding block is this. So we can ignore this. And whatever is the result from till here and here, we can consider that. Okay, we can consider that. So I hope it makes sense that why are we taking this position if there is a match? I minus 1, j minus 1 when there is a match. Okay, now this is the case. So just the position above the current cell, this is the place when we can insert an element. Okay, so this is for inserting an element. So when we have not found a match and we want to insert an element, so we will pick up the, so that means let's say here we are, okay, and we want to insert an element, so we will be checking this particular location. Okay, we will be checking I minus 1 jth position. So here we have I minus 1 and j, and then for deletion we will be checking I comma j minus 1. Okay, why? Because if let's say, so let's say we are at this block only, and or let's say when there is not a match, let's say this block, now this is deletion. Why? This signifies deletion, that when we are not considering this, so when we are just considering, so we are ignoring this character, and that means we are just checking what was the result for this and this string. Okay, so then at that point we can take this value. Okay, makes sense that we are ignoring this character, we are deleting this character, and we are checking that what was the maximum when we have ignored this character. Okay, because if we are ignoring, that means we don't have to check for this particular position. Whatever will be the value ignoring this character, we will take it from its left cell. Okay, now let's proceed with this. Let's see what we'll get. Let's try run the approach. Cool. So here S and S match, therefore we can ignore them and take whatever is present over here, that is 0. That means we have to make no changes, and therefore the steps are 0. Now we go to this S and so we go to this S and U, they don't match. Whatever is minimum at this location or this location or this location, we will take it and we will add 1 to the cost, because now we are considering these elements as well. Okay, so 0 is minimum, we will take 0 and add 1 for the current operation. Now let's move on. So we have, now we will be checking for, so let me fill it. So S and U, so we are at S and N, they don't match. We will take the minimum of this and this. So 1 is minimum, this becomes 2. Now S and D, so S and D also don't match. The minimum is 2, this becomes 3. Now S and A don't match, minimum is 3, this becomes 4. S and Y don't match, minimum is 4 and this becomes 5. Now we are at this element and we will check again. So A and S doesn't match, minimum is 0, we will take 1. Then A and U don't match, so 0 is minimum, we will add 1 to it. A and N doesn't match, 2 we'll get. A and D, for A and D what we'll get? We will get 3. Then here we will this match, right? So we will take this cell, so add 1 to it. Sorry, we don't have to do anything, we will just take it. Okay, we don't have to add to it. Cool. Now A and Y are there, so 4 will come over here. Then so likewise, shall I fill the complete table, or it makes sense now? Is it clear that we have to take the minimum of the 3 cells, that is the above, the on the top left corner, so either, so if you are standing at this, so minimum of this or this or this. Okay, so let's code it, and finally we'll get our result at this location. Okay, because ultimately we are considering the complete string. The single cell actually tells that what is the value, the jumps till that particular position. Okay, the last cell will tell us the final result, so we will return the last cell. So we have the, let's take the string length in some variables. So let's say m is equal to a dot length and n is equal to a dot b dot length. We will take a 2D DP where it will be of a size of m cross n, right? And the first cell will have a value of 0, right? Because that will signify the empty strings. So to convert an empty string to empty string will cost us 0. Now what do we have to do? So basically we have to do the base cases thing, right? So I is equal to 1, we will start from 1. I less than, so rows is m, right? And okay, so string a is equal to, so we have string int I equal to 1, I is less than equal to, okay, so here the string length n, we will be going through all the, let's say all the columns, so that is n, okay, and I plus plus, so that will be dp of 0 I is equal to dp of 0 I minus 1 plus 1. What are we doing? We are actually initializing our base cases, okay? We are just adding the values from the previous cell on the top rows and the top, on the top row and the top column. Int j is equal to, let's say 1, and j is less than equal to m, j plus plus. Now dp of, so dp of j 0 is equal to dp of j minus 1, 0 plus 1, okay. Cool. Now let's move through all the cells, that is it's equal to m and I plus plus, then for int j equal to 1, then j less than equal to n, j plus plus, then int, let's say we are taking the, storing the distance like this, so q1 denotes the cost, c1, let's say cost is equal to dp of I minus 1 j, okay. So this is the cost when we are inserting an element. Int c2 equal to dp of I j minus 1. This is the cost when we are deleting the elements, and this is the cost of replacing the element, okay. I minus 1, j minus 1. By replacement, it means that we have changed the character to the character that we want. Now if the current character, if it's same, right, I minus 1 is equal to b of j minus 1. So at this point, dp of I j is equal to dp of I minus 1, j minus 1, right? We don't have to add any cost because the characters are same. Else, what do we have to store? So we have to store dp of I j is equal to 1 plus minimum of q1 comma minimum of q2 comma q3, okay? And finally, we will return dp of mn. Oh, these are not q1, q2. These are c1, c2, c3. Cool. Okay. dp of int m is equal to a dot length. Perfect. mn dp of m plus 1. Right. Sorry. So it should be m plus 1. Okay. Let's see now. Cool. We have got the solution. Cool. So let me actually make you go through the question that we discussed previously. I think few of you had doubt in that. See, we are doing DP and we were doing it in bottom up manner. Okay. Notice that what DP, so you should know that what the state of the DP is, right? What these cells represent, and that actually tells what's the state of the DP. So this is the DP array and this is the given array. Now the state of the DP says that DP of I is equal to maximum profit by doing, we have got by doing the transaction till that particular point. Okay, if we are standing at here, then from 0 till this point, what is the profit that we have achieved? So that's what the DP of I tells. Is that clear? Now moving ahead, at position 0, we cannot sell this stock even if we buy. So therefore the profit is 0. Now if we go to the next position, so here we have to check for, we have two options. Either we can take this up, we can sell the stock on this particular day to get the profit, So that is one, sell the stock. Second is don't sell, right? So these are the only two options. Now, in case of sell the stock, we will start. So let's say we are at position this, and for selling the stock, we will start from this position all the way till this position. Okay, till I minus 1, this is I, till I minus 1 we will go. We will check if the value of jth element is smaller than this element, right? And also what we'll check? We'll check that whatever is the value at, let's say j is here, actually let's say j is here, okay? Now whatever is the value till this point, we will add to the profit we have achieved by selling stock 1 on by selling the cost of 1 on for cost of 3. That means dp of j plus a of I minus a of j. Make sense? Does that make sense? That why is this condition for? Now this is why we have taken this thing. Okay, so this is the case when we are selling the stock. We will check for every I. We will check for every j, starting the j from 0 all the way till I minus 1. We will check for this condition. And there is some other case as well when we don't sell the stock. If we don't sell the stock, then we take whatever is present on its previous day. So let's say we want to see the cost of this. So if we are not selling on this day, then we are actually checking whatever is present on here will come over here. Okay. So whatever is maximum from whatever is maximum between this, that is when we are selling the stock and when we don't want to sell it stock. So whatever is maximum, we will take that value in here. Does that make sense? So that's essentially what we are doing. Okay. So that's what the DP solution is of order of n square. Okay. The pseudocode says that we'll take the DP array, then DP of 0 will be initialized to 0 because of the condition I told over here, that we can, if we even buy it, we cannot sell it. And we will go to all the elements starting from position 1 all the way till n minus 1. And if DP of I is equal, so here we are actually taking the previous DPI. That means we are actually not, this is the case when we are not considering selling the stock on day ith. So therefore we are taking the cost till I minus 1. We are taking the profit till I minus 1 day. I hope that makes sense. Now moving ahead, if we want to sell it, so we are going from j, we are going j equal to I minus 1, right? And we will be taking whatever is maximum between dp of I minus 1 and this condition that I told you. Okay, so this is the condition when we are taking stock, when we are selling stock, and this is the condition when we are not selling. Okay, now this will do for all the elements, and that will take the time complexity of order of n square. Now I said that we can optimize it. So if we see this particular condition, this condition, right? In this condition, we want to maximize this condition. I have actually changed it to this. Okay, I have changed it, and this I have got now. So to maximize this, this should be maximum, right? Now we are actually iterating in this j loop to find that for which value of j this is maximum. For which value of j this is maximum. Okay. So instead of going through every element and checking for which value of j this thing is maximum, we can actually keep on storing it from the start. Okay. So that's what we are doing over here, that we are storing it from the start. We can actually maintain a max variable. Let's call it max var. Okay. And this can, so initially it will be initialized to dp of j, which will be nothing but 0. Initially the dp of j is 0, right? And we will be doing 0 minus a of j. Okay, minus a of j. So we will get dp of 0 minus a of, let's call it variable only. Okay, let's call it variable, equal to a of 0. Okay, this will be initialized. Now whenever we'll be moving in a loop, right? So let me write it. So for I dp array dp of 0 initialized to 0 variable, let's call it maxi only. Okay, now it will be initialized to dp of 0 minus a of 0. Okay, so for I which goes from 1 to n minus 1, dp of I is equal to dp of I minus 1 when we are not selling the stock. So we are taking the stock of the previous day. Now, if we are selling the stock, so we will do dp of I equal to maximum of dp of I, comma, what we want, a of I plus maxi, and then we will update this maxi variable to max of maxi, comma, dp of I minus a of I. So essentially we have done it in just order of n.
So today is the third and the final day where we will be solving particularly DP problems. So we will start with the road cutting problem, and if there is any other request for a problem that you want us to solve, please do mention in the comments, or I will pick up any two randomly. Okay, great. Let us begin. The problem says that there is a road of length n, okay, on x-axis. So basically it's an horizontal road with its left end at x is equal to 0 and right end at x is equal to n. Okay, so basically n plus 1 points are there. Now there are m weak points out of those n plus 1 points, denoted by positive integer values all less than n. So basically there are m a1 to am weak points. Okay, we have to cut the road at all these weak points. Okay, so we have to make a cut at these points such that you can perform these cuts in any order. After a cut, road gets divided into two smaller subroads. Yeah, because it will be divided. Okay, cost of making a cut is the length of the subroad in which you are making a cut. Cost of making a cut is the length of the subroad in which you are making a cut. Okay, your aim is to minimize this cost. Okay, return an array denoting the sequence in which you will make cuts. If two different sequences of cuts give the same cost, return the lexicographically smallest. Okay. Okay. Basically, we have to give the sequence of points in which we will cut, right? And the points should be lexicographically smallest. And we have to basically we have to denote the sequence as well. Okay, that what will be the sequence in which we will cut. So basically, there is a road 1, 2, 5. So that means I will first make a cut at. So this is the, I have to minimize the cost. So minimum cost will be here in those two. And out of these, the minimum will be 2, 1, 5. So I have to return 2, 1, 5. Got it. Okay. So I mean, like the problem to find the minimum seems to be a simple DP problem that, hey, I mean, like DPIJ can represent the minimum cost, to what we say, to cut from index I to index j. That can be a possible thing, but let me say that what is the value of this n. Okay, the n can be up to 10 to the power 9. So basically we can't create a 10 to the power 9 dp table anyway, so we have to do something in terms of m. So if I have made a cut here, then let me think of the dp table. I mean, like in any dp question, when it comes, I try to first find that what the state relation can be. And I haven't seen this question earlier, so let me think what the status, what the dp state can be. So for example, n is equal to 6 and a is equal to 1, 2, 5. Okay. Let me, I mean, like when the values are not given, is m always less than n or less than n? Okay. By positive integer. So a1 will be greater than 0 and am will be less than n. So let me say I add 0 here and I add 6 here, because padding often helps in such DB problems. And then if I create a 2D DP, I'm not really sure if I should create a 2D DP, but if I create a 2D DP, then it should be, then the answer should be, let us say that the indexes are uh, 0, 1, 2, 3, 4. So my final answer should be in dp 0 to 4. Okay. Which will represent the minimum sum of costs to split roads, right? Okay, let us say that we say this. So Abhishek has asked to please explain the question. Sure, Abhishek, let me explain the question again. So basically, we are given a road of length n. On these road, there are some points. There are m points like A1 to AM, where we have to make cuts on the road. Okay, the cost for a cut is equal to the present length of that particular road. For example, suppose there is initially the road of length 6. Suppose you make the cut 2. Suppose you first make the cut at position 2 or position 1 or position 5. The cost that will be added will be 6 because that is the current length of the code. Now, suppose you had earlier made the cut at 2. Now, when you will make the cut at 1, the length will be 0 to 2, right? The length will be 0 to 2, which will be 3. So the cost added will be 3. So that is, I mean, like, then you have to find the minimum permutation of cuts such that the total cost is minimum. So suppose that is the minimum cost or minimum sum of cost to split roads from index I to index j. Okay. Then that means I can make cuts from index, what we say, I plus 1 to j minus 1. Let us say that we say this. I mean, like, I can make cuts from index I plus 1 to j minus 1. Let us say I can make cuts. Suppose that particular index is k. Okay, suppose that particular index is k. Then after this, the problem will reduce to dp of I to k because I have already made a cut at k plus dp of k to j plus what is the current length of that, right? So, okay, I mean, like, I can say the minimum sum of cost to split roads such that, then I think I should change that, such that the current road is of length I to j, is of length I to j. I mean, like, j minus I plus 1, or what we say, ai to aj. This seems to make some sense. Okay, then I will add what is the current length of the code of the road. That will be aj minus ai plus 1, right? Aj minus ai plus 1, or will it be equal to aj minus ai? So this dp relation seems to be fine. I'm not really sure. Let me say that, okay, I will first, I have to, okay, first let me actually put this 0 and this n in the array p. Okay, so as to pad it. Okay, if I pad it, then I will have to say that b dot pushback. Let me actually make it a comment. B dot pushback a is the length of that. Then I will say reverse b, and I will b dot pushback 0. Then I will again reverse it so as to bring it to the correct position. Okay, cool. This seems to be fine. And now if I have padded it, now I have to create a dp table. I have to create dp table of this length, right? The new length is what we say, the new b dot size. So I will create a dp table of n cross n, vector of n, dp of n plus 1, comma vector of n, dp of n plus 1. One thing is that it is not given to us that what is the value of this m going to be. So I hope an order of n square solution passes, order of n square solution in time as well as in space, but I don't really know. Okay, so this will be the dp matrix that I will create. What will be the base case for this? The very first case will be of length 3, right? All the length 3 cases I have to handle because that is where I can make a cut. Okay, so I can say for int length equals to 3 and the maximum length will be n, right? 1, 2, 3, 4, right? So n will be, in this case, n will be 5, so it will be less than n. For int length equals to 3, length less than n, plus length. That will be the base case. Then I will have to put an I. Okay, then what will be I for int I equals to 0? I mean, like, what the start position should be. I plus length should be less than n plus I. J is equal to I plus length, right? Or will it be I plus length minus 1? It will be I plus length minus 1, right? I plus length minus 1 should be less than n, because for index 0, length 3 and set 2. Index 2. Okay. So some people want the problem link. This is the problem link. Okay, now I know j. Then I have to have another loop. So it will be an order of n cube time complexity then. For int k equals to I plus 1, k less than j. I mean, like, that is where I will split at plus k. Initially, I will set the value of dpij to be int max. I set the value of dpij to be int max. But I have to finally return what we say the sequence. But I'm firstly trying to see if I can, if the algorithm that I'm coding up has the correct answer, then I will be able to create the parent array to that. dpij will be equal to min of dpij, comma, array j minus array I. That will be the length of the code. That will be the cost that will be added, plus dp of I to k plus dp of k to j. That is a subproblem that should be there. And then finally I will return dp of 0 to n minus 1. That should be correct, but that is not returning the the original answer, right? So let me first see if this is returning the correct cost. Then we will try to, what we say, create the answer thing, right? Okay, so suppose let us take care of this test case only. For example, 6 and 1 to 5. Let us try to see what it returns there. Is it A? It is B. Bj minus bi, and then they should go. Returning 0. Why? I say dpij is equal to int max and length is equal to 3. dpi will be 0, yes. So I plus length minus 1 should be less than n, so that is fine. Is bj minus bi min of dpij, which will be initially int max, comma bj minus bi plus dpik plus dpkj. Okay, so I should be returning the correct answer, right? Let me try to see what dpij is coming for each index. Just if I suppose do that, what is this? I j, and then I say dpij. I just first want to clarify if my algorithm is correct. I'm just trying to see it. So then it will give me, yeah. So from 0 to 2, the cost is coming to be 2, which is correct, because that is the only thing. I never do 0, 1, 2, 3, 4, right? I never do 0. So this array will change to, what we say, this array will change to 0, 1, 2, 5, 6, right? So the answer will be at 0 to 4, but I'm never computing 0 to 4 here as such. Okay. I'm computing 1 to 4, but I'm not computing 0 to 4. I plus length minus 1 should be less than equal to n, right? N is 4. N is 5 here, so this thing is coming out to be correct. My length should be less than or equal to n. My length starts from 3, and my length should be equal to n, right? Length is less than equal to n, then it will be computed, I think. So that is the thing that, yes. So the answer is 12, and the 12 was minimum. That thing we also knew, right? So at least we are getting the correct TP answer. I mean, like, correct numerical value. The issue now comes, how will we, how will we create the lexicographically smallest permutation? Okay. One thing that is not probably given is that, is the array of B1 to BM sorted? It is not given, right? It is not given that B1 to BM is sorted. So we have to sort that. Sort of B dot begin to B dot end. Okay, great. So that thing we already know, and now we also know that we are able to come to the correct answer. Okay, so now the problem remains as to how we will create the lexicographically smallest permutation. Okay, So to that, suppose I'm also storing that what was the index that gave me the minimum value. Suppose what was the index that gave me the minimum value? Suppose that I also had this. Rather than doing this, I would have told that if command x is less than dpij, okay, that means dpij is first equal to this, this, and then I can also say that this will be min index. Then I can say that min index of I to j will be nothing but k. Okay. So once I have this, I know that dpij is going to return to the correct solution. So now I have to just probably process this matrix backward. That in which order will I make the cut? So I can say that vector of int answer initially will be empty. Okay. Currently my endpoint is 0. Int start 0 and end is equal to my end will be n minus 1, right? So till when should I find the sequence of cuts? I should keep cutting on. Okay, then I know that there are two problems in which that I have to find. Okay, the dpij and dpkj. Right. So first, the very first cut will be actually what we say answer dot pushback min int start comma end. But then there will be sub cuts, right? Then there will be multiple other cuts that will also be there. So how should I compute that? Because otherwise I will have to do that recursively, right? I first compute that, then I compute that, or can I do a recursive function to do that? Probably if I do a recursive function, then it will automatically handle it, right? So let me say that suppose my void recurs to what we say start comma end, and this is the vector of end at answer. Okay, when do I know that this is done? I know this when if start minus end is less than 3, right? If end minus start is less than 3, less than 2. If end minus start plus 1, that is the length, is less than or equal to 2. That means I don't have any answer. That means I don't have to put anything. So in that case, I can return. Else, I will say answer dot pushback min end of ij, min end of start end, and then I will recurse for start to min end of this with this answer, and I will also need to pass my min end, right? And min end, okay. Similarly, then I can recurse from this plus 1 to, sorry, this only to end, and I will need to pass it answer and min end. Okay, and here I will have to have this min end. Okay. I will actually need to have the P of that particular base, not min end, but okay, let us say that I have this. Then I will say recurse of 0 to n minus 1 to answer to min end. But now I will have to change everything in the answer to reverse of that. So then I will have to change everything in the answer to reverse of to basically what was the value in this B. So I will have to say for auto iterative index in answer, index will be equal to P of index, and I can return answer. This should probably work because I'm calculating it in the correct sequence. It should be correct probably. What am I missing? I don't have a semicolon here. Anything else? Probably no. So I'm returning 2, 1, 5, which is absolutely correct. I hope I'm not missing any other test case, but let us test it. Yes, and let us try to submit it. I hope the time complexity passes because we are not given the constraints. Yeah, so we are told that we are failing for the partially correct. Okay, so we have some wrong answer for larger test cases. Right. Okay, so probably the time limit is exceeding, right? Because there is no other reason why it should fail. The time limit can be exceeded because this is order of n cube. Can we bring this to order of n square? When I am computing this dpij, I need to know this thing is always going to be fixed. So I need to know the minimum value of dpik plus dpkj, right? So if somehow I know from I to k, which is the minimum k that stores that, but that I can't do. Currently, I'm at an order of n cube solution, and probably because I'm failing this, I have to get it to order of n square or anything else. No, probably the answer is there some modular arithmetic issue? Yes, there can be modular arithmetic issue, right? Because n can be up to 10 to the power 9. Then if n is up to 10 to the power 9, and all these numbers are 10 to the power 9, 10 to the power 9 minus 1, 10 to the power 9 minus 2, in that case, I will overflow, right? Yes. In that case, I will overflow. So then I think I will need to have this vector as a vector of long end, long end, and then probably this should work. Because there doesn't seem to be any other issue then. If I'm failing for the large test cases and I know that there is overflow possible, then probably that is the thing. And then this dpij will also have to be something larger than integer max, right? Or not. Eventually it should not, but it can be. So I have to let me make it. I have taken it as a long 10 to the power 17. Then let me first test for the normal cases if I am doing some compilation issues. I think I will be doing this matrix. Yeah, because min index is k, but bj minus bi can be larger, right? So yeah, this seems to be fine. Okay, so this seems to be fine, and then let us try to submit it if that is the real issue, because that is what seems to me as to be the issue. And yes, let's try to do it. Correct, that was the issue, and we fixed it. Okay, great. So basically, how I identified that that was the issue, that was an interesting thing. That here I saw that the value of n can be up to 10 to the power 9. So when we were calculating the cost of the last three indexes, they can be 10 to the power 9, 10 to the power 9 minus 1, 10 to the power 9 minus 2, which will be equal to 3 into 10 to the power 9 minus 3, which is greater than integer max. So there was a chance of an overflow, and we fixed it up. Okay, great.
Hello everyone, in this video we're going to talk about the problems from Code Drift Day 1, and the topics are DP and Griddy. So let's get started. The first problem is turn on the bulbs. Now let's give it a read. There are A bulbs lined in a row numbered 1 to A, which are off initially. In one step, you can choose any bulb and turn it on. If you turn a particular bulb on, the bulb 2 places to the right and 2 places to the left of this bulb would also turn on. Bulbs that are already on will not be affected. Formally, if you turn on the bulb numbered x, it will also turn on the bulb numbered x minus 2 if it exists, and bulb number x plus 2 if it exists. Okay. Find the minimum number of steps required to turn on all the bulbs. And the problem constraints on A are, A can vary from 1 to 10 raised to power 9. Now with all this information, let's move on to solve some examples first. Now let us talk about these two examples. We are given A as 2. So we are given 2 bulbs, right? In case of 2 bulbs, let's say I turned on this bulb, then I can turn on a bulb which is at position, let's say this is at position 1, then I can turn a bulb which is at position 1 minus 2, or that is minus 1, but negative 1 is not a valid index in this case, right? Similarly, I can turn on a bulb which is at position 3, 1 plus 2, 3. Again, we don't have any bulb at third index, so I can just turn on this bulb. Then after that, I need to turn on another bulb which is at second position. So for a equal to 2, our answer will be 2. Now let us talk about a equal to 4. We'll have 4 bulbs, and we can solve it in this way. We can turn on this bulb, and we can turn on this bulb in one operation, and we can turn on this bulb, and we can turn on this bulb in one operation. So we'll have 2 operations here as well. So for a equal to 4, we need to return 2 as well. Okay. Now let us move on to see the solution to this problem. Now in order to solve this problem, we need to make some observations. Let's say we have certain amount of bulbs here. If I try to turn on this bulb, then I will also turn on this bulb and this bulb, right? Similarly, if I try to turn this bulb on, then I can turn this bulb on and this bulb on, right? So here we can clearly see that if we have 6 bulbs, we need exactly 2 operations to turn all of them on, right? So we can make batch of 6 bulbs and we can turn them on using 2 operations. Okay, so our solution will be, let's say we are given some A, then we'll try to make batches of 6. Okay, we'll try to make batches of 6 and we'll try to turn them on in 2 operations. After that, we'll have some remaining bulbs. So what can be the number of remaining bulbs? Remaining bulbs can be 0, can be 1, can be 2, can be 3, can be 4, can be 5, right? So these are all the values. We cannot have 6 remaining bulbs. Why? Because we can again make a batch of 6. Okay, so these are all the possible values we can have after we have made all the batches of 6. Now let's try to solve these examples on pen and paper. Now we can solve the problem for these values quite easily. So let's do that now. Let's say what will happen if our A is 0, then if we don't have any bulb remaining, then we have 0 here. If we have 1 bulb, then obviously I need 1 operation. If I have 2 bulbs, I have already discussed this, then again I'll need 2 operations here. So I'll have 2 here. If I have 3 bulbs, let's say these are our 3 bulbs, then I'll again need 2 operations here. Why so? Because if I'll turn this bulb on, then I need to turn this one as well. Then I need 1 more operation to turn this middle bulb on, right? So I'll need 2 operations here as well. In case of 4, let's talk about 4 now. 1, 2, 3, 4. I'll turn this bulb on and this bulb on. I'll turn this bulb on and this bulb on. So I'll need 2 operations here as well. Similarly, let us talk about 5 now. For 5, I'll have 5 bulbs. 1, 2, 3, 4, 5. And let's say I turn this bulb on, then I need to turn this one and this one. And after that, I need 1 more operation to turn these 2 bulbs on, right? So again, in case of 5, I need 2 operations. So here we can see that now I have list of all the values I need to return in case of 0, 1, 2, 3, 4, 5. Now that we have all the values that we need, now let us try to write a formula for this. So let's say we are given some A, then first I need to create all the batches of 6. Okay, so how many batches of 6 I can create out of A elements? So that will be A by 6, and this will be an integer division, right? For all these batches of 6, I can make 2 operations per batch. So I can multiply this with 2. Okay, after that I'll have some of the elements left, right? So in order to know the rest of the elements, I can just do A modulo 6. Okay, and the value of A modulo 6 can vary from 0 to 5, and we can take those values from this table. Either we can store all these values in an array, or we can make one observation. For 0 it is 0, for 1 it is 1, and apart from that, for any other value which is greater than 1, it is just 2, right? So what we can do here, we can return minimum of A mod 6 comma 2. Why so? Because if A mod 6 is 0, we need to return 0. If A mod 6 is 1, we need to return 1. And otherwise, whatever value we have here, A mod 6 can be 2, 3, 4, 5, then we need to return 2. Okay, so we just do minimum of A mod 6 comma 2. So this formula here is our final answer. Now let's move on to see the pseudocode of this problem. Now let us talk about the pseudocode, which is quite straightforward. Basically, we are creating the batches of 6, then we are multiplying it by 2 because a batch of 6 needs 2 operations. Then after that, we are returning minimum of a mod 6 comma 2. The second problem is yet another string operation problem. The problem description states that you are given two strings a and b of same length. In one operation, you can set some ax equal to bx. This will cost you 1 coin. Otherwise, you can also reverse a substring a from I to j at most once. Okay, so you can choose to reverse some substring of a given string, and you can do this operation at most one. Okay, so you can either do it or not do it, and this will cost us c coins. Now we need to find minimum operation required to make both string equal. Okay, the problem constraints are length of a and b are equal, and they can vary from 1 to 1000. A and b consist of lowercase alphabets only, and cost c can vary from 0 to length of a. Now let us move on to see some examples. Let us talk about these examples now. We need to convert this string to this string. So a b c e d a to b d e c b o. Here we can see that if I reverse this much of string, I'll just get this string. Okay, so I'm gonna reverse it, and the cost of reversing a string is 1. Okay, so I'll add 1 to the answer and I'll just reverse it. Now it will look like D E C B. Okay, so now the characters which remain unmatched are A and A. We need to convert this A to B, which will take again one operation, and we need to convert this A to O, which will again take one operation. For this example, our answer will be 3. Now if I talk about second example, I have two strings here again, and we can see that only the first character is different in both strings, so I just need one operation here. Okay, so in this case our answer is 1. Okay, now let us move on to see the solution to this problem. So basically we can see here that we need to convert this string to this string, right? The solution here is based on dynamic programming, so we can define states here. The states we can have are L, R, rotate. Here L will be the starting point of the string, R will be the ending point of the string, and rotate can take two values, 0 or 1. It will be 0 if we have not used the rotate operation right now, and it will be 1 if we have already used the rotate operation. Now currently my L will be here and my R will be here. Then what I can do, and let's say the index are 1, 2, 3, 4, 5, 6. Then my recursion will look like go from 1 to 6. I need to solve from 1 to 6, and currently our string is not rotated. Okay, so from this string I can come to this state, go 2 to 6 and not rotated. And how can I transition to this state? What I can do, I can check whether this character matches with our first character of string B, and if they match, then I'll add 0 to the answer, otherwise I'll add 1 to the answer. Okay, and then I'll recur for this relation. Apart from this, I can also check the last character of our current string with the last character of our string B, and if they are equal, then I'll add 0 to the answer, otherwise I'll add 1 to the answer, and I can recur for 1 comma 6 minus 1, that is 5 comma 0. Okay, we haven't rotated it. Now there's one more operation that I can do, that is I can reverse the whole string. In that case it will cost me c units, so I'll add c to the answer, plus I'll recur for the same string from 1 to 6, but this time it is in rotated form. So in the similar fashion, I can transition from one position to another position. Let's say I want to transition from this position, then I'll go to 2 plus 1 3 comma 6 comma 0, and I can also go to 2 comma 6 minus 1 5 comma 0. Okay, and apart from that, since it is 0, we can rotate it, right? If it is 1, then I'll cover that case, but if it's 0, I can just try to rotate it here, 2 comma 6 comma 1, and then after that we can rotate it, we can add c here, right? So that's how we can transition. But there is one special case, and that is what will happen after we have rotated the string. Okay, so let's cover that now. Let's say I'm using my rotate operation, then I'll add c to the answer, and I'll transition from 1 6 to 1 6 only, but this time I've rotated my string. Okay, now from this state, as we know that our string is rotated now, that means the substring from 1 to 6 is rotated. Okay, so whatever we have at first position, it should be in the last position in case of second string or string B. Similarly, whatever we have in the last position will be in the first position of string B, right? So from this place, our transition will be, if our first character is not equal to the last character, we'll add 1. And similarly, if our last character of string A is not equal to the first character of string B, I'll again add +1. And then I'll transition to 1 plus 1 2, 6 minus 1 5, comma 1. Okay, so that is the only transition that I can make. And if I try to write it properly, it will look like this. AL, if AL is not equal to BR plus, if AL is not equal to BR, this condition will be 1 and that will add 1 to the answer. Similarly, if AR is not equal to BL, or that is the last character of string A is not equal to the first character of string B, then again add 1 to the answer, plus go 2, 5, 1, right? So that's how we can solve this problem. Now that we have covered all the cases, let's try to generalize it. Now let's say our recursion looks like this. Go from L to R and this is root. Then we have two cases here. If ROT it's equal to 1, then we can perform only one transition, and that is we can return go from L plus 1 to R minus 1 with rotation intact, plus we'll try to compare the first character of our current string with the last character of our string that we need to convert it into. Similarly, we'll compare the last character of our first string with first character of the string B, right? So that's how we are going to solve it if we have already rotated the string. Otherwise, we'll have three cases. We can do go L plus 1 to R with 0, plus we'll compare the first character with the first character of string B, right? And I can do the same for last character as well. So what I'll do there, R minus 1 comma 0 plus I'll compare the last character of our string A with last character of our string B. And apart from these two, I can always reverse my string. So in that case, I'll just do go L to R, but this time I'll pass 1 here because I have already reversed my string. Okay, in this case I need to add C. So I can return the minimum of these three. We can return this. Apart from these things, we need to handle some base cases, like what will happen if L is greater than R or if L equal to R. And in this fashion we can solve this problem quite easily. After this, all we need to do is memorize the solution, and that will pass the time limits. Now let us talk about the pseudocode to this problem. So basically we are given two strings A and B and an integer C. Then I have this go function here which has three parameters L, R and rotated. So rotated here signifies whether we have reversed the string or not, and then LR signifies the same thing. L represents the first character, R represents the last character of the current substring we are watching. Okay, if L is greater than R, then it is an invalid interval, we need to return 0. Otherwise, if L equal to R, then we are going to return whether the current character of string A is equal to current character of B. If they are equal, then we need to return 0, otherwise we need to return 1. Okay, so this condition, just do that. After that, we have discussed this part here. If rotated is true, we can do just one transition, and that is we'll check the first character of our string with the last character of string B, and the last character of our string with the first character of string B, and then after that I'll do the transition to L plus 1 and R minus 1 with 1, right? Otherwise, I'll have three conditions. I can go to L plus 1, or I can go to R minus 1, or I can go to LR but with rotation as 1. Okay, you can see that here rotation is 0. That means that currently we haven't reversed our string, but here we are trying to reverse it, and since we are trying to reverse it, we are adding C to the answer. Okay, so after that I'm just returning the minimized answer that I'm getting out of all these conditions. And at this part, we are basically memorizing the solution. We are just trying to store the solution in this DP state, right? And at the end, I'm calling this function go, and it is returning me the optimal answer. So that's how we are solving this problem quite easily. So that's pretty much it for this video. Please like the video if you enjoyed the content. Do subscribe. Thank you for watching. Hey guys, in this video, we're going to talk about the problems of Code Drift Day 2, and the topics are DP and greedy. So let's get started. Let's talk about the first problem, maximum XOR with minimum x. The problem description is, given an integer a, select two integers x, y such that x and y can vary from 1 to a such that they have maximum possible XOR. If there are multiple x, y's, choose one with the smallest x. So basically we need to maximize the XOR of any two values, and those two values should be in range 1 to a. The problem constraints are a can vary from 1 to 2 into 10 raised to power 9. Okay. Now let's talk about some examples. Now let us talk about the solution. Let's say we are given any integer a and the number of bits in this integer is x. Then I claim the maximum XOR that we can get is 2 raised to power x minus 1. Or basically, this also means all ones x times. This is binary representation. Now, why do I claim so? Okay, so in order to understand this, let's see how actually the binary pattern works. I'm going to write some numbers in binary here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, right? So in this binary representation, you can see that number of bits here is 1, here it is 1, but here number of bits is 2, right? Now here we can see an increment in the number of bits, right? Similarly, if we look at this place, we have 1, 1, then we have 1, 0, 0. Again, we have increment of 1 in the number of bits. And similarly, at this place, I can see an increment of number of bits, right? Because here it is 3 and here it is 4. Now, whenever we see an increment in the number of bits, we can see that the lowest number with x bits, we can XOR it with the highest number of x minus 1 bits, and we'll get a number with all x bits set, right? So whenever I'll have a number of x bits, I know that I'll always have some number, like in this case a number with x minus 1 bits, which will fulfill our condition of XORing and maximizing the answer to this value. Similarly, here I can see that I have a number with x bits. Okay, we have 1, 0, 0. Then I am sure that my range from 1 to this number will also include 1, 1. Okay, so I can always make 1, 1, 1 out of it. That's why I said, given a number a who has number of bits equal to x, I can make this number. Okay, and that number is 2 raised to power x minus 1. Moving further, let us assume that 2 raised to power x minus 1 is k. Then we need to create k, right? So what we can do, our answer will be k minus a, comma a. Why so? Because we know that all the bits in k are set. So we have something like this. Okay, we have some structure which has all the bits as 1, and if I subtract a from it, and let's say we have something like this, then one thing that we can notice here is wherever we have 1 in our a, I'll get a 0 there, right? So this one is k and this one is a, and if I tend to subtract them, if I try to calculate this value here, so wherever I have 1 in a, I'll have 0 in my answer. Okay, and apart from that, I'll just have 1, right? Now this value is k minus a, and if I XOR it with a, which is 1, 1, 0, 0, 1, 1, right? So if I XOR it back with a, I'll get my answer as all ones. So that's why we can choose k minus a, comma a as our answer. But there are two base cases that we need to handle. The first one is If a equal to 1, we have just one possible choice, and that is 1 comma 1, and the XOR of these two values is 0, which is the maximum we can get. And apart from this, we have one more condition. Let's say our a is equal to k. Then in that case, k minus a will be 0, right? So we don't want that. Why? Because the range that we can operate in is from 1 to a. So we cannot use 0. So in that case, what I can do, I have one extra information here is that a also consists of all ones now. Why? Because k will also consist of all ones, and since a is equal to k, a will also consist of all ones. So in this case, what I can do, I'll just subtract it with 1. So if I'll subtract a with 1, I'll get 0 at last position. Right. Now if I try to XOR this value with 1, I'll get my answer. Right. I'll get my answer back as k. So in case of a equal to k, I'll return 1 comma a minus 1. So that will be my answer for this case. Now let us quickly see the code to this problem. We are given an integer a. If a equal to 1, we are returning 1 comma 1. That is one corner case. Otherwise, this x, it will contain the number of bits in our current number, or basically in a, right? After that we are calculating k is 2 raised to power x minus 1, and then we are checking if k equal to a, we are returning 1 comma a minus 1, otherwise we are returning k minus a comma a. So yeah, that's it. Now let us talk about the second problem. Valid parentheses again. So Robin bought a sequence consisting of these characters. A sequence is valid if it follows any one of the following rule. An empty sequence is valid. If x is valid sequence, then opening bracket plus x plus closing bracket of same kind, or similarly here as well, is also valid. If x and y are valid, then x plus y is also valid. Fine. His brother played with the sequence and misplaced some of the characters. Those misplaced characters are denoted by question mark in string A. In order to make the sequence valid again, he decided to replace the character question mark. The task is to determine the number of valid sequences that can be created by replacing question mark. Since the answer could be large, output answer modulo 10 raised to power 9 plus 7. The problem constraints are a can vary from 2 to 150, and length of string a is always even. Now let us move on to see some examples of this problem. Now let's say we are given this string and we need to count the number of valid sequences we can make out of this string, right? So I think we can do this like this. This is a valid sequence. Similarly, I can just change this outer bracket to something else. Let's take the big brackets. And similarly, I can change the outer braces to curly braces. Okay. So this also works. So apart from these three strings, we cannot have any other string. Why? Because we need an opening bracket for this one and we need a closing bracket for this one. And we cannot have the opening and closing bracket for these guys here. Because if I'll have an opening bracket here for this one, then I'll have one element left in between. Similarly here I'll have one element left in between. And we cannot pair up that element, right? So that's why we can have just three kind of strings here. So in this case our answer will be 3, right? So that's how we need to solve this problem. Now let us move on to see the solution of this problem. Now let's say we are again given the same string, and this time we need to create an algorithm to solve this problem. So let's start with brute force. So what I'm thinking to do here is, I'll say that this is my left pointer and this is my right pointer, and I'll assume that my left pointer is an opening bracket. Okay. Then after that I'll iterate on this string from L plus 1 to R, and I'll try to brute force each and every position for the closing bracket of my current position L. Okay, so in this manner eventually I'll reach at some base case, and if that is a valid sequence, then I'm gonna add 1 to the answer, right? So that's how I'm thinking to solve it. So let's try to solve it recursively. Okay, so let's say this is currently our string. Then what are the choices we can make? So for this guy as an opening bracket, I can have this guy as closing bracket. Yes. And since both of them are question marks, if this question mark is this, we can have this here. This question mark is this, we can have this here. This question mark is this, we can have this here. So this question mark can take 3 values. Okay, so we can have this as opening and this as closing bracket in 3 ways, right? So in case of a pair of question marks, what we can do, we can just recurse for the rest of the string, and we'll just fix this string that these two guys are done here. Okay, so let's say I am recurring for the rest of the string. What is rest of the string? That is this much, question mark, and since these two can take 3 values, so whatever I'll get answer from this recursion, I'll just multiply it by 3. Okay, because I can do that 3 times, right? Now again, let's try to say that this is my ending bracket. Okay, now in this case our ending bracket is not a question mark, it is a curly bracket, right? So that defines our starting bracket as well. Okay, so our starting bracket cannot be any other bracket but a curly brace. So in this case I'm not gonna multiply with 3 like I did here, because in this case I have just one possibility, right? So if I assume that this is my opening bracket and this is my closing bracket, then I need to solve the sub problem of this string and this string. Then I need to solve question mark. So these two strings, I need to solve these two strings separately, right? And similarly, let's say now I take this as my closing bracket, but in this case I can see that this is already not a question mark and it is an opening bracket, so it cannot be a closing bracket, so I cannot choose this position, so I'll just move on. So I'll move on to this position. So again it's a question mark, so I can choose it, and I can choose it in 3 ways because we have a pair of question marks here. So I'll choose it in 3 ways. I can multiply it by 3, whatever I'll get the answer from here. Now what are the strings that I need to solve independently here? It is question mark, curly and parenthesis, and one question mark. So these are the strings that I need to solve independently, right? Let's move on to this value. Now for this value, again we have a question mark, so we can see that we'll have 3 choices. And what are the strings that I need to solve it for? We have just one string, that is question mark, closing curly brace, opening parenthesis, and a question mark. So that is my sub problem here, right? Now here you can see that this is a string of length 1, so it cannot make a pair. So this is a base case. So we can conclude here that this string is not going to get converted to a valid string. Okay, so we can return from here. Here we have a string of length 1, so we cannot create a pair out of a string of length 1. It must be even at each and every position, right? So again I cannot do it here as well. Now I have only 2 choices left, this one and this one. Okay, and both of them consist of just one string of even length. Okay, so let me remove the choices which are not valid. Now we have these 2 choices, right? So again we can do the same. So let's iterate on this string. I'll fix my first character of this string, okay, and I'll assume that this is an opening bracket, but in this case as we can see that this is not an opening bracket, so this choice is again invalid. Okay, so since it is a closing bracket and we cannot find a pair of this bracket, so we can just return 0 from here, and 3 multiply 0 will be 0. Okay, so this is again invalid. Now let us move on to the second problem we have. So here let's fix this character as the first character of our current substring, or the character which will possess opening brackets, right? After that I'll iterate for the closing bracket. So let's say I'm currently here and I assume that this is my closing bracket. Then in this case, since the closing bracket is not a question mark, I can only do this in one way. So if I choose this as my closing bracket, the sub problem that I'm gonna get is parenthesis and question mark, right? Because these two are selected. Now let's say I choose this as my closing bracket. Now since it is an opening bracket, I cannot do that, right? Because it will be an invalid choice. So I cannot choose this. Now let's try to choose this as my closing bracket. Now again, here we have two question marks, so I can put three kind of values there, right? So my sub problem will have some strings. In this case, I'll have just one string, and that is this one, and we can get the answer in three ways. Now after this, we can see that this pair is invalid, right? Because it starts with a closing bracket. So we can again return 0 from this position. So we'll return 0 from here. So 3 into 0 is 0. Now we have one substring left here. Okay. So for this substring, I'll choose this as my starting bracket. Okay. Opening bracket. Then I have this choice as my closing bracket. And since this closing bracket is a question mark, but here our opening bracket is not a question mark, right? It's a fixed bracket. So my closing bracket can be made by just one choice. So what I'll do here, I'll multiply by 1 and I'll say that this is my closing bracket. So the string that I'm gonna get is an empty string of length 0. So in case we got an empty string, that means that we have already paired up all of our brackets, right? So in this case, I will return 1 from here. I'll say that this is a valid choice. Now 1 multiplied with 1, it is 1. Then this 1 will propagate further to here 1. Now I'll multiply this 1 with this 3. So I'll return 3 from this position. Okay, so I'll get 3 from this string. And rest of the values are returning zeros. So that means the number of valid strings for this string is 3. Okay, so that's how we can solve this problem recursively. So basically we can optimize this recursion using memorization. And now we can move on to see the pseudocode of this problem. That will definitely help us understand the recursion better. Okay, now let us look at the code of this problem. So this is our solve function. We are given the string and then we are passing it to a recursive function go, and here 0 is L and n minus 1 is R. Okay, so we are solving it. So now let's look at the go function here. This is L, this is R, right? Now if I is greater than j, we are returning 1. So when I is greater than j, then we are encountering an empty string, right? So as we have already discussed, in case of empty string, we are technically claiming that we have already paired up each and every bracket, right? So we can return 1. And if I equal to j, then currently we have one character left. And since we have one character left, we cannot pair it up. We need at least 2 characters to make a pair. So in that case, I'll return 0. Otherwise, I have this answer variable and I'm memorizing it using this dp table. After that, I'm checking if our vi is not an opening bracket or a question mark. I'll return 0. Because if my string starts with a closing bracket, I cannot pair up with an opening bracket, right? So in that case, we'll return 0. Otherwise, we'll iterate from I plus 1 till j. And for each element, if vi equal to question mark and vid is equal to question mark, so here vi is the opening bracket and vid is the element we are trying to consider as our closing bracket right now. Okay, if both of these are question mark, then we can solve the sub problem in 3 ways, right? That's why I'm multiplying by 3 here. And then I am recurring from I plus 1 till id minus 1 and id plus 1 till j. So let's say this is the string question mark dot 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 question mark dot dot dot. Then this is our first character I and this is our sub character id, which I have considered as our closing bracket. If I consider this as a pair, then I need to recur for I plus 1 and id minus 1, that is this string, and id plus 1 till j, and that is this string. So I need to recur for these 2 strings, right? So that's why I'm recurring for these 2 strings and I'm multiplying the number of ways in which we can solve these 2 subproblems, right? After that, I'm multiplying it by 3 because we can solve our current subproblem in 3 ways because we have 2 question marks, right? Now if we don't have a question mark, we'll have a closing bracket which we can use. So in case of a closing bracket, we can recur for I plus 1 and id minus 1 and id plus 1 and j, and we won't get 3 ways here because I know our closing bracket is something, okay, some character. So our opening bracket should be that same character only. That's why we are not multiplying by 3 here, right? If my vi is equal to question mark, then we have covered the cases. And if my vi is some opening bracket, in that case, I need to check again, right? So here our BID or our closing bracket can either be a question mark, or it can be a reverse of our current bracket, right? Since we know that our VI is not a question mark, that means our VI is some character. So here's the reverse function that actually returns us the reverse of current bracket. Okay, for this the reverse is this, for this the reverse is this, for this the reverse is this. Otherwise it will return an invalid sign. So that means if this is the case, then I am recurring from I plus 1 to ID minus 1 and ID plus 1 to j, and I am adding that up to the answer. After that I am returning my answer. So that's how we can solve this problem. So that's pretty much it for this video. Please like, share and subscribe. Thank you for watching.
Okay, so today we are going to study a very important data structure. This is going to be very handy, which can reduce the time complexities of many problems significantly just by adding a little bit on the space side. Okay, and this is called a hash map or a hash table. Okay, and the whole process is called hashing. In today's class, we are going to study some basics of hashing, how a hash table functions, and we'll also discuss some problems which have been asked in the interviews, and we'll see how you can solve these problems optimally using a hash map or hash table. Okay, I have a question for you guys. Have you ever encountered hashing in your real life? Hashing, have you ever faced any practical scenario where you have used hashing? Let's talk about those days when there was no corona, or let's call it the pre-COVID era. Let's talk about the pre-COVID era. So during the pre-COVID era, we used to go out on holidays, right? We used to go for trekking. We used to go to visit different places, right? And whenever you go to a different place, you need to stay in a hotel, right? So let's say that if you go to a hotel and if you want to look for a room, right? You go to the receptionist and ask whether a room is free or not. Now the job of the receptionist is that he will take all your preferences. He will ask you what type of room you want. And then based on your preferences, he will just check whether a room of those preferences is free or not, right? So you go to a hotel, and in this hotel, you have a receptionist, right? And you go to the receptionist and you ask for a room. Give me a room which, let's say, is a single bedded room, has a AC, has a balcony and all, right? And this guy will just check whether a room is free or not. Now, this guy has got two ways to check the room. First is that he can actually go and he can visit all the rooms of the hotel and check whether such a room is present or not, right? He will go, he will knock each and every door. He will check whether the door is closed or whether the door is open, whether the key is with him or whether the key is with the person who has taken the room, right? So this is one way. Now, as all of you can see that this is a very unoptimized way of finding a room, right? Because if there are, let's say 200 rooms in this hotel, if this is a very big hotel, then he is going to check each and every room for each and every customer, right? So if there are n customers and if there are m rooms, then how many checks is he going to make? This unoptimized receptionist is going to make n into m checks. This is not going to be profitable for the hotel business. Whoever is the owner of the hotel, he will fire him the next day, right? The other way that this guy can use is he can maintain a map, right? He can just against each and every room, right? Let's say room number 101, 102. He can maintain whether this room is occupied or whether this room is empty, right? Or he can also have the keys in the key holder itself. He can also have the room number written, right? So now whether he has the key or not, that is also visible here. Whether the room is empty or not, that is also visible here. He can also have the type of the room written here. So he can have that 101 is a single bedroom, which is empty. 102 is a single bedroom, which is non-empty. Let's say 202 is a double bedroom, which is empty, right? So he can have each and every information regarding the room stored against the room number. Okay, is this going to be a better choice? Yes, right? That is why each and every receptionist actually does this. You must not have seen any receptionist who actually go and check all the rooms, right? But this is something which you all must have seen, correct? Let's talk about another example. Okay, so let's say that in those days we also used to go to shopping malls, right? So this was an example when we want to stay on a hotel. Another example would be that if I want to go to a shopping mall. Okay, now if I want to go to a specific shop in the shopping mall, again there are two ways, that either I go and check each and every shop in that mall, right? So there are going to be multiple floors in that mall, right? Each floor will have different shops, right? And let's say I'm looking for a specific shop. Okay, let's say I want to buy the magical drug Coronil. Okay, I have a perception, I have read on WhatsApp that if I take Coronil, then Corona is not going to catch me, right? So what I would want is, I would want to search this shop which is selling this drug Coronil, right? Now again, I have got two ways to do this. First is that I go to each and every floor and I check each and every shop one by one, right? Or some of the malls who have a logical owner or who have a logical management, what they do is they put a board or a map of the mall, right? So what they do is they put shop number, they give the complete address of the shop, floor wise. They will say that in the first floor, these are the shops which are there in this order, right? And in the second floor, these are the shops. So what I can do is I can use this map and I can find the exact location of that shop, and then I can go to that shop, buy this drug, and then I can make sure that Corona is not affecting me. But since this was a knowledge that I gained from WhatsApp, this might not be true, right? But this way of searching the shop, this definitely is a better approach, right? Instead of visiting each and every shop, what I'm going to do is I'm going to check this map and then find the exact location of the shop. Okay, does this make sense to everyone? These are two examples which all of you must have used, like these or something like this in your real life, right? Where you have to keep track of things and you just create a table or you create some entries and you just mark true, false, or you just the attendance register that we have, that we used to have in our school classes, right? That was also an example of hashing. If, let's say, a teacher wants to know whether a student is present in the class or not, right, what he will do is he will just do a linear scan on all the students. And doing this linear scan while taking the attendance, he also marks the attendance, right? So if there are students, let's say in our class, we have Aman, then we have Monica, then we have Anmol, right? So if I have to check whether all of these guys are present in the class or not, what I can do is just before beginning the class, I can just mark their attendance, right? Now, if let's say after some time I want to know who all were present in the class, I will not do another scan. I will just check whether Monica is present, whether Aman was present or not, right? So this again is another example of hashing which we have been seeing from the school days, right? Okay. Is Oyo also used concept of hashing? Yes, Oyo must also have used this same concept, right? Okay, so this is the general idea of hashing. Now let us see how it actually functions in the world of computer science. Okay, so let's try to understand this whole process using an example. So let's say that we are given an array, and this is just to understand how hashing is going to function. Okay, this is going to be a very easy example to understand the working of hash maps and hash tables. Okay, so let's say that you are given an array. And in this array, you have all the numbers from range 1 to 1000. So you know that any number in this array is going to be from, or let's say from 0 to 1000. Okay. So you're given an array of size n, and each and every number of this array ranges from 0 to 1000. Okay. You have to return the frequency of every number. Let's say you have got queries about the numbers. Okay, so you have this array and now you are getting multiple queries. You have to answer these queries, and each query asks you the frequency of a number. Okay, so for example, if the array is something like this, okay, if this is the array, after getting this array, you will get different multiple queries, and you have to answer what is the frequency of the given number in that query. So for example, if your query has 58, you will return 1 because 58 occurs only single time. Then if let's say you get 3 in the query, then you will be returning 2 because 3 is occurring twice in this array. If you get 2, you will again be returning 2 because 2 again occurs twice in the array. Okay, is this scenario, is the problem clear? How can we solve each and every query in the most optimal time? Okay, let us start from the brute force. Okay, what is the brute force way to solve each and every query? The brute force way to solve each and every query is that whenever you get a number in the query, you iterate over this complete array and you count the occurrences of that number, right? So if I get 58, I will do an iteration over the complete array, which is going to be an order n operation, and then I will return 1. If I get 3, I will again do another order n operation over the complete array, and I will return 2. Okay. So what is the total time complexity of, if I go by this approach? Let's say there are q queries. Solving each query takes order n time. So the total time complexity is going to be q into n. Right? Now this q can be very, very large. Okay. So this is something which is not optimal, right? Any other approach that we can use in this case that you might have studied in the previous classes? Can we optimize this order n factor here? Let us say if I do some pre-processing, okay? If I sort the array, what happens to the order? Now the order is, the array sorted in ascending order, right? Now can I find the frequency in a more optimal time? Can I reduce this factor of n? Yes. Now how can we count the frequencies? Now we can use binary search. You must have studied this, you must have learned it in the previous sessions, that given a sorted array, you can count the number of occurrences of any element using binary search, right? You can just find what is the first occurrence of that number using the binary search. Then you can also find what is the last occurrence of the number, and then you can get the length of this subarray, right? So if you use binary search after sorting, then each and every query is going to take how much time? Only log n time, right? So now what is the total time complexity of finding all the frequencies? So if you have q queries, then solving all the queries is going to take you q into log base 2 n time. This much is the time that you will invest in resolving each and every query. But before this, you have also sorted the array, right? So that amount will also be counted. Now, whichever is the greater of these two will be the overall time complexity, right? This still is a lot because again, n can be very large, q can also be very large, right? So can we further optimize this, right? So as many of you have already suggested, what if I have another array, right? So I can see here, if I focus on the constraint of the problem says that any array value is going to be in this range strictly, right? Any array value cannot be more than 1000 and it cannot be less than 0, right? What if I just have another array where each and every index of the array represent the numbers and the value in the array represents the frequency of a number in this original array? So what if I have another array, just call it a frequency array, right? And store and count the frequency of each and every original array element in this array, right? So I can have another, let's say, frequency array of size. What should be the size of this array? What should be the optimal size of my frequency array? If I know that all the numbers are going to be in the range from 0 to 1000, I know that the maximum number that I can have is 1000. To have 1000 as an index, I need an array of size 1001, right? 1001. This array is going to be, this array can accommodate all the numbers from 0 to 1000 in index, right? So now what I will do is, whenever I am iterating over this array, so initially I initialize this complete 1000 sized array by 0. So in this array, initially I have 1000 zeros in every index, right? And then whenever I visit a number, I will just loop over this array. And whenever I visit a number, I will increase the value here, right? Because this denotes the frequency. So initially I am assuming that frequency of each and every number is 0. Whenever I encounter a number, I will increase the frequency, right? So I will just loop over this array. I will say for I equals to 0, I less than n, which is the size of the given array, I plus plus. And I will say frequency of a of I plus plus, right? If I just do this, what will I get? In this array, frequency of 1 will be increased to 1, right? And then frequency of 2 will also be increased and it will be 2. Frequency of 3 will also be 2, and so on, right? So now, after I have built this array, if I have to return what is the frequency of any given number, right? What is the operation that I have to do? After I have built this array, for any number I, for any given number I, if I have to return what is the frequency, frequency is nothing but frequency of I. So if I have to return what is the frequency of 58, I will quickly do frequency 58. If I have to return what is the frequency of 2, that is going to be frequency of 2. And that's it, right? So what is the time complexity of this operation? Time complexity of this operation is constant, right? This is a constant time operation. I'm just retrieving a value from the array, right? So this is going to take order 1 time, correct? Now I have q queries, and each query is being solved in order 1 time, correct? So what is the overall time complexity of solving all these queries? Overall time complexity becomes order q, because each and every query is taking how much time? Only order 1 time, right? So this is the time to resolve each and every query. And then we have also built this array, right? So we have iterated over the given original array, and then we have also built that array. So this takes order n time. Order n plus q, whichever is greater will be the final time complexity. Okay. Does this make sense to everyone? How we have solved this, like optimize the time complexity from n square to n log n plus q log n to order n plus q. Okay. Now, one of you just asked what happens when array elements range from 1 to 1 raised to power 10 raised to power 18. Okay. What if, so in this problem, it was given to us that the numbers are going to range from 0 to 1000. That is the reason why we are able to create an array, right? I can create an array because I know that indexes can be in this range, correct? Now, what if the numbers are going to be very large? Okay, a of I as asked by Lucky Movies. What if the range is this? Can I use the exact same approach? So now I cannot use the exact same technique because I cannot have an array. I cannot create a frequency array which has a size 10 raised to power 18, right? Because this is going to cost me a lot of memory, right? How much memory is it going to cost? If this is an array of integers, one integer takes how much memory? 4 bytes, right? So if you want to create an array of size 10 raised to power 18, this is going to cost how much time? How much memory? 4 into 10 raised to power 18 bytes. Can anyone quickly tell me how much is this in GBs? 4 into 10 raised to power 18 bytes. How much is it in GBs? So if you want to create an array of that size, you need to have this much of memory. You need to have this much of memory in the RAM, right? So this much of memory in the RAM is definitely not going to be possible for an ordinary computer, right? So what we are going to do is, now we'll have to be a little more logical and we'll have to apply a little more mind, right? Unlike Mumbai police. So let us be a little more logical and let us try to see if we have an upper limit on the memory, right? If let's say, let us take a smaller example, and let's say that the numbers are ranging from, just to understand, let's take the smaller example that the numbers are again ranging from 1 to 1000, but the largest array that I can have a size of 100. This is the upper limit on the size of array. Okay, similar example. So what we are doing is numbers are ranging from this 1 to 1000, but the maximum size of the array can only be 100. All right. Now again, I cannot use the exact same method. Why? Because having an array of size 1000 is not possible, right? So if I want to store the numbers as an index in the array, then I can only store till 100. Is there a way using which I can map all these numbers from in this range from 0 to 99? Because the maximum size that I can have is 100. So can I map all these numbers in this range? Is there a way? Have we seen any way? Or let's say that all these numbers are ranging from 0 to 1000, right? Yes, what can we do? We can simply take modulo, right? Is everyone familiar about what is a modulo operator? This gives you the remainder, right? So if I take modulo of any number ai with 100, which is the maximum size of the array that I can have, can I say that this number, which is ai modulo 100, will always lie in the range from 0 to 99? Can I say this? Yes, correct. So I have got one way to map these numbers which are in this range from 0 to 1000 to a range which is very, very small, right? This range has a length 1000, 1001, and now the resulting length is only 100. So I am mapping these 1000 numbers to 100 numbers. Okay. If this is the case, how am I going to store the numbers? Let's have an example. Let's say I have 492, 5, 8, 23, 15, 142, and some random numbers. Okay. And now if I can only afford an array of size 100, right? How can I map these numbers? I will first take the modulo of these numbers with 100. And then whatever number I get by doing this operation, I will store these numbers in that index. So I get the index by taking modulo of these numbers by 100. So first number will be stored against index 92. This will be stored against index 5. This will be against 23, 15, 42, 54, and 64, right? So if I have these as the array index, 54 and so on till 99, then at 0 is going to be empty, 1 is empty, 2 is empty. At 5 I am going to have 5. At 23 I will be having 823. At 42 I will be having 142, and then 6, 54, 764, and so on, right? So now, is this going to work? Is this going to work correctly? If these are the indices and I keep the values in array element mod 100 index. Okay, now some of you are saying that this is going to work, but there can be collisions, right? What are collisions? Okay, so let us say that in the array, in the original array, I have these numbers 100, 201, then I have 302, then maybe 300, 401, 200, right? If I have these numbers, right? So in which index should a number belong? In index 0, how many numbers am I going to have? In index 0, I am going to have 100. Then I am also going to have 300, and I am also going to have 200, right? All these numbers will try to get inserted against a single index, right? These are called collisions when there are multiple prospects candidates for a single index, right? So index 1 will try to accommodate 201, then 401. Index 2 is going to have 302, and then 2 also, right? So there is no one-to-one mapping, right? A one-to-one mapping does not exist, correct? If a one-to-one mapping does not exist, is this even possible to use this technique? Are we going in the wrong direction? Is this a correct way? Is this the correct path that we are taking? Maybe, right? We have also studied a data structure called linked list, right? If you know about a linked list, what if we have an array of linked lists? If I keep an array of the linked list nodes, right? Can I say that this can work in that case, right? So currently, if you are only storing a single element, if you are only trying to store a single element against one index, then since there is no 1:1 mapping, this will definitely fail. We are going to lose some data, right? Because every time you have a collision, the previous number will be overwritten. But what if I use a linked list? So instead of having these integers, right, if at index 0 I have this complete linked list stored. So if I have to create an array of linked list, what do I need? I only need the pointer to the head stored in that correct index, right? Only if I have an array like this where I have this head pointer, then using this head pointer we can have the complete linked list, right? So we don't need to actually store this complete linked list in the array. We only need to store the head pointer, right? Similarly, at index 1, we can have the head pointer of 201. At index 2, we can have the head pointer to 302. Does this make sense to everyone? So we can still manage doing hashing in this case. Even though the range which we have to store is very large, the size of the array is very small, but we are making sure using the modulus operation that we are mapping these numbers to the available size. And then using a linked list, we can also make sure that we are not losing out any data, and we are storing all these numbers using the chaining. Okay. Now, if I'm storing the values like this, now if I have to find what is the number of frequency, or let us say if I just want to check whether a number is present or not, right? What is the worst case time complexity of this case? If I'm going by this approach, if I'm storing linked list, if I'm having an array of linked list nodes, what is the worst case time complexity of finding whether a number is present in the array or not? Worst case is going to be if all the numbers are mapping to a single index, right? So if let us say that the numbers are these 1, then you have 401, then you have 101, then you have 601, right, 701 and 501, correct? If I take mod of all these numbers with 100, all of them are going to take the exact same key. So all of them are going to map against 1. So what will happen now? If I have to search whether a specific number is present in this array or not, I will be traversing this complete linked list, right? So first, let us say I get a query. I get a query of, let's say, 801. I have to check whether this number is present or not. So first of all, I will try to see in which index is this number is stored. So I will just do 801 mod 100, which is going to be 1. So I go to index 1 of my array. And now I have a linked list of size n. I will iterate over this linked list, and since this is also not in sorted order, right, I will have to check each and every element, and I will then figure out whether I have 801 or not, right? So this is going to be a order and time complexity operation. Does this make sense to everyone? This is the worst case time complexity of checking whether the number is present in this list or not, right? Okay, so this is the worst case. What could have been an ideal case? When can I say that this is the best thing that I want? What is the ideal case in this scenario? The ideal case would be that if all the numbers are mapping to different index, if all the numbers, if I have a data and like if I have the data in such a way that all the numbers are distributed evenly amongst all the index, right? So if I, let's say, have 401 against 1, then I have 2. So let's say I have 702, and then I have 23. So I have 823, and I have exactly one element for each and every index. This is going to be the ideal case. And what is going to be the time complexity in this case of just finding whether a number is present or not? Since the list size in each and every case is exactly 1, the time complexity is going to be constant, right? So this is the best case time complexity, and this is the worst case time complexity. Is everyone clear about these two? Okay, great. So the aim is that the mapping function that we are using, right? Currently the mapping function is mod by the size of the array, right? So the aim should be that whichever mapping function we are using should try to evenly distribute the load amongst all the possible indices, right? So this function, the mapping function that we are using, this is called, what is it called? Anyone knows what is the name of this function? This is called the hash function. Okay, and hash function is a very, very big topic in itself. There is a lot of research going on. There has been a lot of research already done on what could be a better hash function or for what case, right? So you can just go and Google up and read about hash functions. There are multiple publications on these. You can read, you can go through some of the publications if you are interested, right? But taking a mod, this is the most simple hash function that you can have, but not the most optimal. Right? This was just for the example. You have very complex, very optimally written hash functions which try to distribute the load evenly. Okay, so you can just go back and read about what are hash functions, and you can also read about some of the common hash functions. Okay, cool. Now, if I write one of the best hash function, even which is the best possible hash function currently present in this world, can I say that that hash function will guarantee zero collision? Can there be any hash function which can guarantee zero collisions? No. Why? Why no? You have got a very big range of numbers, right? You have to map numbers from, let's say, 0 to 1000. You have got only 100 slots. Do you guys, are you aware about the pigeonhole principle? You have 100 slots and you have to put 1000 things. When you put the first 100 things, and if your hash function is guaranteeing zero collision, 100 slots are filled, right? Now when you pick the 101 index number, this is definitely going to collide with at least one of the pre-existing slots, right? So since you are mapping a bigger list of numbers to a smaller list, you will always have collision. So there cannot be any hash function which can guarantee zero collisions. Okay. However, there are hash functions which try to distribute the load evenly. That is possible. There has been a lot of research done on that. You can Google and read. Okay. Cool. So this is the basics of hashing, right? You can read about hash functions. You can also read about hash tables. Hash table is nothing but key and value, right? So you must have seen what is a dictionary. If you use Python, you must have used hash maps. So hash maps or hash tables, they are nothing but a key value pair. This key is the result that you get from the hash function. This is a hash code of any value, and in the value you can store anything, right? So the key, as you all now should understand, these keys in this case are the index from 0 to 100, right? So keys are always and always going to be unique. Values can repeat. You can store the values in list or maybe in some other data structure, but keys are always going to be unique. Okay. Now there was a question that if you are using a list, is there any specific reason of using a list, or can we have any other data structure here? What do you guys think? Can we have any other data structure in place of list? So Surit is asking why we use linked list. Is there any specific criteria? Correct. So Komal has got a good solution to that. If I'm using a list, what is the worst case time complexity of searching a list in if you have a list which is not sorted and which is a linear linked list, what is the worst case time complexity of searching in this list? Worst case time complexity of searching in list is order n. Okay. Now, do we know any data structure which provides a better searching time complexity? Is there any data structure which can store the numbers maybe in some order and then can give us a better time complexity? Do you guys know about binary search trees? In a binary search tree, all the values on the left subtree are going to be less than or equal to the value of the root. All the values of the right subtree are going to be greater than the value of the root, right? So just by using a technique like binary search, it can always discard, while searching for a number, it can always discard half of the search space, right? So what is going to be the time complexity to search a number? It's going to be log base 2n. if you are using Java 8, if anyone of you who is using Java 8 must know this, that in Java 8, they optimize this worst case time complexity of retrieving from a hash map using a balanced binary search tree. In a normal binary search tree, in worst case, you can also have a time complexity of n if the tree is skewed. But if the tree is always balanced, then you are always going to have a searching time complexity of log base 2n. So in Java 8, what the hash map does it, if the size of the list is till a threshold number, which I don't remember correctly, I guess it's 5 or 6, till then it maintains a list. If the size exceeds the threshold value, then it converts the list to a balanced binary search tree. So the worst case time complexity that we have seen to be order n will reduce to order log n. Okay, cool. So guys, this is in brief about hash maps and how they work. Okay, let us quickly solve a problem also. Okay, in which type of questions can we blindly use hash functions? Okay, in any question where it talks about the frequency or counting the numbers or maybe checking whether a number is present or not, or checking the presence of anything, then you can use hash function, or then you can use hashing. Okay, let's quickly solve a problem and then you will get a better idea of when to use hashing. Okay, so the problem says that you are given an array and you have to check whether there exists a subarray which has sum equals to 0. Okay, so for example, if your array is this, in this case, does there exist such a subarray? Yes, right? If you see the sum of this subarray, what is the sum of this subarray? It is exactly 0. So you can return true. If there exists a subarray which has a sum equal to 0, the subarray can start from any index, it can end at any index, it can have any length which is possible. But if there exists any type of subarray which has sum equals to 0, then you can return true, else false. Okay, modify cadence algorithm. Okay, how will you do that? Remember that the subarray can start from any point. This subarray is starting from this point. There might be an input where your subarray which is causing a 0 sum can be present, let's say here, or the subarray can be present here, or maybe the complete array can also be the subarray. What is the brute force way? If you are not getting any solution, can you quickly write down what is the brute force way? Okay, the brute force way is going to be that you actually try to calculate the sum of each and every possible subarray, right? So you first check all the subarrays of size 1, then you can check all the subarrays of size 2, then you can check all the subarrays of size 3, and so on, right? How many subarrays are possible? N square subarrays are possible. To calculate the sum, what is going to be the time complexity? For every subarray, you will also run another loop to calculate the sum. So it's going to be an n cubed solution, right? Which is highly unoptimized. How can we come up with an optimized approach? And we have also studied hashing. Hashing doesn't seem to contribute in this question, right? Okay, let us assume that there exists a subarray. Okay, there exists a subarray which has got sum equals to 0. Okay, so let us say this is the initial array that we have, and there is a subarray, let's say this part, which has a sum equals to 0. How do we define a subarray? We always define a subarray using a range of indices, right? Because as I said, the subarray can start at any point, it can end at any point, right? Let us say it starts at a point L and ends at an index R. And I'm saying that we are just assuming that the sum of this subarray starting from L to R is 0. Okay. Now, if this subarray has got sum equals to 0, right? If I also have the sum of all the subarrays starting from 0 stored with me, okay, what can we say about this part? This part which is in the blue dotted line. What is going to be the sum of this part? The sum of this part is nothing but sum from 0 to R. right? And this sum from 0 to r can be broken down as sum from the range 0 to L minus 1, right? Plus sum of the range from L to R. Does this make sense to everyone? Right? So sum of any subarray can actually be written in terms of this prefix sum, right? I can write sum from L to R is equal to sum from 0 to R minus sum from 0 to L minus 1 index. I can write the sum of any subarray which starts at index L, ends at index R in the form of the sum of subarray starting from 0, which is nothing but the prefix sum. Everyone here understands what is a prefix sum, right? So if I have a prefix sum array P, then I can say that the sum of the subarray starting from and ending at R is nothing but P of R minus P of L minus 1. Does this make sense to everyone? Prefix sum is nothing but, prefix sum is the sum of all the indices till that index. So if I have an array, right, prefix sum at any index I is nothing but, it is the sum of all the elements including the ith and all the elements before the ith. Okay. So if let's say I have an array 1, 2, 3, 4, the prefix sum array would be 1, and then this will store the sum of these 2, is 3, then this will store the sum of all of them, which is 6, and then this will store the sum of all of them, which is 10. So this is the prefix sum array for this array. If I have all these numbers stored with me already in this array prefix, now I can represent the sum of any subarray in the form of prefix sums, right? And if I'm saying that this sum is equal to 0, if this sum is equal to 0, can I make any comment about these two values? If this sum is equal to 0, this means that prefix sum of R should definitely be equal to prefix sum of L minus 1, right? Let us visualize this in this diagram and then it will be more clear. So I have these two parts, right? Now I am saying that this blue box represent the prefix sum of R. This is the sum of all these elements from 0 to R. Okay. This yellow box, this represents the sum of all the numbers in the range L to R. Correct. And what about this green box? This green shaded box represents the prefix sum of the index L minus 1, the sum of all these numbers. Can I say that if this is going to be 0, right? If I'm adding the sum of all the index from left to right, and if this part is equal to 0, then whatever sum I get at this point, the exact same sum will also be present after this, because the contribution of this is 0. Does this make sense to everyone? Right? So if I have an array, right, and if I'm just calculating the sum of all the array elements till that index, and then there is a part which is contributing exactly 0 amount, right? So this will give some sum, right? Let's say S, this gives S dash, and then if I add this as well, this gives S double dash, this gives S triple dash, and then this gives something. After I'm here, I will again get S triple dash, because the overall sum of this part is 0. Does this make sense to everyone? Let us take the example as well, and then this will be crystal clear. So I will just copy this thing. So if I just calculate the prefix sum of this array, I will be getting 4, right? 6 minus 3 again is 3, then 4, and then 10. Okay. Now what I was explaining is, since the sum of this part is exactly 0, this part, the contribution of this part in the sum of all these numbers is going to remain 0, right? That is why whatever number I am getting here will also be repeated here, right? So whatever sum I am getting at this point, which is, this point is L minus 1, right? Because I am assuming that this subarray starts from L. So the previous is L minus 1, and this is the R. these two have to be equal. If these two are equal, this means that this subarray, the contribution of this subarray was exactly 0. All the values cancelled out each other, and we are remaining with whatever we had before starting this subarray, right? So how can we now solve this problem? If we calculate the prefix sum of the array, and then if we observe that there is a number repeating in the prefix sum, can I say that the contribution of all the elements between these two numbers is going to be 0, which means that this subarray is adding to 0. Okay, is the idea clear to everyone, guys? Is the idea clear? Right, let's take another example. Let's say I have 4 2 0 1 6. Okay, now if I take the prefix sums, I will be getting 4 6, then again 6, and then 7 and 12. So again I can see that a number is repeating in the prefix sum, which means that whatever comes in between these two, this is, if I said that first number should be L minus 1, this is L minus 1, right? And this number is R. So whatever is from L to R is going to give me a sum equal to 0. L to R here has exactly one element, which is 0. Now one of you asked, what if same number is repeating twice, right? That can also be possible. You will have to understand what is the physical significance of this thing, right? So even in this case, if I just modify this array, here I got 4, then I have 0, then let's say again 0, then I get 2, and then minus 2, and then something, right? Now what will be the prefix sum here? Again 4, 4, 6, again 4, and then 5, right? So this means that all these numbers which are repeating, they all are forming a subarray which is going to give a 0 sum. If these two are repeating, this means that we have a sum 0 here. If these two are repeating, this means we have a sum 0 here from this plus 1 to this, right? Because this has to be the L minus 1 index. So even if you have multiple repetition, that points to only one thing, that the subarray between them is giving a 0 sum. Okay. Now, how do we solve this problem? So one thing should be clear to everyone, that the first step is that you create the prefix sum array. How can we create the prefix sum array? This is very easy task. You can have P0 equals to A of 0, because the first number is going to be exactly the same. And then for building the rest of the array, you can just keep calculating. You can just keep adding the current value to the previous prefix sum, right? Prefix sum of I is nothing but the previous prefix sum, whatever is the sum till now, plus whatever is the sum of the current element. So now we can run a loop from I equals to 1, I less than n, I plus plus, and then you can say P of I is equals to P of I minus 1 plus A of I. This gives you your complete prefix sum. Now in this prefix sum, you just have to check whether there are two numbers which are repeating or not. Is there any data structure that we know which can solve this problem very optimally? You just have to check whether there are two numbers which are repeating or not. How do you check for a repetition of a number? You can have a hash map, right? Maybe you can have an integer here and a boolean, right? When you get 4, you store true. When you get 6, you store true. When you get another 6, you know that 6 has already occurred. If 6 has already occurred, this means that there is a subarray which is giving a 0 sum. If you also want to find what is the length of the subarray, instead of having the boolean, you can try to store the index here. This also becomes integer, and now you can say that 4 occurs at index 0, 6 occurs at index 1, then 6 again occurs at index 2. This means that from this index, this plus 1 to 2, we have got a subarray which is giving us sum equals to 0. Okay, let's take this example which we initially had, this one, right? You can have your key and value. Key is the sum, value is the index in the hash map. You get 4 sum at index 0, then you get 6 sum at index 1, 3 at 2, and then you again get 4 at index 3, right? Now we had discussed, right, that keys are going to be unique. So once you get another same key, you can just check that this key is already present in the hash map and the starting index was 0. This means from 1 to 3 I have an array which is giving sum equals to 0. Okay, does this make sense to everyone? What is the time complexity of this complete problem, of this complete algorithm? First of all, we have calculated the prefix sum. This costs us order n. While calculating the prefix sum only, you can just also enter in the hash map, right? Here only, what you can do is you can do your map dot put, or first maybe you can check if map dot contains pi. This means that you have found a subarray, you can directly return true, right? Else you can say map dot put pi and comma whatever you are storing, whether it is index or whether it is your true or false, right? And this is going to solve the problem. Overall time complexity here is order n. Okay, so guys, I will now end the session. Please do solve all the problems. Thank you guys.
Hello everyone. So today we have the topic as hashing, and I am Paridhi. I am a software developer at InterviewBit. So today I have selected two questions basically that I'm going to discuss here, and it's basically how important they are from interview point of view. So I have selected them, and so today we are going to do first question is anagram. So let's quickly dive into that. Okay, so today we are going to do our first question, and that problem is anagram. This is a very famous problem. This has been asked in Amazon, Microsoft, Goldman, as you guys can see. Very important from the interview point of view. Let's quickly see what it says. Okay, so given an array of strings, return all groups of strings that are anagrams. Okay. So represent a group by a list of integers representing the index in the original list. Fine. So we are given a group of anagrams, and basically we have to group the same, basically the anagrams together. Okay. So let's see the example for clarification. First of all, what is an anagram? So it's a word, a phrase or name formed by rearranging the letters of another, such as spar is there, formed from rasp. Okay, so basically anagram is a word in which two strings can be said as anagrams if they have same characters, right? And the frequency of the characters is also same, but their order is different. Okay, so here as we can see that S is present in spar and S is also present in rasp. Then P is present in spar and P is present in rasp. Likewise, A is present in spar and A is present in rasp, and R is present in spar and R is present in rasp. Fine. And these are the only characters. So these characters are basically jumbled, right? So these are known as anagrams. Now, given the example, we have cat, dog, god, and TCA. Fine. So these are the anagrams, and we have to group the anagrams together, right? Okay, fine. So we have cat, and I can see that 1 and 4 are anagram. That means cat and TC are anagrams. Okay, fine. They have same set of characters and frequency is also same. Makes sense. And dog is there and god is there. They both are anagrams. Fine, makes sense. So they have same basically characters and frequency is also same. Fine. Okay. So what do you think we can do? What is the first thing that comes to your mind? So what I can think of is that from these two anagrams as given in the example over here, the spar and rasp, right? They have same characters and also the frequency same. So maybe if I like sort them, they should give the same result, right? So if I sort spar, I should get the same result as if I sort rasp, right? Does that make sense? Exactly. So you guys have started to reply and you are on the right track that we can sort them. And after sorting, what is the thing that we are going to get? Let's see. So let me share my screen first of all, the notepad screen. So here we have, so in the example, we have, fine. So let me just copy it down. So we have cat, dog, and God and TCA. So I'm just copying it down on here. So, okay. So if I sort them, this will become ACT, right? And if I sort, so if I sort dog, I will get DGO, right? If I sort God, I will again get DGO. And if I sort TCA, I will, okay, so wait a minute, it just got auto corrected. DGA, sorry, DGO, and this will also be DGO, and this will be ACT, right? So that means here we know that CAT, as in the example, CAT and TCA are anagrams, and when we sort them out, then ACT and ACT we have got the same string, right? Okay, that means anagrams will have the same string, makes sense. And likewise in dog and God, DGO and DGO, they have the same string. Now, what can we do to group them up? So as someone of you has have said that we can hash them up correctly. That perfectly makes sense that basically here the sorted string can act as a, so here the sorted string can act as a, the key, right? The key is the sorted string and the value are going to be the indices of the anagrams. Does that make sense? So here the, so let's actually number them up. So we have 1, this is 1, this is 2, this is 3, this is 4, and we want the indices only, right? So indices are starting from 1 in this case. So basically the key here for CAT is going to be ACT, and here we are going to have the value will be a we can say a vector where we can store the indices of the anagrams. So ACT is a string and CAT is an anagram for that. So that means we can have in a vector we can have 1, and also this TCA is also, if we sort it up, we will get ACT, right? So that means the same string, and so the value is going to be 4 over here, right? So that means we have actually paired up the anagrams, the main task, right? Now the second string is DGO, right? And we can pair the strings that are forming the anagram. So that means 2 and 3. Does that make sense? So, right. We can do it in various ways. We can even hash them up in various ways. We can use frequency arrays as well. So you can do it in any way, right? So let's just code it up. So I think most of you are ready for this. Let's code it up. So here we have the screen and let's quickly code it out. Right, okay. So basically we will be keeping, first of all, we need a vector of vector for the answer thing, for storing the answer, right? So vector of int, and also we need the map, sorry, we need a map, unordered map. So we'll basically do int, comma, okay. No, sorry, not int. We need string, right? We need string and we need a vector of int. Let's call it maybe group, right? These are the groups. And now the task is that we have to basically iterate through the vector of strings that is given to us. So let's iterate through it. So I will go from 0 to a dot size, right? And I++. Now, okay. So we will take the first string. Let's take it in. Let's say we will actually have to generate the copy of the string because we have to sort them up, and also we need the original string, right? So therefore we are maintaining a copy. So let's take it in here and this will create a copy. Now let's sort the string. So let's sort the copy string. So cpy dot begin, then cpy dot end, right? So we have sorted, and now the task is that we can actually hash it. So that's what we are doing. So let's hash it. So the groups is the map that we have taken, and this is copy, right? So string is copy that we have sorted. Okay, so we have sorted it, and let me see if there are some comments. Okay, so now what shall I do? May I get it in the comments? What shall I write? So basically I can push, if that copy is present, I can push the index value, right? So after sorting this copy string, the string at AI, if after sorting we get a string which is there in the hash, right, which is present in the key, we can actually push I+1 to that. It's exactly what we have done in our notepad, right? So we will do it for all the strings, and finally after doing it, we actually have to iterate through the map. Does that make sense? That we have to iterate through the map. So let's do it. Groups is the map. Iterator, let's say, is IT. Now we will simply move through it. So that means IT equal to, that is groups dot begin. Then IT is not equal to groups dot end, and IT plus, right? So we have to just take the value, right? So here we have actually maintained an answer variable, answer array, and we have to basically push the entire vector that we have created in our answer, in the main answer, right? So basically we will be pushing back IT, that means the iterator dot second, and here we can simply return the answer array, right? So does this look fine? Please check, everyone. Are you guys coding with me? Yes. So basically for that, we are actually storing the indices only, right? So Nilesh, we are storing the indices only. We actually have taken the string in the copy string, that means the extra string. Then we have actually sorted this copy string, and here we need not maintain the main string. Basically we just want the index of that, right? So here we are pushing the index, right, just as we have seen in the notepad. So that's what we are doing. Let's try it now. Let's see if it passes. Oh, sorry. So this should be pushed back. Great. Let's see if it gets submitted. Cool. So we have done a good job, and we have scored 338 out of 350. Not bad. Okay, so have you guys got it? Have you guys got it? Are you guys with me? Is it clear? Shall we move to the next question, guys? Cool. Do submit it with me, right? Be here with me. Okay, so now let's do the next question of the day, and the next question is, so here I am taking the longest substring without repeating characters. So here is our question. Let's proceed to it. This question has been asked in Amazon, and not only Amazon, I have heard previously, as in recently, that it has been asked in various other companies as well. Can't remember the name right now, but yes, this is a very important question. So let's get to it. Okay, so Ashish says he has a question. In interview, are we allowed to use inbuilt function? Okay, so basically it's like when you are asked to implement something, which is, let's say you are asked to implement a substring function. In that case, you cannot use it. Or let's say you are asked to sort the array. So the trivial question is that, so the main question here is that you have asked to sort it. So how can you use the inbuilt function, right? In that case, you have to actually perform the sorting with the various algorithms you have. You can't use inbuilt function in that case, right? So here the question is different. You can use the inbuilt function in this case if it's not mentioned. If it's mentioned that you cannot use, then you cannot use, right? So it actually depends. You can actually ask your interviewer about it, that if you can use it or not. Make sense? Cool. Okay, great. So guys, let's move on to the next question. And the next question is longest substring without repeat. Okay. So let's see. So the question says that given a string find the length of the longest substring without repeating characters. Okay, so here we are given a string. This is the string, let's say, and here it says that ABC is the longest string and the length is 3. That means ABC is the longest such substring in which there are no repeating characters. As you can see that, okay, ABC has unique characters. Okay, so basically we want a substring out of a long string which has only the unique characters, right? Which doesn't have a repeating character basically. In the second example, as you see that we have so many B's over here. And that means here the substring is just a B. That means of length 1 that has a unique character. If we try to extend this up, that means if we try to make the length 2, then definitely we will get BB, and length of 2 doesn't have unique characters. Does the question make sense to everyone? Okay. Could you elaborate more? That what would you do? Guys, please at least come up with the brute force approach. I would like to discuss it with you all. That what do you have in your minds? Can you guys think of the brute force approach for this question? Is the question clear to you all? Okay. So guys, please think on this question, okay? And then in a minute, we are going to proceed with the solution. Okay. So Garima says that please explain the question again. Sure, Garima? So here it says that you are given a string, okay? You are given a string and you have to find the length of the longest substring without repeating characters. Now, first of all, do you guys understand what a substring is? So a substring is that when you take, so here if I say that this is a string, right? So what are the substrings of this string? So let me actually show you my screen. Cool. So here is my notepad screen and let's remove this. So here we are discussing the longest substring without repeating characters. Okay, so let's say I have a string A, B, C, D, and or B, C. Okay, A, B, C, B, D. Now, first of all, what are the substrings of this string? So A is a substring, then AB is a substring, then ABC is a substring, ABC B is a substring, then ABC B is a substring. Okay, then starting from B we have just B, then BC, then BCB, then we have BCBB, right? Then starting from C we have C, then CB, then CBD, and starting from B we have just B, then BD, and then starting from D we just have D. Does that make sense that these are the substrings of this string? The consecutive characters. Garima, is the question, so the question says that once. So basically you have to find the longest length of the substring that has unique characters. Here such a longest length is just ABC, because if we consider any length which is beyond 3, then that has a repeating character. So if we have let's say ABCB, right? So in this case also we have 2 repeating characters, as in 1 repeating character, that is B, right? So B occurs 2 times, which we don't want. So the question says that you have to find the longest substring without repeating characters. Am I clear with the question, guys? Am I clear with the question? Okay, great. Okay, so let me clear this up, right? Okay, so let me actually build your solution, then you will be more clear. Okay, so the brute force approach that comes to my mind is that we can generate all the substrings, right? We can generate all these substrings and we can check if these substring consists of unique characters or not, right? So how to check if a substring consists of unique characters or not? So basically for that purpose, we can maintain a hash map. What's it? So we can maintain a hash map that will tell us that if some character is already present in our string or not. Does that make sense? That we can use a hash map because it tells us in just order of one time that, okay, if some character exists or not, already exists or not, right? So this is the brute force approach. So does anyone know that how many total substrings we can create out of a string? How many total substrings are there? Okay, so total substrings are n into n, wait a minute, n into n plus 1 by 2. Okay, these are the total number of substrings that we can create. and where n is the number of characters in the string. Okay, now so once we generate all the substrings, and then if we check with the help of a hash map that if that particular substring has unique characters or not, then the time complexity for first of all for generating the substring is going to be order of n square. Okay, because total we have n into n plus 1 by 2 number of substring, therefore the time complexity of generating these many substrings is order of n square. Now we also have to check it with the help of a map if it consists of unique characters or not. So for that it's again going to take order of n, because why? Because we for maintaining the hash map it's going to take again order of n. So the total number of time complexity, the total time complexity is going to be order of n. Does that make sense to everyone? Cool. So the time complexity is going to be n cubed, but it can be further optimized if while going through our second loop, we can actually check on that pace only if we are getting the unique characters or not. So what I'm saying is that while maintaining the second for loop, in the second for loop itself, we can check that substring from I till j has unique characters or not. And this we can do in our for loop only, the checking part. We don't have to do it separately for checking the unique string. Okay, so then the time complexity will reduce to order of n square, right? Because here we will be doing it in our second for loop only. We will be checking it in the second for loop only. Does that make sense, guys? Is it clear now that why n square? So n square is because while generating a string, let's say I am at A, so the string is, wait a minute. Let's say the string is A, B, C, D, D, right? This is our string. Now I'll keep my I pointer here, and initially the J pointer will also be here. Okay. Now we will also maintain a map side by side, and we will put the character in the map that if so for checking if it's unique or not. Right now in our map A is not there, right? So we will put that okay, A is not there, that means A is unique. Let's put it in our map. So first we will check that if some character exists in the map or not. If it doesn't exist, that means that character is unique. Once we get to know if that character is unique, then we can add that character in the map. Okay, so okay, now we have done it. So we have checked for string A. Now we will move. So now we have AB. So we have in the map we just have A till now, right? Now we will check that if the character at B is in our map or not. If it's not present, that means it's a unique, right? That means it's unique. But once we have checked that if it's unique, we will add it to our map because we have already taken it. So are you guys able to relate that how in the second loop only, that is while moving our J, we are able to check in the map. That's why the complexity is order of n square. Okay. Do try to dry run it on your own, right? And then I am sure that you are going to get it. And if you are still confused, then you should definitely try to code that up. Now I would try to, so here we are now. So the time complexity of the brute force solution is order of n square, right? Or I would say a little optimized solution is order of n square. But here we are generating all the substrings. Do we really need to generate all the substrings? So let me make my point clear from here. So we have A, then AB, then ABC, ABCB, ABCBD, right? So here we are actually generating all the substrings. Here I am trying to make my point clear that we actually don't need it. So I can figure it out. Let's see if you are able to. This is our main substring basically, and here we have all the substrings. Okay. So if you see here in the third also we have to maintain the length as well, right? We have to return the length of the longest string. So when we had 1, the length is equal to 1, right? When we had AB has unique characters, length become 2, right? Then we have ABC, then length become 3, right? Because ABC has unique characters as well. Makes sense, right? Then we have ABCB. That means it doesn't have unique characters. Length is still 3, right? Then again ABCBD is there, and length is equal to 3 again because it doesn't have unique characters, right? So that's how we will keep on going on, and the length will remain 3 entirely. Now the point that I'm trying to make over here is that if you carefully look, then here we have ABC, right? We have ABC, and once we got this fourth B, we come to know that okay, this string can have a length of 3. Then as soon as we are moving to B for length of 4, for checking for length of 4, the strings doesn't have unique characters. Now if you see, then in the second step we are generating ABCBD. Do we really need to do that, guys? Do we really need to check for ABCBD once we have checked for this? No, right? Why? Because here we have already checked that ABCB is non-unique. Then even if we add D, that doesn't make any sense, because here till this point this is not unique. So in any way, if we try to add more characters, that will still be non-unique, right? So that means this is redundant. So why are we doing something which is redundant, right? So we can ignore that. So this is the first point that I tried to make. Now we can actually, now the second point that here to be seen is that once we have got this B, right? Once we have got this B, so here from this A, I am sure that my substring having a unique characters starting from A more than of length 3 is not possible, right? Does that make sense? That starting from A, if I have already got the repeating character and if I had any more character, now it won't create a unique string at all, because here I have a non-unique character. That means starting from A, I have just ABC as a length, right? Now here we have, the point here to be seen is that even from B, if I start, I can get at most 2, I can get the length of 2, right? Where the string length is 2 of the unique characters, right? So that means from A, I can get the maximum length of 3. From B, I can get the maximum length of 2. But starting from C, there is a chance that I get a length of unique characters, a substring of length, a substring of unique characters which is more than 3. Does that make sense? So now here comes the point to do what I can feel is we can do sliding window, right? As suggested by Nilesh in the comments, we can do sliding window. So let's see how can we do that. So let me just remove all of this. We have A, B, C, B, D. Now in my sliding window, I will keep a window. I will start the window from A. Okay. In the sliding window, we have 2 pointers. Okay. One is left pointer and one is right pointer. So I'll keep both the left and right pointer at 0th position, which is A, right? Okay. So A is unique, and that we are going to see it from the, we are going to do it from the map, right? So we are also keeping a map. So let's keep a map. A has a, so we can maintain an index. Okay. So we can maintain an index. Let's also put the indices 1, 2, 3, 4. Right, we can put an index over here. That means A is at index 0 and A we have already taken. Now let's try to expand the window. Before that, we will also keep a length variable which will keep the track of length. Length right now is A. Now we will move our R. So now the window has become from A to B. B is also not present in the map. Let's make the length 2, right, and add B to the map. Index of B is 1, right? Now let's increase R. So R is at C. So C is not there in our map. Let's include C in the map with the index, right? Also the length has become 3. Now let's move R. Okay, as soon as we move R, we saw that now we don't have any unique characters. So that means length will remain same. And now we will move our left pointer so that we can actually remove the previous occurrence of B, right? We will move our L till the point the occurrence of B becomes 1 only, right? Does that make sense? That we will move it till the point the occurrence of 1 becomes 1. Okay, so let's move our L now. So as I move my L moves to B, right? L moves to B and R is still at 3. Okay, L is at 1 and R is at 3. Now we will, so A has gone out of window. That means L to R is the window. A has gone out of the window. So remove A from map. Okay, we will be removing A from map. Now we will check that still is the element, is the character at R still present in the map? Well, yes, it's still present. It means that it's still the part of the window. And in that case, we will again move our L. So let's move the L and L comes over here and B will remain at 3. Now B will be gone. That means here. So we actually remove this B from the window. Let's remove it from here. Now we will check that, okay, is B present now? Is B present in the map? Well, yes, it's not present now, right? It's not present. That means we can include this B in our map now. We can include this B with its current index, which is 3. Okay, which is 3. Now we can start moving our R again. So let's move our R. Now R comes to 4 and B is not present in the map. Length will remain 3 only because L to R, the length is still 3. Let's include D in the map. Now D becomes, so D is at position 4. Okay, and now let's move our R, and now R, there are no more characters, therefore we will simply stop, and whatever will be the length, we will simply return it. So this is how we can process it using sliding window. The time complexity of this approach is going to be just order of n, because we are iterating to each character not more than twice, because one with the left pointer and one with the right pointer, right? So as we are moving our left pointer and as we are moving our right pointer, so we are not coming to any character more than twice. Therefore, the time complexity is going to be 2 into n, which is nothing but order of n, right? We don't consider constants. And the space complexity is order of n again, because here we are using a hash map. Does that make sense? How we have beautifully come across a good, just by building some, observations, we have come to this solution. Does that make sense, guys? Shall we code it? Great. Cool. So let's code it up. Here we are. Now let's quickly do this. Okay. So first of all, I have to maintain an answer, which is, let's say, at present int min, right? We want the maximum value. So we will initialize it to int min, or we can initialize it to 0 as well. It doesn't matter, right? Okay, so we can, the left pointer we will keep, which is initialized to 0. And also we will keep a right pointer, right, which is initialized to 0. And also we will keep a length, right, which is again 0. Now we will be iterating through our string. We will be iterating it with the help of right pointer. Right pointer, so let's keep the right pointer in the loop. So let's initialize the right pointer here only to make it more readable for you guys. So right is less than a dot length, then right plus plus. Okay, and we will, okay, so we have to take a map as well, right? So we will take a map, and that will be map will be of char comma int, because we will be maintaining the index. Make sense? We will be maintaining the index with each character. Now, okay, so if the character at right is present in the, so it's not present in the map, right? So how we will check that? M dot find, right? M dot find is equal to M dot end. That's how we will be checking that if character is not present in the map. So if it's not present, we will simply do what? We will simply do M at A of right is equal to I. Sorry, right. Here we are actually assigning. So here we are doing nothing, but let's say we have A, B, C, D, D, right? So here we are doing nothing. In the map, we will be storing A mapped to 0. That means the index of A. Okay, that's how we will be storing it. Now, after storing it like this, what to do? Let's increment the length, right? Because we have actually found a new character we have included in our map. Let's increment the length. So after incrementing the length, we are done till this point. Now, what if the character is already present, right? So for that, we will use a else block, and in the else block, we will be actually moving a left pointer. We will be moving the left pointer till the point. So let me just write it and then I'll make it clear maybe. Okay, so let me make it clear first. So here, what my point is that I have, let's say, L here and my R is here, okay? And now A, so let me actually change the map. The map will be for A it's 0, for B it's 1, for C it's 2, and again B comes, right? So I will be moving my L till this point. That means the index of previous B plus 1, because we actually have to remove the first occurrence of B. So we will be moving our L till the index of this B, right, plus 1. So here, let me write it. So while left is less than equal to M at A at right, we will be moving our left pointer. And what more do we have to do? Moving our left pointer, and we have to erase the occurrence of whatever is left behind, right? So that means M dot erase A at right. Okay. And also we have to do one more thing. So we have to reset the length. Okay, we will be resetting the length. We have maintained a global variable. That means this is, let's say this is the answer. But as our left and right shifts to this place, that means L comes over here and R comes over here. Again the length, so we will also maintain a variable length. So now it will become 2. Okay, it will become 2. That means the current window size. And that is given by what? That is given by right minus left plus 1. Okay, and also we will be updating our answer to max of answer comma length. And finally we will return the answer. Let's see if it works. Are we missing on something? Does this look fine? Okay, so we actually have to do one more thing over here, and that thing is that we actually have to write the new index, right? So here, let's say A was gone, and now the new index of B is equal to 3, right? So that means it's equal to nothing but M at A at right is equal to right, and that's all. Let's test it. I'm really sorry I didn't see that. Let me share it again. Don't worry, I will explain the code. Okay, so you guys want me to just explain it. Cool. It's good that you have understood the logic, and I'm sure that you will all will be able to code it. Let's see. So here I am maintaining the answer, which is initialized to int min. Okay, then we have a left, that is the left window, and this length is basically the to keep track of the length we have, right? This length is actually from left to right. Okay, now we also have a map that is from map to character to int, that character map to the index. Okay, now we with the help of this right pointer, we will actually be iterating through our string. Okay, and while iterating through the string, we will check that if the character is already present or not. So here we are actually checking if the character is not present. Okay, so the character is not present, so we will actually put the character with the index in the map. Okay, and also we will increment the length. So this is when character is not present. But if character is present, in that case we will be moving the left pointer. Okay, we will be moving the left pointer till the point. So actually I have shown it to you in the editor. I think you have seen it there, right? You have seen it there. So we are actually moving our left pointer till the first occurrence of the repeating character in is gone. Okay, it's gone. So then we will do left plus plus, and we will erase the character that we have left behind. Okay, and then we will do it till the character at right pointer, which we found repeating in the current window. So till the repeating character is no more repeating, we will then add the new index of that character in our map. Make sense? We will add the new index of that character in the map. Does that make sense? So, okay, let me complete it and then I'll get back to your questions. Okay. So here we have the character with its new index, and also now we will reset the length to the length of the current window, right? To the length of the current window, and then we will update our answer. We will keep on doing this, right? So length will have the size of the current window, and this answer is the global answer that we have. So whichever is maximum, that will come in our answer, and we will return the answer. Okay, we will return the answer. Let me try to submit it. Let's see if it gets submitted. Okay, it failed. Where did it fail? Okay, sorry. We need to erase the left, not right. Okay, and let's see it now. It's still not passing. Let's see if this works. Yes, it worked. So first we have to basically erase, and then we have to do left plus plus, right? Okay, so there was just a little bug. Okay, so is everyone fine with this thing? Okay, so basically you should use set when you just have to keep track of that particular character only, or I would say that particular data only, as in when you don't have to map anything, right? So here we see that we actually map the character to the index, right? So that's why we used a map, because keeping the index also was necessary to move our left pointer, and therefore we preferred map over set, right? Does that make sense? Execute now that why do we need to keep map over here, why not set? We actually made a streak today, right? So Pavandeep, I would say that yes, maths is important, but competitive programming is more than maths Olympiad, right? So it's more than maths Olympiad, that I would say. But yes, it will definitely help you, right? Because in competitive programming, we can see maths a lot. So yes, that's a good question, Pavandeep, that you brought up. So this was it from my side. These were the questions, and I hope that you enjoyed them, right? So see ya, bye bye, take care, stay safe.